Hello.
हेलो हेलो, आवाज आ रही है? हेलो हेलो।
Good morning to all attendees of this session. Today, I'm sure we'll have a very fruitful, technically rich session. And the first speaker, the Honorable Mayor of Indore City, is on his way. Very soon, he will be here with us. I request that uh, the mobiles should be please switched off, and let us see how Indore was made the cleanest city of this country, not once or twice, but 6 times in a row. So I'm sure it's a kind of a popular talk which you will enjoy. So just bear with us for some time while he is on the way. Thank you. Excuse me, I have a request to the people who are sitting at the back. Please come forward. Please, all of you. The students here, you don't have to be a backbencher here. Please come forward.
हेलो। सुनिए, देखिए। हेलो, चेक माइक चेक 1 2 3 4। हाँ। आ रहा है, सुशील ने किया।
Check. Hello. Check. Check. Hello. 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 Check. Hello. Check. Hello. Check.
Raja Ramanna Center for Advanced Technology, a constituent unit of DAE, has India's only two synchrotron radiation sources, Indus 1 and Indus 2. When a moving high-energy electron is bent by a magnetic field, it emits radiation called synchrotron radiation, which is used for experiments in experimental stations called beamlines. There are 19 operational beamlines, among which 2 beamlines were commissioned in the last 3 years. The beamlines are national facilities dedicated to the utilization of X-rays for the study of materials. Experiments for Mangalyaan and Chandrayaan 1 and 2 missions for the calibration of detectors and validation of software have been carried out. Determination of the crystal structures of materials for understanding and enhancing their properties are carried out. Proteins present in all living organisms have extremely complicated structures which can be easily determined at a synchrotron beamline. Uranium-based nuclear fuel have been studied, which is important for fuel production and reprocessing. Detailed measurements and analysis have confirmed the non-toxicity of mercury-containing Ayurveda medicine Ras Sindura. X-ray lenses developed at Indus have been used for in-house applications and at the Diamond Light Source, UK. Imaging of the internal structure of tissues and human bones have been carried out. To further enhance the properties of synchrotron radiation at Indus 2, 3 insertion devices have been commissioned in the last 3 years and the related beamlines are being constructed. The total number of user experiments have been increasing steadily and was 639 in 2016.
Sheetal Vahak Yantra. Shivai is an economical and eco-friendly liquid nitrogen-based transportable refrigerated container for perishable items like fruits and vegetables of farmers, pharmaceuticals, dairy products, etc. It can be transported on any carrier like train or truck or built on any chassis of vehicle. It is designed to withstand rough roads without maintenance problems. Shivai has successfully completed 1000 km of road trial. This development will enable farmers to transport produce without quality degradation.
Light is ubiquitous in both its presence and its applications. Light makes life possible on Earth and also allows us to delve into the depths of the universe to unravel its myriad mysteries. Raja Ramanna Center for Advanced Technology, Indore, an R&D unit of the Department of Atomic Energy, Government of India, is dedicated to advancing the science and technology of light. RRCAT is home to 2 major sources of light, namely lasers and synchrotrons, and the Light Exploratorium is dedicated to generate curiosity and increase awareness in this vibrant field of science. Under Azadi Ka Amrit Mahotsav, Light Exploratorium was inaugurated on 8th July 2022 by Padma Vibhushan Dr. Anil Kakodkar, Chancellor HBNI, former Chairman AEC and Secretary Department of Atomic Energy, Government of India. The Light Exploratorium is housed in the erstwhile Sukhnivas Palace, which was a summer recreational point developed by the Holkar dynasty of Indore in the year 1903. The palace is situated on the banks of Bhamori Lake and is surrounded with natural beauty and rare species of flora and fauna. The Light Exploratorium at RRCAT, spread over an area of about 630 square meters, is a unique and one of its kind museum in the country that showcases light in its various manifestations and their applications. The Light Exploratorium houses about 25 exhibits spread over 2 floors in the Sukhnivas Palace. The exhibits are hands-on models that students can experiment with to understand the various properties of light and their uses. The Exploratorium hopes to act as a bridge between textbooks and formal laboratory activity in understanding light and serve as a teaching aid for science teachers in explaining about light and its properties. The exhibit layout starts in a central hall which houses a banner with a timeline of important events associated with light in the history of mankind. The bottom half of this banner displays the electromagnetic spectrum in all its glory, starting from very low frequency and all the way up to gamma rays. Subsequently, one walks through various exhibit rooms in sequential fashion, exploring the wave nature of light, the particle nature of light, geometrical optics, the finite speed of light, biological effects of light, physiology of vision, etc. An exhibit on the Raman effect is set up in the room dedicated to Sir C.V. Raman. The basement floor houses exhibits on discovery of lasers, modern light sources, applications of light in industry and biology, etc. There is an exhibit dedicated to our star, the Sun, in the Sun Room, followed by an exhibit on light and gravity demonstrating the use of laser interferometer for detection of gravitational waves. The Light Exploratorium endeavors to make learning about light both interesting and fun. The exhibits in the Light Exploratorium will be constantly upgraded and modified so that people visiting it after a while would have something new to learn about light.
Raja Ramanna Center for Advanced Technology, a constituent unit of DAE, has India's only two synchrotron radiation sources, Indus 1 and Indus 2. When a moving high-energy electron is bent by a magnetic field, it emits radiation called synchrotron radiation, which is used for experiments in experimental stations called beamlines. There are 19 operational beamlines, among which 2 beamlines were commissioned in the last 3 years. The beamlines are national facilities dedicated to the utilization of X-rays for the study of materials. Experiments for Mangalyaan and Chandrayaan 1 and 2 missions for the calibration of detectors and validation of software have been carried out. Determination of the crystal structures of materials for understanding and enhancing their properties are carried out. Proteins present in all living organisms have extremely complicated structures which can be easily determined at a synchrotron beamline. Uranium-based nuclear fuel have been studied, which is important for fuel production and reprocessing. Detailed measurements and analysis have confirmed the non-toxicity of mercury-containing Ayurveda medicine Ras Sindura. X-ray lenses developed at Indus have been used for in-house applications and at the Diamond Light Source, UK. Imaging of the internal structure of tissues and human bones have been carried out. To further enhance the properties of synchrotron radiation at Indus 2, 3 insertion devices have been commissioned in the last 3 years and the related beamlines are being constructed. The total number of user experiments have been increasing steadily and was 639 in 2016.
Sheetal Vahak Yantra. Shivai is an economical and eco-friendly liquid nitrogen-based transportable refrigerated container for perishable items like fruits and vegetables of farmers, pharmaceuticals, dairy products, etc. It can be transported on any carrier like train or truck or built on any chassis of vehicle. It is designed to withstand rough roads without maintenance problems. Shivai has successfully completed 1000 km of road trial. This development will enable farmers to transport produce without quality degradation.
Light is ubiquitous in both its presence and its applications. Light makes life possible on Earth and also allows us to delve into the depths of universe to unravel its myriad mysteries. Raja Ramanna Center for Advanced Technology, Indore, an R&D unit of the Department of Atomic Energy, Government of India, is dedicated to advancing the science and technology of light. RRCAT is home to 2 major sources of light, namely laser sensing neutrons, and the Light Exploratorium is dedicated to generate curiosity and increase awareness in this vibrant field of science. Under Azadi Ka Amrit Mahotsav, Light Exploratorium was inaugurated on 8th July 2022 by Padma Vibhushan Dr. Anil Kakodkar, Chancellor HBNI, former Chairman AEC and Secretary Department of Atomic Energy, Government of India. The Light Exploratorium is housed in the erstwhile Sukhnivas Palace, which was a summer recreational point developed by the Holkar dynasty of Indore in the year 1903. The palace is situated on the banks of Bhamori Lake and is surrounded with natural beauty and rare species of flora and fauna. The Light Exploratorium at RRCAT, spread over an area of about 630 square meters, is a unique and one of its kind museum in the country that showcases light in its various manifestations and their applications. The Light Exploratorium houses about 25 exhibits spread over 2 floors in the Sukhnivas Palace. The exhibits are hands-on models that students can experiment with to understand the various properties of light and their use.
नमस्कार सभी अटेंडीज जो इस सेशन के हैं उनको मेरा स्वागत और विशेष करके स्वागत मैडम रेणु जैन जी और पुष्यमित्र भार्गव साहब जो हमारे मेयर हैं। आज यहाँ पे दिस इज रियली ए स्टार स्टडेड गैलरी। फॉर्मर चेयरमैन ऑफ एटॉमिक एनर्जी कमीशन एंड सेक्रेटरी डीएई श्री के एन व्यास जी, मन्ना साहब president of INAE, Nake Saab, the director of RRCAT, everybody is here. So as Nake Saab said yesterday, तारे यहीं पे मैं बोलूँगा सारे तारे यहीं हैं आज। तो with this I would have I have been given a pleasant duty to introduce two special dignitaries, our mayor Shri Pushyamitra Bhargav ji and Professor and Vice Chancellor of Devi Ahilya University, Madam Renu Jain ji, to this the people collected here. It's a very interesting thing. Madam Jain is an academician जहाँ से सारे innovation की शुरुआत होती है और पुष्यमित्र भार्गव साहब is the person who is getting these things implemented on ground. So हम लोग कहीं उसके बीच में हैं. This is the origin, this is the final culmination. So this is what the selection has been made and I think it is quite apt. Just to introduce Shri Pushyamitra Bhargav ji, I had put this thing there, but it doesn't say what he actually is. ये एक जुझारू नेता हैं जिन्होंने हमेशा से जनता के मुद्दों को फाइनली इम्प्लीमेंट कराया है, चाहे वो वैक्सीन के टाइम पे वैक्सीन की लीगल बैटल लड़ना हो, चाहे कान्ह नदी को रिस्टोर करने का इनका प्रयत्न हो. Another thing which I would like to say is अभी 8 महीने पहले since he has become the mayor, he has taken up very innovative things. There is a pump station from where entire Indore gets water supply. It is called Jalut pumping station. He wants to make it completely solar driven. So this is the kind of vision that he has. He is, as I said, he is the youngest additional advocate general of MP. He is an expert in cyber law. So you would have the pleasure of listening to what he has done for the city. यह आसान नहीं है कि एक साथ एक लगातार 6 बार एक सिटी पूरे देश में क्लीनलीनेस के बारे में नंबर 1 हो. But he and his team have implemented it. So this is something for which we should give him a real big applause. और अंत में मैं बस इतना बोलूँगा कि हम वैज्ञानिक लोग जब सोचते हैं तो हम सोचते हैं कि हमने इस प्रॉब्लम का सॉल्यूशन निकाल लिया. Whereas होता ये है कि that is the first step. Then people like Pushyamitra Bhargav Saab, they come up, they adopt this technology, they assimilate this technology, and they are the people who finally get it implemented. तो ये जो process है जो हम लोग करते हैं, that is the beginning. Yes, it is important, and there I would include Madam Renu Jain also, because she is, I'll take the pleasure of saying that she is the person from our side only, but जो काम है उसको implement करना, that is where we have people like Pushyamitra Bhargav Saab. So with this, I would request Madam Jain and Bhargav Saab to please take the seat. So now I hand over the session to Madam Jain.
Namaskar. A very good morning to all present over here. Honorable Professor Vyas, Professor Manna, Professor Pal, uh, Professor Mishra, all the dignitaries, all the esteemed guests, and all the dynamic participants of this prestigious engineering and conclave, which is being held here from 5th to 7th October. And at the outset, I would like to thank Professor Manna and Professor Pal for agreeing us to our proposal for making us a part of this conclave. So I thank you very much, and with the, and I also congratulate the Mayor of Indore, Shri Pushyamitra Bhargav ji, for having won the prize of the crown of becoming the cleanest city for the sixth time in a row. And recently, the Indore city has also been awarded to be the smartest city of India. And this prize was given by none other than the President of India herself. And moreover, he has been very innovative. He has started several new schemes. He has taken several new initiatives as mentioned by the organizers. He has started several new schemes, including internship with mayor. And he has started with issue of green bonds. And so many, one more thing, he has recently opened a challenge for all the students of Indore to give some innovative idea which can help Indore to grow into a green city and clean city. So there are so many schemes he has started, and we are very proud of him as he has been our alumnus. Congratulate him again and again. And I'm sure he is going to talk on green and how he has made this possible to keep Indore in the front row as the first cleanest city in a row for the sixth times. So with these words, I invite him for delivering his talk, and at the same time, I request him to please finish it within half an hour. Thank you so much.
इंजीनियर्स कॉन्क्लेव 2023 के इस अवसर पर मंच पर उपस्थित देवी अहिल्या विश्वविद्यालय की सम्माननीय कुलपति प्रोफेसर रेणु जैन मैडम, यहाँ के निदेशक डॉक्टर एस.वी. नाखे साहब, डॉक्टर के.एन. व्यास साहब, फॉर्मर चेयरमैन ऑफ एटॉमिक एनर्जी कमीशन, ऑल अदर डिग्निटरीज, देश भर के अलग अलग स्थानों से पधारे इस कॉन्क्लेव के डेलीगेट्स, कैट के सम्माननीय सदस्य, स्टूडेंट्स, नौजवान दोस्तों, सबसे पहले तो ये इंदौर के लिए बहुत सौभाग्य की बात है कि सेंटर फॉर एटॉमिक स्टडी एंड रिसर्च का एक बड़ा सेंटर हमारे यहाँ है, जो हमेशा से इंदौर को साइंटिफिकली सोचने का, टेक्निकली एक्सपर्ट बनाने में मदद करता रहा है। उससे भी महत्वपूर्ण बात यह है कि कैट का ये प्रांगण कई बार हमारी स्वच्छता की अलग अलग कंपटीशन में, चाहे सबसे अच्छे कैंपस की बात हो, अच्छे से सॉलिड वेस्ट मैनेजमेंट की बात हो, पब्लिक पार्टिसिपेशन की बात हो, एसटीपी की बात हो, इन सब क्षेत्रों में अलग अलग कैंपस कैटेगरी में अवार्ड्स जीतता रहा है। इंदौर के स्वच्छता का मॉडल हो या पब्लिक पार्टिसिपेशन का मॉडल हो, उसमें कैट ने जो भूमिका निभाई है, उसके लिए मैं पूरे इंदौर की तरफ से सबसे पहले उनका धन्यवाद करता हूं, उनका अभिनंदन करता हूं। साथ ही देश भर से जितने डेलीगेट्स या इंजीनियर्स इस कॉन्क्लेव के लिए आए हैं, इंदौर के प्रथम नागरिक होने के नाते आप सबका मां अहिल्या की नगरी में, देश की सबसे स्वच्छ नगरी में, देश की सबसे स्मार्ट सिटी में, देश का ऐसा शहर जो अपना एयर क्वालिटी इंडेक्स ठीक रखने के प्रयासों में देश में नंबर 1 है, वाटर कंजर्वेशन में जो शहर देश में नंबर 2 है, एक ऐसा शहर जहां आईआईटी और आईआईएम दोनों हैं, ऐसे शहर में आप सभी का स्वागत करता हूं, वंदन करता हूं, अभिनंदन करता हूं। एंड कमिंग टू द एंड बिफोर कमिंग टू द टॉपिक, आप सबको मैं इस बात के लिए भी आमंत्रित करता हूं कि स्वच्छता के साथ साथ ये शहर स्वाद की राजधानी भी है। तो इंदौर के जो सराफा है वो बहुत पुराना हमारा नाइट कल्चर है, और अभी देश भर में सबसे अच्छी फूड स्ट्रीट का अवार्ड भी हमारी 56 दुकान को मिला है। तो आप यदि आए हैं और इन दोनों जगह नहीं जाएंगे तो ये इंदौर आपका आना अधूरा रहेगा। इसलिए मेरा आपको निमंत्रण है कि आप सराफा और 56 जरूर जाएं। इंदौर की सक्सेस स्टोरी, इंदौर की ग्रोथ स्टोरी यदि आपको बहुत कम शब्दों में समझना है तो इंदौर में जब एनआरआई समिट हुआ रिसेंटली इन 2002, द non-residential Indian summit was in Indore, which was inaugurated by the Honorable Prime Minister, and in his speech he started, इंदौर एक दौर है, और उनका ऐसा कहने का तात्पर्य ये था कि इंदौर एक दौर इसलिए है कि ये समय से आगे चलता है लेकिन अपने मॉरल्स को, वैल्यूज को कभी छोड़ता नहीं है, नंबर 1। नंबर 2, देश भर में कोई शहर किसी काम को करने के बारे में सोचता है तब तक इंदौर वो काम कर चुका होता है। और वो इसलिए भी उन्होंने ये बात कही थी कि माननीय प्रधानमंत्री नरेंद्र मोदी जी ने जब देश के प्रधानमंत्री के रूप में 2014 में शपथ ली, उसके पहले जब वो बनारस के गंगा घाट पर आरती के लिए गए थे तो उन्होंने देश से एक आह्वान किया था कि अब स्वच्छ भारत होगा, स्वस्थ भारत होगा। और स्वच्छ भारत मिशन की शुरुआत उन्होंने शपथ लेने के पहले ही शुरू कर दी थी। तो ये देश भर के सब शहरों के सामने एक चैलेंज था कि प्रधानमंत्री जी का इतना कठिन टास्क, एक नौजवान होने के नाते जब मैंने भी उस बात को सुना था तो मेरे मन में आया था कि ये सबसे कठिन काम प्रधानमंत्री जी ने सबसे पहले अपने हाथों में ले लिया, तो ये कैसे पूरा होगा। लेकिन हमको खुशी इस बात की है कि उनके सपने को साकार करने का काम इंदौर ने किया। तो 2015 में जब पहले स्वच्छता के सर्वे की रिपोर्ट्स आई तो हम 47वें नंबर पर थे, और जब हम 47वें नंबर पे थे तब हमारी स्थिति ये थी। ये 2015 की हमारी स्थिति है। तो स्वच्छ भारत मिशन इंदौर के लिए बहुत बड़ा चैलेंज इसलिए था कि शहर की हर कॉलोनी के कोने पे इतने बड़े बड़े लिटर बीन्स, कचरे के पहाड़, पूरी सड़कों पर कहीं भी आपको आवारा पशु देखने को मिल जाएंगे। तो ये 2015 की स्थिति है। ना तो वेस्ट मैनेजमेंट का कोई स्ट्रक्चर था, ना वेस्ट कलेक्शन का कोई स्ट्रक्चर था, और पब्लिक पार्टिसिपेशन, लोगों की जरूर इच्छा थी कि इंदौर स्वच्छ हो, लेकिन उसमें उनकी भूमिका क्या हो ये तय नहीं थी। So there was no mechanism to involve public into the mechanism of cleanliness or into the solid waste management. ये हमारा लेगेसी वेस्ट था 100 इयर्स का, जिसको अभी हम ट्रेंचिंग ग्राउंड बोलते थे। अब तो वो बहुत सुंदर बगीचा है, वहां पर अभी की स्थिति में प्री वेडिंग शूट भी होता है और शादी की पार्टी भी होती है। लेकिन ये वो जगह है जहां 100 इयर्स का लेगेसी वेस्ट था। ये 2015 का ही फोटो है। ये रिवर्स या जो रिवर नाले में तब्दील हो गई, उसमें लगभग 7,200 आउटफॉल्स थे सीवरेज के। लेकिन 2015 में जब हमारी 47th रैंक लगी और उसके बाद एक आइडिया के साथ उस समय के ऑफिसर्स ने, उस समय के मेयर ने, उस समय के पब्लिक रिप्रेजेंटेटिव्स ने और सबसे ज्यादा रेसिडेंट वेलफेयर एसोसिएशंस ने इसको एक चैलेंज के रूप में लिया। डोर टू डोर कचरे को कलेक्ट कर गार्बेज ट्रांसफर स्टेशन और वहां से ट्रेंचिंग ग्राउंड, इसका एक मैकेनिज्म डेवलप किया। बहुत स्ट्रिक्ट रूल बनाया कि सड़क पर कोई आवारा पशु नहीं दिखेगा। आवारा पशु रखने वाले लोगों के खिलाफ बहुत स्ट्रिक्ट कार्रवाई हुई। तो आज ये स्थिति है कि शहर में आपको कहीं भी ढूंढने पर भी खुले रूप से गाय या आवारा पशु एक्सेप्ट डॉग घूमते हुए नहीं दिखेंगे। उतने सालों के प्रयास में आज 2022 देश में लिटर फ्री और बिन फ्री शहर है। केवल हमारी मेन रोड्स पे हमने बिन्स लगाए हैं कि यदि रास्ते में कोई कचरा है तो वो बिन्स में डालें। और इंदौर देश का पहला शहर है जिसने 2 बिन को 3 बिन में कन्वर्ट किया और अपनी जो इनिशियल कचरा गाड़ी थी जिसमें 2 बिन्स हुआ करते थे, गीला कचरा और सूखा कचरा, अब हम देश का एकमात्र ऐसा शहर है। कई लोग हमसे कहते हैं ना कि आप बार बार क्यों जीतते हो, तो मैं उनको कहता हूं कि इंदौर इसलिए जीतता है कि इंदौर में कचरा गाड़ी में 6 बिन्स हैं, प्लास्टिक, नॉन प्लास्टिक सूखा कचरा, 1 बिन गीले कचरे का, 1 बिन ई वेस्ट का, 1 सैनिटरी वेस्ट का, 1 हैजार्डियस वेस्ट का। तो ये 6 बिन की गाड़ी जब घर पे पहुंचती है किसी के सुबह, तो घर के लोग इन 6 तरह के कचरों को अलग अलग सेग्रीगेट करके अपने घर के बाहर डालने के लिए रेडी रहते हैं और इन 6 कंपार्टमेंट्स में डालते हैं। तो घर से सेग्रीगेटेड कचरा इकट्ठा करने वाला, गाड़ी में जाना एक अलग बात है, घर में रहने वाला आदमी 6 हिस्सों में अपने कचरे को सेग्रीगेट करके रखता है। तो डोर टू डोर कलेक्शन ऑफ सेग्रीगेटेड वेस्ट ये देश में केवल इंदौर में होता है। और इसका कवरिंग एरिया जो है अभी 90% है। अभी हमको भी 100% इसको अचीव करना है, लेकिन 90% डोर टू डोर सेग्रीगेटेड कचरा कलेक्ट करना, उसको कचरे की गाड़ी में कलेक्ट कर जो गार्बेज ट्रांसफर स्टेशन बने बड़े 10, उसमें भी उसी सेग्रीगेटेड फॉर्म में कलेक्ट करना और वहां से उसको रिसाइकल, रिप्रोड्यूस या उसका जो भी डिस्पोजल का तरीका है, जो सैनिटरी वेस्ट का या ई वेस्ट का डिस्पोजल मैकेनिज्म आप लोगों ने, साइंटिस्ट ने तय करके बताया है ताकि वो पर्यावरण को नुकसान न दे, उसी तरीके से उसका डिस्पोजल करने वाला देश में एकमात्र शहर है। और इसके आगे की स्टोरी ये है कि ये जो 100 इयर्स का लेगेसी वेस्ट आपने देखा, इसको आपके बताए हुए तरीके से साइंटिफिकली बायो रेमीडिएट करने का काम देश में यदि पहले किसी ने किया तो वो इंदौर ने किया, वो भी रिकॉर्ड टाइम में 2016 से लेकर 2020 के बीच में। और इस मॉडल को माननीय प्रधानमंत्री जी ने कहा है कि ये चूंकि अमृत काल है, भारत की आजादी का अमृत वर्ष है, इसलिए देश के 75 स्थानों पर इस मॉडल को, बायो रेमेडिएशन के मॉडल को हमको अडॉप्ट करना है। वो 75 शहर के लोग, नगर निगम के लोग अभी इस साल इंदौर से उसकी ट्रेनिंग लेकर गए। तो ये मॉडल जिन जिन शहरों में डेवलप हो जाएगा वो अपने आप स्वच्छता में आगे आने लगेंगे और ऐसा कई लोग कर भी रहे हैं। तो स्वच्छ भारत मिशन का स्वच्छता का सर्वेक्षण कोई कंपटीशन नहीं है, ये सर्वेक्षण एक हेल्दी कंपटीशन है लोगों को कॉम्पीट करके इस देश को आगे बढ़ाने का। ये जो मैंने आपको बात की है, ये उसका फोटो है उस गाड़ी का कि ये 6 तरह के कंपार्टमेंट्स उसमें लगे हैं और लोग अपने घरों में 6 तरह का अलग अलग कचरा लेकर सुबह रेडी रहते हैं। गाड़ी की आवाज से लोगों का दिन शुरू होता है और रात को घर का कचरा सेग्रीगेट रखने करने के काम से दिन का अंत होता है। आज भी मैं अपनी वाइफ को भी देखता हूं, मैं आ जाता हूं, खाना खा लेते हैं, हमारी बात हो जाती है, उसके बाद वो घर के बाहर जाती है। मैं क्या हो गया, तुम क्यों जाती हो बाहर? बोली ये कचरा आज ही रात को ही रखना है। तो ये घर की एक आदत बन गई है। तो जो इसका मूल मंत्र है वो है बिहेवियरल चेंज। इंदौर के लोगों ने अपनी आदत को बदला है, जो कि कठिन है, अभी भी 100% नहीं है। कई बार अगर हमारी गाड़ी नहीं गई या लोग देर से उठे या हॉस्टल में रहने वाले जो हमारे स्टूडेंट्स हैं जिनकी दिनचर्या थोड़ी लेट शुरू होती है, तो वहां का कचरा कई बार सड़कों पे या डस्टबिन के बाहर देखने को मिलता है। तो उसको हमने अलग से एक मैकेनिज्म उसका तैयार किया है कि ओपन टिपर से या अलग गाड़ियों से उसको उठाने का हम प्रयास करें, लेकिन अभी भी और अवेयरनेस और बिहेवियर को चेंज करने की जरूरत है। ये मैं आपको बता चुका हूं। ये वो गार्बेज ट्रांसफर स्टेशन है जहां पर ये कचरा पहुंचता है और उसी 6 फॉर्म में अलग अलग बीन्स में कलेक्ट होके। अब इसमें एक इंटरेस्टिंग बात और है कि ये जो डोर टू डोर कलेक्शन वाहन है हमारे करीब 500, ये AICCC एक हमारा सेंटर है जहां से हर गाड़ी GPS से ट्रैक होती है। अगर 1 मिनट से ज्यादा कोई गाड़ी एक स्थान पर रुकती है तो उसको कॉल जाता है कि आप वहां क्यों रुके हो। अगर कोई वैलिड रीजन नहीं है तो उस पर फाइन होता है और उसका एरिया डेजिग्नेटेड है कि उसको इतनी देर में इतना एरिया कवर करना है। तो जो डोर टू डोर कलेक्शन वाहन है उसका टाइम, उसकी मॉनिटरिंग इस AICCC सेंटर से लगातार होती है कि रियल टाइम डाटा आ रहा है कि वो गाड़ी उस समय पहुंची या नहीं पहुंची। अब गार्बेज ट्रांसफर स्टेशन पे पहुंचने के बाद जो पहले ट्रेंचिंग ग्राउंड हुआ करता था, अब वहां पर सॉलिड वेस्ट मैनेजमेंट और वेट वेस्ट मैनेजमेंट का बायो CNG प्लांट बनाने वाला एशिया का इतना बड़ा बायो CNG प्लांट बनाने वाला शहर इंदौर है। तो जो हमारा गीला कचरा है, ये जो हमारा गीला कचरा है, घर में से जितना सब्जी का या जितना भी वेट वेस्ट है, उससे बायोगैस और CNG बनाने का एशिया का सबसे बड़ा प्लांट इंदौर में बना। 550 मेट्रिक टन पर डे के कचरे को प्रोसेस करके CNG बनाने की उसकी कैपेसिटी है। और उससे जो CNG बन रही है वो हम अवंतिका गैस को बेच रहे हैं। हमारी खुद की जो AICTSL की बसेज हैं उसमें वो हमको 5 रुपए कम के रेट में मिल रही है। तो ये बायो CNG वेट वेस्ट को प्रोसेस कर रहा है। वैसे ही जो सॉलिड वेस्ट है हमारा, उसके ब्लॉक्स बनाकर आइदर हम सीमेंट फैक्ट्री को एज अ फ्यूल दे रहे हैं या उसके रीप्रोसेस से जो भी गुड्स बन सकते हैं वो हम दे रहे हैं। तो ये कचरे से वेल्थ कमाने का काम इंदौर ने शुरू करके बताया है। इसको कई सारे और शहरों ने अपने अलग अलग ढंग से आगे बढ़ाने का काम किया। मुझे किसी ने बताया कि उत्तराखंड में ऋषिकेश और हरिद्वार के बीच में कोई स्टार्टअप ने इतना अच्छा प्रोजेक्ट लगाया है कि वो ई-वेस्ट से गोल्ड बना रहे हैं। मेरा मन है उसको एक बार जाके देखने का। ऐसा इनोवेशन हम इंदौर में भी करें। ये वहां जो ड्राई वेस्ट प्रोसेसिंग का प्लांट है, सेग्रीगेट कर कर उसको अलग डिस्ट्रीब्यूट करके। नाउ दिस इज द सीन अबाउट द लेगेसी वेस्ट। जो मैंने आपको 2015 का फोटो बताया था उसमें 2017 की पोजीशन, 2019 और ये 2020, इसको हम वहां, इसका नाम हमने दिया है स्वच्छता की परी। आप भी कभी भी जाकर वहां पेड़ लगा सकते हैं, अपनी किटी पार्टी कर सकते हैं, हाई टी ऑर्गेनाइज कर सकते हैं और उस प्रोजेक्ट को समझ भी सकते हैं, देख भी सकते हैं। लेकिन उसमें 4 चांद तब लगे जब लोगों ने वहां जाकर प्री वेडिंग शूट शुरू किया। पर इसके बाद भी कई सारे लोगों के ग्रीवांस रह जाते हैं। तो ग्रीवांस मैकेनिज्म स्वच्छ भारत मिशन में सबसे बड़ी आवश्यकता है। तो इंदौर का 311 ऐप जो है उसमें कई सारी चीजों को हमने इंटीग्रेट किया है। अभी हमने उसका इंटीग्रेशन ग्रीवांस रिड्रेसल से आगे ले जाकर, अगर हमारा जो ट्रीटेड वाटर है, जो हम एसटीपी से सीवरेज का पानी ट्रीट कर रहे हैं, कुछ तो हम किसानों को दे रहे हैं इरिगेशन के लिए, लेकिन हमने अभी उसमें एक नया इनोवेशन ये किया है कि आपको अपना घर बनाना है, पीने के उपयोग के अलावा अगर किसी भी पानी का उपयोग करना है तो आप 311 पे हमको कहेंगे तो हमारे टैंकर आपको वो पानी किसी दूसरे यूज के लिए सप्लाई कर देंगे। तो इस 311 पे कई सारी सुविधाएं, सोलर सिटी, डिजिटल सिटी, या अभी एक नया 311 से हमने इंटीग्रेट किया है, वो बहुत संवेदनशील विषय है। भगवान ना करे किसी के घर में कोई दिवंगत हो, लेकिन कई बार बड़े शहरों में अंतिम यात्रा के लिए गाड़ियां नहीं मिलती हैं। तो हमने 6 गाड़ियां खरीद के उनको इस पे इंटीग्रेट किया है कि जो 311 पे इसको ऑनलाइन चाहेगा, अगर वो बुक होगी तो उस समय पे वो अंतिम यात्रा का रद्द भी 311 से आप मंगवा सकते हो। बाकी सारी नगर निगम की जितनी सुविधाएं हैं, चाहे प्रॉपर्टी से रिलेटेड हो, सीवरेज ड्रेनेज की कंप्लेंट हो, वो सब इस 311 पे स्वच्छ भारत के इस ऐप पर इंटीग्रेटेड है। इट इज लाइक अ मेयर हेल्पलाइन और सीएम हेल्पलाइन जैसा होता है। तो ये 311 इज अ मेयर हेल्पलाइन। लिक्विड वेस्ट मैनेजमेंट के बारे में मैंने आपको बताया ही है। शहर में यूरिनल्स वाला विषय भी इसमें आया है। तो ऐसे कई सारे पब्लिक पार्टिसिपेशन के मोड पर इंदौर ने अपने आप को आगे ले जाने का काम किया है। लेकिन सॉलिड वेस्ट, लिक्विड वेस्ट या स्वच्छता के आगे क्या? तब हमने सोचा कि पर्यावरण की दृष्टि से भी इंदौर को बहुत काम करने की जरूरत है। इसके आगे हमको अपना एयर क्वालिटी इंडेक्स कैसे इंप्रूव हो, इस पर काम करने की जरूरत है। उसमें भी हमने पब्लिक पार्टिसिपेशन से सबसे पहले हमारे कुछ मार्केट्स को डिस्पोजेबल फ्री किया। आपको डिस्पोजेबल आइटम्स भी इन मार्केट्स में नहीं मिलेंगे। प्लेट, क्रॉकरी, ग्लास भी कांच के या स्टील के कांच जो पहले ग्लासेस चला करते थे, तो 100% डिस्पोजेबल फ्री मार्केट्स। होटल्स और मोटेल्स में लकड़ी और कोयले का उपयोग बिल्कुल बंद किया और सीएनजी पे भट्टियों को ट्रांसफर किया। वैसे ही इनोवेशन के साथ पहले साल में 75 महिलाओं को ई रिक्शा दिलवाए ताकि ईवी का प्रमोशन हो। इस साल उसको बढ़ाकर 111 किया। एक ड्राइव शुरू किया, रेड लाइट ऑन तो इंजन ऑफ। इन प्रयासों से एयर क्वालिटी इंडेक्स इंप्रूव करने के प्रयासों में अभी इस वर्ष इंदौर देश भर में नंबर 1 आया है। तो ये सब पब्लिक पार्टिसिपेशन से संभव हो पाया। लेकिन इस सब के बावजूद आज भी जो हमारा सबसे बड़ा चैलेंज है, मतलब ये एक सक्सेस स्टोरी भी है और एक इनोवेशन करके काम करने का प्रयास भी है और पब्लिक पार्टिसिपेशन का मॉडल भी है, और इंदौर का सक्सेस मॉडल कैसे इंडिया का और ग्लोबल मॉडल बना उसका एग्जाम्पल भी है। इंदौर स्वच्छता में देश में नंबर 1 है, सभ्यता में, संस्कृति में, स्वाद में। लेकिन फिर भी एक ऐसा विषय है जिसमें और हम नंबर 1 है, वो है रईसी। इंदौर के लोग रईस बहुत हैं। ऐसा लोग कहते हैं कि एशिया का सबसे रईस शहर इंदौर है। मैंने भी जब ये बात सुनी तो मुझे लगा कि बड़ा कठिन है, ये कैसे संभव है, इतने तो रईस नहीं है यहाँ, तो सब सामान्य मध्यम वर्गीय परिवार के लोग हैं जो खुद की भी और शहर की भी चिंता करते हैं। तो फिर मुझे लोगों ने बताया कि ये रईस इसलिए है कि हम एशिया का सबसे महंगा पानी पीते हैं, और केवल पीते नहीं है, सुबह अपनी कार भी उसी से साफ करते हैं, बरामदा भी उसी से। तो जो रईस आदमी है जो महंगे पानी से इतना सब कर रहा है, इसलिए वो रईस है। फिर मैंने उसके और आगे को उसको जब समझने की कोशिश की तो पता चला कि इंदौर में पानी लाना और पानी पिलाना, ये जलूद है यहाँ से, जहाँ नर्मदा जी हैं, यहाँ से 75 किलोमीटर पे जलूद है जहाँ से हम पानी पंप करके इंदौर लाते हैं। अभी तक 3 फेज उस पंपिंग स्टेशन के हो गए, जिसमें सिर्फ इलेक्ट्रिसिटी का जो कॉस्ट है उसका इलेक्ट्रिसिटी का कॉस्ट है 300 CR पर ईयर, 25 करोड़ रुपए महीना सिर्फ हमारा बिजली का बिल आता है, प्लस फिर बाद में ओवरहेड टैंक्स, उसकी सप्लाई लाइन, उसका स्काडा सिस्टम, ये सब मिला के लगभग वो जाता है 450 करोड़ रुपए साल का। और इंटरेस्टिंग बात यह है कि इतना खर्चा करने के बाद हम उसमें यूजर चार्जेस जो लेते हैं, मान लीजिए एक घर का खर्चा 1000 रुपए है पानी का लाना और आपको देना, उसकी यूजर चार्जेस हम लेते हैं सिर्फ 200 रुपए। तो 800 रुपए का डेफिसिट है हमको पानी सप्लाई करने में पर हाउस। तो इसको कैसे कम किया जाए, इसके लिए क्या प्रयास कर सकते हैं? तो फिर माननीय मुख्यमंत्री शिवराज सिंह जी चौहान और जो सोलर का अभी देश भर में अभियान चल रहा है, तो हमने ये प्लान किया कि क्यों ना एक सोलर प्लांट वहीं लगाया जाए, वहीं उससे इलेक्ट्रिसिटी जनरेट की जाए और उसको कंपनसेट किया जाए। लेकिन उसके बाद चैलेंज ये था कि वो सोलर प्लांट लगाने के लिए भी 300 करोड़ रुपए लगेंगे। तो वो 300 करोड़ कहां से आएंगे? तो जब देश की फाइनेंस मिनिस्टर इस बार का बजट लोकसभा में पढ़ रही थी, तो उनकी स्पीच में थ्राइस शी मेंशन्ड दैट नाउ इट इज हाई टाइम दैट अर्बन लोकल बॉडीज शुड कम अप विद द सॉवरेन बॉन्ड्स, ग्रीन बॉन्ड्स, या अपनी जो भी आवश्यकता है उसके लिए कॉरपोरेशंस को बॉन्ड्स इशू करने चाहिए, पब्लिक पार्टिसिपेशन से काम करना चाहिए। मुझे बहुत खुशी हो रही थी उनका भाषण सुनते हुए, क्योंकि जिस दिन वो भाषण दे रही थी उसके एक दिन पहले रात को इंदौर को सेबी ने फास्टेस्ट अप्रूवल दिया था अपना ग्रीन बॉन्ड लाने के लिए। और वो ग्रीन बॉन्ड इसलिए था कि हम सोलर प्लांट जलूद में लगाने वाले थे। तो 60 मेगावाट का फर्स्ट फेज में जो हमको सोलर प्लांट लगाना था, तो देश की पहली अर्बन लोकल बॉडी बनी जो अपनी ग्रीन एनर्जी के लिए, अपने पानी के खर्चे को कम करने के लिए ग्रीन बॉन्ड्स लेकर आई। हमको टोटल रिक्वायरमेंट थी आउट ऑफ 300 244 CR की, क्योंकि बाकी का जो बचा हुआ पैसा था वो केंद्र सरकार सब्सिडी के रूप में और कुछ हमको कार्बन क्रेडिट्स के रूप में मिलने वाला था। कार्बन क्रेडिट से पैसे कमाने वाला भी शहर इंदौर है, क्योंकि ये जो कचरा है प्लास्टिक का रीप्रोसेस हो रहा है, इसमें भी हमको कार्बन क्रेडिट्स मिल रहे हैं। तो 20 करोड़ रुपए उससे मिलते, 30-35 करोड़ केंद्र सरकार देने वाला था। तो ऐसे हमको ग्रीन बॉन्ड से 244 CR जनरेट करने थे। तो जब हमने उसका इशू ओपन किया, वो 3 दिन के लिए ओपन हुआ। 3 दिन में 244 की जगह हमको मिले 721 CR। और उससे इंटरेस्टिंग बात, जब उसके फाइनल डाटा आए तो ये पता चला कि देश के हर राज्य ने, फ्रॉम फार ईस्ट टू वेस्ट, जम्मू कश्मीर टू तमिलनाडु, हर स्टेट ने इंदौर के ग्रीन बॉन्ड में इन्वेस्ट किया है। तो इंदौर का पब्लिक पार्टिसिपेशन का मॉडल इतना हिट है कि देश भर के लोगों को विश्वास है कि इंदौर अगर कोई काम कर रहा है तो हमारा रिटर्न सेफ है, सिक्योर्ड है, और 8.25% का रिटर्न उनको मिल रहा है। अभी पहली किस्त उनको मिल भी गई है उसके इंटरेस्ट की, जो भी इन्वेस्टर थे। तो ये इंदौर ने देश भर में अपना विश्वास कमाया है। और ये जो हमारा सॉलिड वेस्ट का मैनेजमेंट का मॉडल है, अब एक ग्लोबल मॉडल है जिसको देश भर से और दुनिया भर से लोग देखने और समझने आ रहे हैं। और आखिरी में मेरे पिताजी मुझे एक बात हमेशा कहा करते थे, मैं कहता था मुझे ये भी करना है, मुझे ये भी करना है, मुझे ये भी करना है, तो वो कहते थे कि एक साधे सब सधे, सब साधे सब जाए। और अभी भी जब अर्बन डेवलपमेंट की बात देश में होती है तो हर प्रदेश, हर शहर ये बात करता है कि भाई बड़ी यूनिवर्सिटीज लेकर आइए, बड़ी इंडस्ट्रीज खोलिए, बड़े स्कूल लेकर आइए, बड़े साइंटिफिक रिसर्च सेंटर खोलिए, तो लोग यहाँ आएंगे। ये एक सोचने और काम करने का हमारा तरीका था, लेकिन वो बदला है, पूरे देश भर में बदला है कि अगर इंदौर जैसे शहर ने स्वच्छता को अपना मॉडल बनाया और एक काम अच्छा किया, उसने पूरे देश के इन्वेस्टमेंट को भी अट्रैक्ट किया। कई सारे बड़े देश के बोर्डिंग स्कूल खुद यहाँ आकर अपना स्कूल खोलना चाहते हैं। देश के कई अच्छे कॉरपोरेट हॉस्पिटल्स लगातार मध्य प्रदेश सरकार के और इंदौर के पीछे हैं कि हम अपना हॉस्पिटल यहाँ खोलना चाहते हैं। कई बड़े रिसर्च इंस्टीट्यूट इंदौर आना चाहते हैं। तो एक मॉडल यदि हम अपना सक्सेस कर पाए तो ओवरऑल होलिस्टिक डेवलपमेंट किसी भी यूनिट का हो सकता है। उसका एग्जाम्पल सेट करने का काम इंदौर ने किया है और इसमें कहीं ना कहीं स्टार्टअप्स, इनोवेशन, साइंटिफिक रिसर्च और अप्रोच उसका भी बहुत इंपॉर्टेंट रोल रहा है। कैट का, आईआईटी का, आईएम का, देवी अहिल्या विश्वविद्यालय के अलग अलग डिपार्टमेंट्स का जब हमको आवश्यकता पड़ती है तो आप लोगों का सहयोग हमको हमेशा मिलता है। इसलिए मैंने शुरुआत में भी कहा था कि कैट ने हर दृष्टि से केवल साइंटिफिकली सोचने में या काम करने में नहीं, उसको मॉडल को अपने कैंपस में उतार कर भी इंदौर के मॉडल को सक्सेस बनाने का काम किया है। इतना कहकर मैं अपनी बात को विराम देता हूं। आप सभी का पुनः इंदौर में स्वागत है।
आपको बहुत बहुत बधाई। इंदौर की जो सक्सेस स्टोरी है वो आपने बहुत अच्छी तरह से शेयर की सबको। वैसे तो एक प्लेनरी टॉक है, लेकिन अगर किसी के मन में कोई बहुत जिज्ञासा हो, कोई क्वेश्चन हो, तो यू आर वेलकम। यस।
नमस्कार मेयर साहब, मैं इंदौर का रहवासी हूँ, यहाँ पला बड़ा हूँ और अभी यहीं रह रहा हूँ शहर में। एक्चुअली आपने जो रईस शहर का बताया पानी का अपव्यय, तो मेरे आपसे निवेदन है, बहुत सारे लोग जो आपने बोला ना कार और गाड़ी धोते हैं, तो जो कम से कम मोटर लगा के पाइप से सड़क पे धो रहे हैं शान से, उनका आप चालान बनाएं, उनको वार्निंग दे और चालान बनाएं, वो बहुत ज्यादा है। और मैं शहर में अपने आसपास लोगों से काफी वो करता हूँ और मुझे ही सुनना पड़ता है।
थैंक्स फॉर।
दूसरा नहीं, एक और है वो पानी का, लोगों के जो टैंक में नल है वो ओवरफ्लो हो रहा है और सड़क पे पानी आ रहा है, उसमें भी आप एक वार्निंग दे, 2 वार्निंग दे, और उनका पैसे से चालान जब तक नहीं बनेगा ये कुछ रुकने वाला नहीं है, और ये बहुत जगह हो रहा है। तो आपसे मेरा वो निवेदन।
नहीं, आपका सुझाव भी बिल्कुल ठीक है और उसको इम्प्लीमेंट हम कर भी रहे हैं, लेकिन वाटर डिस्ट्रीब्यूशन हमारा चैलेंज है, मैं उसको एक्सेप्ट करता हूं। उसमें और पब्लिक पार्टिसिपेशन और पब्लिक को जोड़कर उसकी जिम्मेदारी तय करने की जरूरत है। लेकिन मुझे लगता है ये ओवरऑल तब सॉल्व होगा जब 24/7 लोगों को मीटर से पानी मिले। उस मानसिकता में आने में थोड़ा समय लगेगा।
नमस्कार सर, मैं भी इंदौर से ही हूँ और कल काफी चर्चा हो रही थी कि ई व्हीकल की डेंसिटी इंडिया में बढ़ाई जाए, ई व्हीकल्स की, और मैं कई बार सुन चुका हूं, पर इंदौर में चार्जिंग स्टेशंस के बारे में कुछ काम हो रहा है, थोड़ा सा प्लीज बताएंगे।
मुझे अच्छा है आपने आज ये क्वेश्चन पूछा। मैंने 15 अगस्त को इंदौर का पहला ई चार्जिंग स्टेशन का उद्घाटन किया था। कल 2 और किए हैं, गोकुलदास हॉस्पिटल के सामने और एक स्नेहलतागंज में, और विद इन नेक्स्ट 6 मंथ्स जो हमने 47 ई चार्जिंग स्टेशन का टेंडर दिया है वो कंप्लीट हो जाएगा। तो 47 चार्जिंग स्टेशन मुझे लगता है फर्स्ट फेज में बहुत हैं, तब तक लगातार लोग ई व्हीकल खरीदे।
नमस्कार सर, मैं भी इंदौर से ही हूँ, यहीं पला बड़ा हूँ और यहीं मेरी जॉब है। आपने बहुत अच्छा स्वच्छता का जो मॉडल बताया वो सब लोगों को पता भी चला। आज से 4-5 साल पहले हम ये सोच भी नहीं सकते थे कि हम इतने स्वच्छ शहर बन सकते हैं। और एक समस्या सर अभी भी है, यदि ट्रैफिक सेंस लोगों में जागरूकता जगाई जाए, क्योंकि पहले हम स्वच्छ हो जाएंगे ये भी नहीं सोचा था, तो हम बहुत अच्छा ट्रैफिक मैनेज कर सकते हैं ये भी अभी सोचा नहीं, लेकिन कर सकते हैं। जो ट्रैफिक की स्थिति है शहर में सर, जो जाम हो रहे हैं और जो सिग्नल ब्रेक कर रहे हैं, वहां पर कैमरे लगा करके और प्रॉपरली यदि उन पे भी कार्रवाई की जाए, वार्निंग दी जाए, और जो पालन कर रहे हैं उनको प्राइज दिया जाए, भेंट दिया जाए, तो इससे काफी कुछ सुधार हो सकता है। वही एक समस्या अभी इंदौर में बची, बाकी तो हम सब टॉप पर है इंडिया में।
अच्छा हुआ ये कॉन्फ्रेंस जो है वो 6 तारीख को हो रही है, ये 4 को होती तो मैं दोनों सवाल का जवाब कठिन पड़ते मुझे। जैसे आपने ई का पूछा तो मैंने कल 2 शुरुआत की। आज भास्कर के 2nd पेज पे आप पढ़िएगा, हम इंटीग्रेटेड ट्रैफिक मैनेजमेंट सिस्टम शुरू कर चुके हैं और 14 चौराहों को उससे इंटीग्रेट भी कर दिया है। तो ई चालान जनरेट भी होगा और इस बार कंपलसरीली भरना भी पड़ेगा, क्योंकि उसका जो रिकवरी का मोड है वो कॉरपोरेशन ने अपने पास रखा है, वो ट्रैफिक पुलिस को उसका शेयर जाएगा। इसलिए अब आप तैयार रहिए भरने के लिए।
I think we are already running late. One last question.
सर, आपने बहुत ही अच्छी तरीके से इंदौर के बारे में बताया, और जो दिल्ली में रहने वाले हैं जैसा कि मैं, इट्स एन आई ओपन। हम लोग कुछ भी नहीं कर रहे अभी तक, पर आई होप दैट वी गेट द इंस्पिरेशन। पर एक चीज आप भूल गए, इंदौर में एक और खासियत है, हेरिटेज। हमें जो इंदौर के बारे में पढ़ा वो विकिपीडिया से पता लगा कि अहिल्या बाई और देवी अहिल्या बाई यहीं पे थी, और उनका महल भी इधर ही है। तो ये तो आपने बताया ही नहीं कुछ।
मैं उसके लिए तो क्षमा प्रार्थी हूं, पर मैंने माँ अहिल्या की नगरी में आपका स्वागत जरूर किया था, पर आज का विषय जो था उससे मैं भटक जाता तो फिर बहुत लेकिन मैं आपको निमंत्रण दे रहा हूं, अगर ये कॉन्फ्रेंस 7 तक है और अगर कैट चाहे या ऑर्गेनाइजर्स चाहें तो मैं कल सुबह आप सभी के लिए एक हेरिटेज वॉक अपनी तरफ से ऑर्गेनाइज करा सकता हूं, जिसमें आप इंदौर का जो हेरिटेज है, राजवाड़ा है, गोपाल मंदिर है, या और भी जिन चीजों को हमने रिवाइव करके सुंदर बनाया है। राजवाड़ा हमारा 1984 में जल गया था, तो अब वो वापस अपने मूल स्वरूप में है, और आप चाहें तो वो हेरिटेज वॉक जरूर करें। अहमदाबाद के बाद इंदौर की हेरिटेज वॉक अभी देश भर में पसंद की जा रही है।
थैंक यू सर। दिस वाज द लास्ट क्वेश्चन।
हाँ, लास्ट क्वेश्चन।
यस,
एक और इम्पोर्टेंट संजय चौक से, एक ये जो साइकिलिंग का मुझे ऐसा लगता है कि थोड़ा जैसा अभी एक दिन रखा था नो कार डे करके, इसको थोड़ा सा और नो ऑटोमोबाइल एरिया या इस तरीके से। भोपाल में मैंने न्यू मार्केट को देखा है, इज कम्प्लीटली ऑटोमोबाइल फ्री मार्केट। वहाँ पे सारा ब्लॉक कर दिया है और इतना बड़ा न्यू मार्केट जो है वो पूरी तरीके से ऑटोमोबाइल फ्री किया है। इस तरह यहाँ पर भी कुछ क्लस्टर्स जो है ना, ऑटोमोबाइल फ्री होना बहुत ज़्यादा जरूरी है। और साइकिलिंग की हैबिट जो है धीरे धीरे मेरे हिसाब से जैसे दूसरे देशों में है, यहाँ पे जैसे अन्नपूर्णा रोड बनी थी तो साइकिल के ये लगे थे, लेकिन मैं देख रहा हूँ कि पूरा अन्नपूर्णा रोड पे ना जो दोनों साइड सर्विस रोड है वो तो पूरी तरह कब्जा हो चुका है उसमें, तो वहाँ से साइकिल निकालना एक्चुअली अब बहुत दिक्कत का काम है। इसलिए हम लोग अपनी साइकिलिंग इसी कॉलोनी के अंदर ही रेस्ट्रिक्ट कर पाते हैं, बाहर जाना हमको साइकिल लेके बहुत मुश्किल लग रहा है। तो उस चीज पे थोड़ा जरूरी है, सिटी का जो आगे प्लानिंग हो रोड्स का, उसमें साइकिल ट्रैक होना बहुत जरूरी है।
ठीक बात है आपकी, पर अब क्या है, बहुत सारी चीजें बहुत कंपल्शन से नहीं हो सकती, सब पब्लिक पार्टिसिपेशन से करना पड़ेगा। कुछ कुछ एक आध एरिया आप भी तय करके उसको करवाओ।
With this, I again congratulate him and let us end the session here. And I thank him for such a detailed talk about the case study of Indore. So thank you so much.
Thank you, sir. Now I would request our director Nake Saab to please present a memento to Madam Jain also.
चला स्पेशली ई वेस्ट के लिए, तो मेयर साहब खुद कॉलोनी में बराबर 10 बजे जैसे बताया था उस दिन आ गए थे, और कॉलोनी में खुद इन्होंने सफाई में अपना हाथ बढ़ाया था, और ई वेस्ट कलेक्शन में खास करके उन्होंने प्रयास किए थे। तो ऐसे मेयर इंदौर को है, तो इसके साथ शहर पूरा अच्छे से चलता रहेगा, और हम कंट्रीब्यूट करते रहेंगे जहां जैसे जरूरत। धन्यवाद।
Thanks. Now I request all of you to join us for a tea outside. Thank you. We will meet here again after 25 minutes. Thank you.
हेलो हेलो आ रही है? हेलो ओके।
To chair the session, we are honored to have Dr. Pradeep, former Vice President INAE and former Vice President TCS, former Vice President Academic Professional International Affairs, Indian National Academy of Engineering from the year 2018 to 2020, and former Vice President TCS and Chief Scientist, Process Engineering Innovation Lab, Tata Research Development and Design Center, TRDDC, a division of Tata Consultancy Services, Pune, and alumnus of Indian Institute of Technology, Kanpur, University of California at Berkeley. Dr. Pradeep joined Tata Research Development and Design Center, a division of TCS, in 1984. After serving BRC for 4 years, after his return from US in early 1981. His main areas of research are diverse, but include rare earth mineral flotations, particle science technologies, mineral processing and extractive metallurgy, to name a few. He has more than 200 publications and 21 patents to his credit, and he has he is recipient of several honors and awards, including Kona's Distinguished Service Award, SME Taggart Award, Vasvik Award for outstanding contributions to industrial research. With this brief introduction, sir, I hand over the session to you.
Thank you. Thank you very much. First of all, very warm welcome to all of you to this very important session on laser technologies for emerging engineering challenges. You can hear me at the back? Or you need mic? No, you need mic. Okay, we are all used to mics. Okay, so first of all, good morning and very warm welcome to all of you for this important session on laser technologies for emerging engineering challenges. We have a very eminent speakers this morning, and we are fortunate to have from both industry as well as from defense. And idea is this session is basically dedicated to role of lasers in defense technology. As you know, it's a very important field. Just to remind everybody, I think everybody knows this already, that this whole idea of engineering conclave is to deliberate and come out with some very definite recommendations on behalf of our professional community so that we can go to the next stage, wherever we are at, where we want to go, what should we do to reach there. So with that perspective, let us listen to, it's a very limited time for the speakers as well as for all of you, but please feel free to make your own observations and recommendations, which will make us all go to the next stage. So with those few words, I should also thank, because I am sure I will run out of time in the end, so that I am grateful to organizers for giving me this opportunity to be here and participate in really exciting sessions. Our first speaker is Dr. Dashrath Ram Yadav, former director DRDL Hyderabad. He is background. I will not go. Actually, it should be Dr. Dashrath Ram's this thing here. So I will not go into great detail because all of you have biodatas of all the speakers. But I will just emphasize that Dr. Dashrath Ram has led many important defense programs. Especially, I'm sure all of you have heard about Akash and BrahMos missile programs, and he has led those projects. And more importantly, established state-of-the-art facilities for missile qualification, testing, large-size hypersonic wind tunnel facility, and build infrastructure for integration and testing of BrahMos missile system, which is a success story from India, as all of you know. Amongst obviously, with such a distinguished track record, he is being recognized by various academies, including our own Indian National Academy of Engineering, Aeronautical Society of India, and many others. So with those few words, I hand over to Dr. Dashrath Ram. I've been told that we have 20 minutes for, and then if there is some discussion, and so please, Dr. Dashrath Ram, please.
So, good morning to all of you. I think such a nice introduction, and today my presentation is one. This one is
point for forwarding.
Today my presentation mostly you will find it is blend of based on the requirement how laser has helped us, because if you see the difference, this application of them is plenty actually. If you see the laser, I think if you name any area, what we can say where laser cannot do as such. As far as defense, we use for a lot of sensors, and basically if you take anything related to missile seeker or other sensor like INS or proximity fuses, everywhere it has the application. But I am basically from that airframe and manufacturing area. So I am just trying to go to cover to you okay, what type of difficulty we face to realize the hardware. Although it is very easy to tell the technology and we do the component level, you do the characterization. But once you go to work on the actual hardware, that time you really face that technology on the ground, how it works, and depending upon the shape and size. Yesterday I saw a presentation from RRCAT, so the type of things underwater cutting and all, nobody can imagine how it is things done. But once you cut, then you know what type of difficulties are being faced. So I am basically going to cover in the manufacturing process control, what type of difficulties are there and how laser is helping us as such to overcome those problems. So if you look about the laser technology, I think it is a very widely, everybody knows what is the welding, what is the cutting, and additive manufacturing process. It is a quite advanced, lot of things are coming. Then drilling and I can say machining, assisting something. Surface treatment, also one of the area where major laser is being used. So as on today, suppose if you take laser cutting, more or less a very established process. So many yesterday you might have seen Shahjahan laser, they are presented. Lot of machines are there, and plenty of industry. It is as on today being used. It is very highly matured, and people are using also. As far as laser welding, it has still a lot of inherent problem. Very specific applications sometimes being done. I will just come on that. Laser hardening, another area, is extensively being used actually, and basically sometime even that being used, laser cladding and all, where we are doing some repairing, the other works are there. This a lot of application now is coming like laser milling or laser and finishing, where you have very hard material is there, brittle is there, how to do and all. Of course, this laser direct energy deposition, another area where plenty of work is being done, and we had also developed few of the machine, because earlier it was a more or less prototype, but now first time we are trying to make where whole engine can be printed, and I think some presentation will be there. The person who has made that machine, part of that, I think he will be presenting, and for that, who has given the sanction for money is also here only. So it is R&D project, nearly 8 crore we gave, and it is one of the best machine I think IIT Hyderabad has developed. And it is where you can, full engine, it can be printed. Of course, a lot of technical challenges are there, but we are going to work with that. Only things we don't have any, we can say one stop laser, one laser, multiple function. If I talk laser, people will be very excited and all, but I will tell this application, then it comes which laser, what power, what wavelength, plenty of things are there. So which laser, how to select which application, there are plenty of issues are there. This is just trying to show the gap where variety of laser are there depending upon the application. One laser cannot help everywhere. As far as laser cutting is there, it is highly matured. I think I am not going to cover much, but as yesterday you might have seen, he was telling some 15 or 16 meter of length. Laser is being developed and it is being extensively used. I am aware of that some of the industry there, particularly for metro bridge and all, nearly 30-meter span and all in one go they are cutting and doing. This is we purchased one laser from the German supply laser 4 kilowatt. This basically we have purchased the machine where we are doing that scramjet engine when we are doing the welding, nearly 6 meter of span is there. For that application we have purchased, but we are doing plenty of application where we can do turbo pump assembly and normal delivery system. It is a basic application sort of thing is there. This is the one typical application I wanted to show, because any missile is made, it is we have to make the rocket motor. Of course, standard material is maraging steel, and it is a very good as such. We do the flow forming, we do the welding machining, established stick welding process is there. But there is a requirement where rear section we have to use AISI 4130. It becomes dissimilar material, and most of the people are there from the metallurgy area. They know, because I don't know metallurgical area, but people face plenty of issues. When we were trying to do, that property was getting degraded and it was not coming to acceptable level, because that material requirement is there, because rear servo is getting assembled at that area. So we did some of the experiment, and basically depending upon that, if suppose you do the continuous current TIG welding and pulse TIG welding and laser beam welding, near property we are able to get at least 96% of the material property. And that is the inherent reason why it is there, because heat effective zone is reduced and it is less temperature is there. So this is one of the inherent advantage if you are using the laser you are able to get. This is the temperature and what is that microstructure it is showing, and that heat effective zone, how it is getting affected in TIG welding and how it is being done in the laser welding. Another application we are having, once particularly either propellant and the warhead, once you close the warhead, generally at the end we have to put a cap and nut and bolt, where because it is rubber sealing has to be done. So that reduce the life actually. So there is requirement after putting the cap, you should do the sealing welding sort of things where explosive is inside. So how to do that one? That is one of the major application. We try to do some experiment. IIT Guwahati also work with that, but that requirement is still there. People are having plenty of issue that really it is a safety related issue is there, and how to do that one. But there are a lot of people have done the experiment. They had measured the temperature distribution surrounding how it is there. But we are aware because Israeli and all they are doing that one. But that technology is not available to us, and some work we are trying to do with some of the institutes. But certainly our safety people are not allowing us to do it until it is fully proven. But there are this sort of requirement is there. Just you can see once this is the combustible material is there and it is totally enclosed, at the end we should do the closing with some shift will be there. So this work is still real application is there, but still technological gaps are there. We have to fill it. As for laser hardening, I am not covering because this is a very established process. A lot of places it is being done, but it has its own limitations. This is the one work we got it done from IIT Hyderabad. Basically, when we do the combustion engine, we have to do the thermal coating actually, and when we do the stabilize the zirconia powder with this cladding, we found a lot of good advantage. We are able to get it, but this process already we had established, but we have to take up to production level. This is the one interesting application because when I am actually IIT Hyderabad is a center of excellence for additive manufacturing. I am the chairman for all those projects. I found this is a really very good application when we do the 3D printing of the things, surface finish and all. Now people are coming, laser can be used as a surface fencing application where it is different type of laser, and people are claiming it is a 60% of the surface finish improvement is there. And some of the example they are shown because they have put the proposal, and I thought I will share. Just you can see after 3D printing and surface finish, it is more or less coming is the near the polishing application sort of thing. And concept is something like that. If you see, because how it is surface finish is done, what is sharp things are there, it just the way it is ring sort of that heating is there, the temperature getting distributed with that, and certainly with the type of way it is a top notch is getting reduced, surface finish improved based on that. This is the anyway very major application area, and many people are working, and this is a quite matured one. Of course, some issues are there, particularly quality and how to acceptance criteria, because a major problem is there. Again, acceptance criteria is the forging one, although you are doing with this, but there only a lot of gaps are coming. This is I was talking about the machine. This is with the collaboration of Hyderabad, what it has, that machine has been built up. Our friend, I think, will be talking more about that. But this is a really very good machine where you can nearly 3 meter of height and nearly 1 meter by 1 meter, it can be printed in one go. This is the requirement is there that when you do, this is the one layer of combustion engine is being shown. You can say the inside nearly 1.5 diameter hole is there. It is not a continuous building with the hole, it is keep on building up to that height. Otherwise, if any way means of making those holes is really very difficult. So this is the some parameter, what is standard distance and all those things, and then what is that carrier gases are there, how it is being done. So now it is already established, means installed and commissioned, and trial is going on there. One more application where we are facing problem, basically this is a laser assisted machining where we are trying to do this radome. Radome is a material, it is basically made out of ceramic, and it is a radio, you can say it is a radio transparency is very high, is for RF seeker, it is a head of the missile, this is being used. But the problem is there with this, that sintering, when we do the casting, yield is nearly 50%. When we do the machining, another 50%. And then we do the sintering, another 50%. So hardly 5 or 10% only comes out of that. So that one, I think our people have done some work with the doing that, how to do the laser assisted machining with that. I found it is a really very promising. One work was done by VIT Vellore with the collaboration of DRDL as a experimental setup we try to do. And you can see that two types of radomes are there, where if you see this is silicon nitride is there, other is alumina. Of course, alumina cutting force is less, and compared to that one's laser assisted things, further reduction is there. And if you see the tool life and whatever chipping is being done, it is much better where tool life and other things are there. So being that promising, I think with the Dr. Paul, our people had worked it out. I think we are working very closely with the RR CAT, where we are trying to see, as far as outer machining, we don't have much difficulty, but how to deliver inside, because this is a conical shape is there, agile, where laser delivery have to be done, and before cutting, you have to heat particular that area, and it should go in the synchronized mode. I think some setup already we have done. We have to work further on that area. This problem is still existing. I think a lot of difficulties we are facing to realize this hardware. So with that, I want to conclude there are laser is very good. It has multiple applications, but a lot of difficulties are there as far as that when we try to implement on the actual components. And basically, as sir was telling, future recommendation, what you want to make, actually from the, I think being in DRDO and knowing what type of difficulty we are facing, one is thing is there, technology may be application in different field, but engineers development of lasers and necessary optical system, it is limited. Most of the places, maybe as on today, I can say few private industries are there. Otherwise, DRDO last tech was doing, and RR CAT is doing some work on that. Then indigenous development, basically how to do the laser source and manufacture, and it should be very cost effective. That is another thing is there. If any small person want to start up and all want to do, he cannot afford actually. The laser source should be made very cost effective. Maybe center of excellence can be there where people can go do their experiment. I think RR CAT can help on that. And then research projects on indigenous development, laser technology and automation, how to do the product, that is more important. And this is the work my two colleagues, Dr. John and Mastanaya, has helped me on this. Thank you.
Thank you very much.
Thank you. Okay, so thank you very much, Dr. Dashrath Ram. He has given an overview. I'm sure there are many metallurgists in the thing. You have some questions for Dr. Dashrath Ram? No questions. Okay.
Yeah. I have a question. The previous slide, you were mentioning that the laser is passing through the tube, right?
Actually, laser is the delivery. Cutting tool, it is not passing through cutting tool. It is side by. So this means the first laser should hit it, and immediately that machining has to be done.
Yeah. So instead of passing it through the cutting tool, you can take it as an external way, right? So that can also serve the purpose.
This is RR CAT only have to tell which laser to use. We want to reduce the temperature where you should come in the cutting.
Just thank you.
Yeah. Any other questions? Yeah. You have no. Okay. So let me ask for everybody. I mean, I'm not an expert in the field, but in metallurgy, we are always taught microstructure determines the final properties. And one big challenge which is there for additive manufacturing is to match the microstructure which we get from conventional manufacturing operations. I mean, just like there are all kind of alloys. Now everybody would like to make it additive manufacturing. There are obvious advantages, and it is all around lasers. So you have some challenge through to those
Sir,
who are working?
plenty of. I think you had asked the right question. I am the user. A lot of applications, people say 3D printing and we are investing. I think it is very good technology. But it comes to the ground level and doing the things. Between you and me, it is not more than 1%.
Correct.
Application. People have to really look why that issue is there. Issue is there, we are able to get the shape, maybe size, but how to accept that one? Acceptance is the one criteria. Second thing is there, you are rightly saying that metallurgical, we always try to compare with the forging route. Of course, that is a different issue altogether. But still acceptance in the actual criteria, there is we are ready to accept that one because plenty of issues there post fabrication. The one is the fencing, second is the, you can say, residual stresses and all those things are there. If you see 3D printing, it is a sandwich between, it is like investment costing and if you do what is called forging route or something. Investment costing, you have advantage if you go in the heating and of course it become more economical and try to do. But suppose we are doing 3D printing, again we are telling we want to do the heating because some of the gaps are there, then it is not economical actually. The people, why not go to that? And then another issue is coming, how to do the fencing operation because surface finish and all, if you go to the forging route, naturally machining and a lot of traditional standard procedure is there. So certainly we have to overcome, but one advantage is coming because particularly I have seen and observed a lot of rocket motor, particularly liquid or cryogenic or you can say where you can do the direct printing and their acceptance criteria is like that PPT sort of thing. If you pressurize it and upload 10%, 15% extra margin is there, you can use as it is because let it see what happens. And there it is succeeding. And their good part is that surface finish is not so good requirement because inside again we put the insulator. It has some inherent application, but the designer is still not able to come because yesterday people were telling na design for additive manufacturing. So that that have to come. Maybe academia have to spread more on that and focus. Okay.
Yeah.
For the ceramic machining, it is very important that you have to go a peak intensity of the laser of 10⁻⁷ to 10⁸⁸. So ablation cutting is there only in ceramic. You cannot melt and cut it. Machine it. That is the problem. Only ablation you can do it because all the particles are sintered and heated it. So ablation technique you can use it, and that energy is required 10⁻⁷ to 10⁻⁻10 watt per centimeter square with a nanosecond pulse. Maybe it is work.
You are right.
Thank you.
Let me just ask you another question. You are saying exclusive center of excellence for R&D on laser application in futuristic technologies for defense and aerospace. Of course, ARCI is doing a lot of work in laser.
I am very closely related things. ARC is also mostly R&D sort of things.
Okay.
Of course, they have few machines installed. It is imported one.
So, based on your experience, you can define what kind of facilities, what kind of expertise should be there. Because I remember at one time I was interested in friction stir welding. So I saw in France, they have created a center where all kind of welding machines are there. And you go with your problem and test it out. And these are like scaled up versions of things so that you can look at whatever. So something you can give some thought.
No, this is because now what I am trying to tell this now DRDO is funding Center of Excellence in Additive Manufacturing. You are right. Issue is there. Initial funding requirements are very high. So nearly we are giving 70-80 crore because until machine is there, what experiment you can do, or anybody want to do, he cannot just component make and just go it. It is very costly sort of thing. That they have put up the proposal where we are aiming that now this is the one process that but 3D printing where people are telling a lot of voids are there and a lot of defects. Other thing is there that wire fed. Where people are telling quality is much better. Now people are talking about the hybrid machining. Like it is, although it is doing the that direct energy melting sort of thing. Beside that, it is keep on machining also. As it is keep on building, that there is no need of after whole thing building. It is partially you do nearly maybe 100 mm. You do the machining. Or maybe some technology is coming where you have to heat and pressurize it and try to see how to avoid. One thing is the stresses, what is the avoid. So that's why IIT Hyderabad has proposed, I think it is called hybrid machine where 4 operations can be done beside the melting. So people are coming with the different solution based on the industrial requirement. As an industry, we should encourage and of course fund it. That way. And I think RR CAT is that way is better place to do it.
Okay. Thank you very much. Yeah. So thanks a lot, Dr. Dashath Ram, for a very exciting introduction.
Thank you.
Oh.
On behalf of organizers, thank you, sir.
Okay, so it's my privilege to invite our next speaker, Mr. Anthony Paul from L&T Defense, and he will give us an overview of role of lasers in defense technology. And just by way of very brief background, as you know, L&T is working very closely in defense applications. He has established the Additive Manufacturing Center of Excellence in L&T's defense related thing, Precision Manufacturing and Systems Complex in Coimbatore. And he is currently heading the Advanced Manufacturing Technologies Center, spearheading the development and utilization of cutting edge technologies. And he has background in robotic manufacturing of near net shaped composite components with directional short fiber reinforcement. Basically mechanical engineering background, working on the cutting edge technologies for defense. Thank you. Over to you.
Thank you, Dr. Pradeep, for the introduction. Ladies and gentlemen, a very good morning to all of you. It's my pleasure to be part of this engineers conclave amongst such eminent speakers and subject matter experts. So my talk today is on lasers in aerospace and defense, some of the research that is being done globally, some of the breakthroughs, and what are the challenges that we face. So we will go through that, and finally we will come to some recommendations to the various stakeholders who are there, including all of you, and on how to take India forward in this particular domain. Before we start, I would like to just give a background on Larsen & Toubro Limited. We are India's largest engineering, manufacturing, and technology company. We are about a $23 billion business in various sectors and verticals. One of that sector is defense, and here we address the requirements of the Indian Armed Forces, both Army, Navy, Air Force, etc. And we work closely with the various defense entities, including DRDO. So the capabilities at L&T span end-to-end solutions in order to fulfill the requirements as I showcased in the previous slide. So we also look at precision manufacturing, and that's one domain where laser is generally utilized. Okay, and in this section, we have a lot of capabilities in-house, and we have recently added additive manufacturing, specifically metal additive manufacturing, both powder bed fusion and wire deposition, that is direct energy deposition. Now, as most of you know, since you are familiar with lasers, there are a variety of lasers that are available, different types based on the gain medium, the resonators, etc., and also based on the modes of operation. And as Dr. Dashath mentioned, the selection of laser for the right application based on each inherent capability is critical. Not every laser will work in every end use. And this is just a summary of the various wavelengths and powers that can be achieved, quickly going through. So there are many applications for laser. It encompasses the entire, human use, right from commercial, scientific, and medical application. I'm going to be touching on industrial applications, specifically on defense and aerospace manufacturing, and also the tactical use as is used in aerospace and defense. So as Dr. Dasrathan had covered before, laser is used in a variety of manufacturing processes, right from welding, drilling, machining, heat treatment, including hardening, ablation, cleaning, cladding, additive manufacturing, marking, scanning, and also in an experimental way for forming. So why are lasers used? One is you are able to focus the energy in a very precise location, and that allows you to control the kind of the damage or inherent defects that might happen. So if I have to do drilling of very fine holes in a very thin structure, since there is no mechanical effect that is happening, I can actually do that without having to go through a drill bit puncturing through the sheet metal. In case of additive manufacturing, we're able to process materials which are reactive in nature and having high melt temperatures. We're also able to create to some extent in how we can optimize the control strategy for how the laser has been impacting on the end target. That can also be done.
Thank you, sir.
Hi, Doctor.
And I think this I want to know, will you be able to throw some light on what is the L&T defense plan in the short term, in 3 to 5 years time, to work in this area?
Yeah, so unfortunately, I cannot disclose what we are doing presently or who we are partnering with. But our understanding is that there is a roadmap that has been set by the armed forces for development of data weapons. There is a definite looking at the fundamental elements of that technology, not just the complete design, but the laser sources, the optics, the assemblies, etc. So we are happy to work with research entities and with DRDO on getting those capabilities put together. So the end effect is addressing what the army needs. Okay? So we are able to step up to the challenge, but we cannot do it alone. We'll need to certainly work with various other players in the industry and also with research entities to address that. But as I mentioned in some of the slide before, high energy lasers are what is the current interest. We're not looking at the low and medium level. So high energy lasers is where we need to work at. And we do have some challenges in having this technology brought to India. So we have to work on developing these capabilities locally.
Excuse me. Yeah. How you qualify your laser-based system? Is there any test setup or standards which you are following it?
I may not be able to give you the full spectrum of qualification, but typically at individual level, there are optical qualifications which are required for the lens and the mirrors, etc. Then at an assembly level, there is a whole sequence in which you need to assemble all these components together, so that as an assembly it functions without any deviation in the beam that you're going out. So there are procedures available. There are also some standards available, but to a less extent for laser data weapon. But there are procedures defined based on the end quality that is required. So these are implemented in the various manufacturing and assembly sequences. So it could be done with a limited factory level testing, and it can also be done for functional field level testing. Both can be done. So primarily looking at the lethality, the spot size, the distribution of the power in a particular spot size, whether it's a flat top or a Gaussian distribution. So those kind of evaluations are done to look at the final quality that you get.
Yeah, there's one question. Yeah, I just wanted to ask you.
Sorry.
Sorry. The Geneva Convention says that you cannot use weapons for blinding. So how does a dazzler get in the way of doing that?
So as with any military, and I'm not talking for the Indian Armed Forces because most of and a lot of development has been happening on that front.
One more? Okay, last one. Yeah, of course, it has created a lot of stress. So over lunch, we can discuss some of the secret things which we cannot talk publicly.
I still cannot talk that publicly, sir.
Sir, till date, up to how much maximum wattage level laser we have manufactured in India?
I'm not privy to what is ongoing research. See, I think we have not reached the kind of power that US is talking about, which is 100 kilowatts and above. Because that is something that is presently being done by the US DoD, etc. So globally, I think, to the best of my understanding, we are in the 100 to 300 kilowatt range systems. Right? But it could exceed that once there are developments. There could be research happening on higher power systems, but they have not been deployed in the defense aspect of it. Or at least it's not shared publicly in the sector.
Okay, so let us give a big round.
Thank you.
Thank you very much, and we can always connect with him over lunch. Now our next speaker, it is,
Behalf of organizers. Thank you.
So it's my pleasure to invite our next eminent speaker, Professor Hari Babu Srivastava from IIT Delhi. He is the, it is wrong, sorry. He is the former director of LESTEC DRDO, Director General Technology Management in DRDO, and at present he is Professor of Practice. Those of you who don't know, I mean, people from industry now can become academic professors at IIT Delhi, and also at the same time visiting Professor of Practice at IIT Kanpur and IIT Roorkee. And he is, of course, also associated with Vivekananda International Foundation, New Delhi. Some of you may know, it's a think tank. Significant contributions in various defense-related technologies. It's our pleasure to request Professor Hari Babu Srivastava to deliver the talk on lasers in defense.
So thank you, Chairman sir, and also the previous speaker. He has made my life very simple. A lot of things which I wanted to say, you have already said. So all of you know, and this has been told again and again, multiple advantages that we have. But let me tell some drawbacks also. They are very bulky systems. Still a challenge to employ on at least the airborne vehicles and also on ground and naval vehicles. They're very power hungry, and most of the power gets converted to heat, and therefore you require another system which will cool them. So that is the problem, and laser beam being the optical beam, it gets affected by the atmosphere that we have. So these are the drawbacks. Positives everybody has told, so let me just skip that part. And this also was covered by a previous speaker, but I will just say 3 types of lasers in military systems. One is the battlefield lasers, you can call laser rangefinders, designators for guiding the projectiles, seekers, all those kind of things. And also the LIDARs, which is equivalent to radar in the microwave domain, for sensing various kind of things, because apparently the nuclear war may not happen, but what may happen tomorrow is the chemical and biological warfare. So we need to be prepared for getting the information from far off distances, standoff distances. So we need to have LIDARs working in various capacities, working in various wavelength regions for detecting the bio warfare agents, chemical warfare agents, and also the explosives. So this is the kind of those applications. Another one is moderate power, where somebody was mentioning here that can be used as anti-personnel. We may not be able to use it today, but should the requirement come, we should be ready for those kind of things. And of course, high power, which is directed energy systems, that is the major thrust these days. And they can be anti-material, structural damage to flying objects, vulnerable points on fuel tanks, optics, everything was covered. And today, of course, we are talking of ranges which is something like up to 20 kilometers. We are not able to say that we can damage a target at 100 kilometer, 200 kilometer. Today, we cannot do that. Therefore, missiles are going to remain. You can be sure for that. And various types of lasers, solid state lasers, gas lasers, electric lasers, fiber lasers, and all that are being talked about. So, from the conflicts that we have seen recently, there are one or two lessons that we need to learn. One is that we need to have weapons that cannot be intercepted. And laser provides that capability, that laser weapon cannot be intercepted. Because speed of light and nothing moves more than that particular speed. And also stealth. And this part was also told by the previous speaker, low cost of engagement. Each engagement costs only $1 or maybe a few dollars. But anyway, missiles, bombs, they're all going to stay because we cannot go far. So HPL is a high power laser, or high energy laser is a very suitable candidate for that kind of application. And of course, these two things again I told, readiness to chem bio warfare, sensing. And this is very, very important. Apparently, nobody in our country seems to be working today. If I am wrong, then it is good. But apparently, we are not working in the underwater communication. So that's a huge challenge for underwater communication. So why we need high powers? And if you look at this chart, from a 1 watt to 1 megawatt, what kind of targets can be defeated? So if you look at today, people are talking of 300 kilowatt, Americans are talking of 300 kilowatt. We can defeat the artillery shell at longer distances. The Israelis conducted a test maybe a few years back where the same artillery shell they defeated at short distance using a 100 kilowatt laser. So we need to have the lasers going up to a megawatt and maybe beyond to take on the threats which are like aircraft, for example, or maybe the ballistic missile at the time of taking off. Those kind of things, we need multiple megawatt kind of lasers. Now, before we get into more of laser, and I will be a little more technical so that some of the questions will be answered, we need to have for a laser weapon, we need to have a laser source, and which mostly as of today people are talking of fiber laser. This fiber laser can be a monolithic source. That monolithic source will not go far. It will not go beyond maybe 5 kilowatt because the beam quality degrades after maybe 2 to 3 kilowatt. Beam quality is not as good as it is required for the weapon system. But we need hundreds of kilowatts. So we need to have the lasers operating at low powers, 1 kilowatt or maybe 2 kilowatt with very, very narrow line width, and all those lasers are combined together, and there are various technologies to combine those lasers together. And that particular beam, through the optics, it is put on the target. Now what I am showing here is not that scheme which I am saying. There are multiple ways of combining those beams. One of the ways is shown here, which is a geometrical combining. And then we need to have the EO sensors for tracking, for detecting the target and tracking the target. If we can track the target well, we can destroy the target immediately. So that is the whole system. So let me go a little more detailed. The laser sources mostly at 1 micron, and somebody was asking which is the active media. The active media, today we are talking about the YB, yttrium. And as I said earlier, single mode lasers, hundreds of kilowatt is required if you really want to defeat the targets. but industry can do with 10 kilowatt and more in multi-mode lasers. So industry does not require, but the defense will require. And these technologies are getting matured now. The most mature is, of course, the fiber laser technology, where the demonstration of 300 kilowatt has happened. The liquid laser also the Americans are pursuing, which also 300 kilowatt they have demonstrated. And of course, finally, the diode pumped alkali lasers. This laser is expected to go to multi-megawatt kind of things. I'll talk a little more detail when we come to that particular thing. And there are several critical components and technologies you also got out. Active and passive fibers and fiber components, pump combiners, FBGs, cladding mode distributors, so many things. Fiber coupled laser diodes we are not making in the country. We are at a very, very low scale, 30 watt. We need hundreds of watt. High power, high laser power damage threshold coatings. We have got some initial successes. I will talk about it. And low temperature coefficient optical materials. Again, most of the optical material is imported. So we need this kind of material to be built in the country. Just to give you a little flavor, because there are people from different backgrounds, this is the kind of laser that you actually have inside the engine, laser engine. You have the active fiber here, and you pump from both sides or one side depending on what kind of power you want to get. These are the laser diodes, so either you pump from one side or both sides, and these FPGs form the FPGs and the active fiber. They form the cavity, and in that cavity the laser gets generated. Now, as I was mentioning earlier, 2 kilowatt we can get a good quality laser, M square, 1.2, 1.1, that kind of thing we can get, the beam quality that you were talking of. But as you go to 5 kilowatt, the beam quality degrades. So probably 1.6, 1.5, that kind of thing you can obtain. Going beyond that is actually defense does not require that kind of laser. So we will not be able to use that kind of laser at all. So you need narrow linewidth lasers to be made, maybe in MOPA configuration, and that particular one can go up to 2 kilowatt plus has been reported. Today we stand at about 1 kilowatt. Indigenous capability is 2 to 3 kilowatt single mode, this kind of laser. It is available. You can buy it from SFO Technologies. The technology is developed together with DRDO and SFO. We have done that. And SLTL is also that Sagadam laser technologies. They are making this laser by importing the engine. So the main core comes from somewhere and then they make the laser around that. So two companies are at least giving you that kind of laser available in the country. So how do we scale up the power? We made 1 kilowatt or 1 kilowatt plus narrow linewidth laser. How do we scale up? And there are 5 main technologies that are available. One, of course, is the tandem pumping. This is championed by IPG in Germany. So what they do is they generate another laser at 1018 nanometer, from 976 to 1018 and from 1018 to 1070. So that way they are able to reduce the heating effect. Thermal load is less. And by doing this, they have been able to get 10 kilowatt with good beam quality, which is something like 1.8, M square 1.8. They also claim that they can go to 20 kilowatt if somebody funds them. So I don't know, nobody has funded them so far, for what is the reason. So this is one good candidate to go up to 10 kilowatt at least, if not 20. The second is tapered fiber bundling. You put all the fibers where you are generating kilowatt plus kind of things and you put them into a fiber. But this gives a very, very bad beam quality, which is of the order of under root n, n being the number of beams that you put. So this again becomes useful for the industry, but not for the defense. Next is the geometric beam combining, where you have multiple beams and each beam you are controlling so that it falls onto the same spot onto the target. There is a lot of control system involved there, but this is possible to do, and multiple people, including our own country, also has done it. But again, the beam quality at the target, beam quality at the source is good, but the beam quality at the target degrades. So therefore, you are not able to actually put the kind of energy density that you want to put onto the target. So what will happen if the energy density is not good? It will take more time to destroy. Next is the spectral beam combination. Here what we do is we generate lasers at multiple wavelengths, which are very, very closely spaced. between 1030 and 1070, because that is the bandwidth of the YB, ytterbium. And those lasers, you do the reverse of what happens in the prism. You put in such a way that all these are, they become collinear. So maybe I'll explain a little later. I have another slide for that. And lastly, the coherent beam combination. So coherent beam combination is phase manipulation. We manipulate the phase of multiple beams so that they combine together and they propagate in the atmosphere. So here, the beam quality will be best here, the second best here, and of course these are all the not so good kind of lasers. I mentioned this already, so I will skip this. This also maybe we can skip. Only thing is output powers of hundreds of kilowatt are possible, and even in our country, Savanna is fabricating. But if you look at the beam quality, I'm square 50 and more. So this is not for defense. Okay. Now geometric combination. Multiple beams, and each beam is through a mirror, and each mirror is being controlled by sensing what is happening, and then you are putting this. Multiple people did the experiments, 30 kilowatt, 50 kilowatt, 60 kilowatt, and all. We are also doing 50 kilowatt. That kind of 6 into 10, assuming that there will be some power loss in this combination, so about 50 kilowatt. This kind of experiments we are doing, and the country is almost at par with what is happening outside. But this will not give us the result that we want. This will give us the result at short distances, not at very long distances. So what we want is probably this kind of thing which has been demonstrated by others. The Americans, what they are talking of 300 kilowatt weapon today, HELSI, is based on this technology. So what happens in this is you generate the narrow line width lasers, and these narrow line width lasers, when I say, they are of the order of gigahertz, and they are put through, this laser is put through a fiber array, and this is a integrated optical element, because each beam has to fall onto a grating at a particular angle. If it doesn't fall at that angle, the accuracy, the efficiency will be less. So this is a very special component that needs to be fabricated using the integrated optics technologies, and then this will go into a transform mirror, and transform mirrors will get reflected, go to the grating. Now we don't have this transform mirror today in our country. We don't make it. We don't make the diffraction grating in our country today. But of course we have done some work, and I will let you know what that work is. But there are two ways of increasing the power. If I have to go to 300 kilowatt kind of thing or 100 kilowatt kind of thing, one is I can have hundreds or 300 laser sources. That is one way of doing. Another way of doing is increasing the power of each of them. So today our country is around 1 kilowatt kind of narrow line width laser. The Americans seem to be having a 2.5 kilowatt. Of course, it is not there in the published literature. It is in one-to-one conversation. So this is one-to-one conversation, I think, is important. So this is where the research activity 3.1. Okay, so this is where we need to invest more time, more energy, more funds to get that done. So one is, as I said, the critical technology is the narrow line width laser. 3.1 is telling, so maybe that is the status. We are at 1 kilowatt level. Beam combining element diffraction grating, which requires high laser damage threshold, and also the angles at which the diffraction angles that are given to the grating. So global status is about 2.8 megawatt per centimeter square. That is the damage threshold people are talking in US. Whereas in our country, we were so far working on very, very low powers, primarily for imaging purpose. But now at IIT Delhi, we have worked out 100 kilowatt, sorry, we require hundreds of kilowatt. We have worked on now 100 kilowatt per centimeter square kind of damage threshold that has been achieved in the IIT Delhi. Again, I have talked about this micro-lensed fiber caps and all, beam combining optical element. So these we need to do. The 300 kilowatt is not the end. The Lockheed Martin has got a contract for making now 500 kilowatt. So this is where the world is going. We are today at 10 kilowatt development level. So we need to actually put a lot of team, lot of money particular technology. The coherent beam combination, as I said, we manipulate the phases, and because the phases are manipulated, we are able to bring a constructive interference, and therefore the power increases. So excellent beam quality. Again, narrow line with lasers are required, but these lasers are at same wavelength. Here the wavelengths are not changing, because if we change the wavelength, we cannot bring the coherence. So same wavelength, multiple lasers, and again same issues, precise control of fiber amplifiers and all those kind of things. So again, a lot of electronics and all that. And same point here again, because we need narrow line width. So again, our technology is today limited to 1 kilowatt. We need to scale it up further. And we will have DAE, which will again handle the same kind of power. So again, high power threshold coatings. And the status seems to be about 50 kilowatt in this particular technology. Maybe this is about 6 months old information. If something else has happened in 6 months, I don't know. So about 50 kilowatt has been reported. But this has the potential to go up to same 300, 500 kilowatt. The advantage is that we can steer the beam also. So maybe even if jumble what we have other place, that can be removed. So it becomes a smaller, lower footprint system. I am sure the question must be coming in mind, why we need such technologies? Why single beam cannot work? So one is, as I mentioned earlier, single beam of 100 kilowatt. If we get the M square, the beam quality will be too poor. But assuming you get the good quality, I am just making the comparison here. So if you have a good quality 100 kilowatt beam, what will happen? Under certain conditions that are given here, the kind of power density that I can still put at 0.5 kilometer altitude, and I think it is 5 kilometer range, only 86 watt per centimeter square. I am sending 100 kilowatt, but what I am getting is only 86 or 76 kind of thing. But since this also I will not get, because my M square is not good. So I have to make M square good, and that is why we need to go to next technology, which is incoherent beam combination, or SBC in this particular case. So if we take either 300 millimeter aperture or 700 millimeter apertures, we can again go back to the same kind of accuracies which I would have got from single beam of 100 kilowatt. So by using this particular technology, I will get the kind of damage capability which I will get by single beam of 100 kilowatt. But I am still looking for more, more. So I am going to the next technology, which is coherent beam combining. And by doing that, if you look at, we can actually deposit multiple times. From 76, 79, we can go to 560 kind of watt per centimeter square. This is another model proposed by IIT Madras and Indian Institute of Science. We were working very closely with these two particular agencies. They say if you combine the SBC and CBC together, the results may be even better. But of course, we have not experimented. This is at the theory level. So what, in my opinion, the focused area have to be are the active fiber, the passive fiber components for the levels that we are talking of. The low levels, hundreds of watt and maybe up to a kilowatt and all, they are available in the country. But we are talking of the much higher levels. Micro lenses, high power fiber arrays, and fiber coupled laser diodes. Today, this is wrong information, today people are talking of 400 watt. And single emitter diodes of 60 watt are being talked about. Our country's capability is today 9 watt. So we need to actually scale up much higher. Again, optical component he brought out, the coatings brought out, DOEs, MLD gratings, all this. So we work at IIT Delhi, we are working on these 4 items. One is the freeform and large size optics, spheric optics, to make the system smaller. Robust laser beam engineering and beam shaping, and of course DOEs that we talked about. CGCRI we funded for fiber and fiber components. They did a good job, and up to a kilowatt level, these components are now available from them. And this one, up to 30 watt SFO from the 9 watt emitters that SSPL gave to them. But I think we need to take this 9 watt to 60 watt and this 30 watt to maybe 400 watt. So I think time is going out. I will not talk much about it. The next is liquid laser. Again here 300 kilowatt has been demonstrated, and the prediction is that this will also go to a megawatt kind of laser. Reason is the heat is actually flowing. There is a flowing liquid which is being lased. So the hot liquid flows out, and that thermal management can happen elsewhere. So this can go up to a megawatt kind of thing. This is being talked about. And the final one is the diode pumped alkali laser, where it's in gas form. So here the heating effect is even less, and therefore you can go to multi-megawatt level. Today, of course, 120 kilowatt is in making for space debris removal. This application also we are not talking in our country. I think we need to start talking. So time is there, few more minutes or no? Yeah, okay. Next I talked about the chemical biological warfare agents. So there are multiple agents both in chemical and biological which are listed here. The problem is that with the wind they disperse and they will settle on ground, and you cannot go there, because if you go there you will yourself catch those things. So we need to find out what is happening in the battlefield from a distance, standoff distance. Of course, people talk that COVID-19 was part of it, but okay, let us not get into that debate. So fortunately, the CW agents, the chemical warfare agents, they have signatures in the IR domain. And if you can find out which particular frequency is being or wavelength is being absorbed in the atmosphere, we can actually correctly predict that this is the agent. And the time of flight will tell what is the distance, and the intensity of the absorption, or the absorption peak will tell you what is the concentration. So all three things can be worked out, and various kind of lasers will be required, 3 to 3.5 in this range here, and maybe 6 to 14. Now 6 to 14 is a CO2 kind of laser. It's a huge system, so it really doesn't work out. You will require a vehicle for it to move into the field, so probably it doesn't work out. But here this 3 to 3.45 is very specific. Smaller systems can be used, and by using this you can actually up to 2 kilometers we ourselves made, and maybe it can further be increased by doing little more signal processing. Likewise, the biological warfare agents, all of them give the fluorescence because of the amino acids that they have, and these, if you shine that with 266 nanometer, and there could be multiple wavelengths, they will give you fluorescence at 350 nanometer or 440 here. But the problem here is that they are broad. This is not a very narrow fluorescence, a very broad kind of thing, and all these wavelengths also interfere with the atmosphere. So the accuracy of prediction as of today is not very high. We can still do that kind of thing up to maybe a kilometer with maybe 50%, 60% kind of probability of detection. The last one, narcotic agent. This is a huge problem as far as the internal conflict is concerned, because lots of them are funded by this narcotic activity. So you have various types of items and you have various kind of test kits. But let me move here. The conventional techniques are these, which are based on color or based on sniffing. The individual sniffs it and tells that this is ganja or this is hashish. But the spectroscopy also can give you result, and which result actually scientifically can be valid. But again, the problem is that they are all giving the fluorescence, and with the fluorescence we have that 50%, 60% kind of probability. So there is another technology that people are now talking about, is the synchronous fluorescence spectroscopy, which is 3-dimensional, and this is promising to be giving up to 90%, 85 to 90% accuracies. But again, in our country we are not working, so I think somebody needs to take up that activity. And lastly, the underwater communication. Blue beam, the requirement is peak power of hundreds of kilowatt pulsed laser here. Probably nobody seems to be working here, because what we want to do is, from the satellite we want to detect the submarine and we want to communicate with the submarine. So satellite will not naturally send the this thing. It has to penetrate firstly the surface of water, and surface of water will act like mirror. But it has to penetrate some part, at least will go down, then it has to go to the submarine, submarine has to again communicate back. So you look at the kind of losses that will happen, and therefore we will require hundreds of kilowatt peak power. So probably this also needs to be taken up at looking at the scene that China and Pakistan and all these players are creating at our side. Now, this is the last one. As I said earlier, the lasers are big, huge systems, power hungry. So probably military is not going to take them as we desire that they should take one laser, one application. They may not take it because logistics probably will restrict that. So we may have to start thinking, the laser community has to start thinking how we can provide multiple functionalities by the same equipment. So maybe, just as an example, the the weapon, the directed energy weapon also works as a designator. Probably we can think about those kind of things. So like that, we need to probably look at the scenarios and work out the system configuration where it will give more advantage to the military rather than saying that you wanted a weapon, I have given you a weapon. That's all. Thank you so much.
Thank you. So it was a very informative presentation by Professor Srivastava, and he is already working on it. Some progress we have made. You have made many suggestions. I suppose we will capture somewhere, right? Or these presentations are available to organizers, right? Yes, sir. Yeah. Okay. So thank you very much, Professor. Questions for Professor Srivastava? Yeah.
Yes.
So the initial couple of slides said there is limited research in underwater communication. So what are those challenges which is hindering this research?
So I just now said, no, one is that when you communicate, first surface is the water, and water acts like a mirror. So most of the energy will get reflected back. Some energy will get inside. But that energy has to go to the submarine. Submarine has to pick up that and then again do whatever it has to do and then send back. So again the reverse way the losses will happen. So therefore you require a good amount of signal processing, good amount of optical system which can actually receive that whatever signal that comes and then transmit it back.
And the challenges regarding water to water communication?
Water to water, actually which wavelength you choose. That is one issue because water doesn't allow many wavelengths to pass through. It appears that at the coastal water around India, 532 nanometer is good enough. But if you get into the high seas, 532 is not will not get through. Probably something like 450 nanometer works. That is the published research.
Thank you. Thank you.
Liquid laser, US has demonstrated 300 kilowatt this year. We are in the 1 to 10 kilowatt domain.
Sir, this water communication that you were talking about, there were quite a lot of signal losses due to water's reflection and everything. So can we include IoT, that is sensors in it, so that we can get a index that what its angle should be to fall over the water surface and how much of the light could enter inside the water for it to communicate in a better way?
So you are right. Actually, there is term called IOMT,
yes,
Internet of Military Things.
Yes, sir.
So this is already being worked on.
Okay, sir. So also, I have one other doubt.
Yeah.
That is, can that laser be used for generating nuclear energy? For example, can we focus laser on some nuclear fuels for it to generate a higher amount of energy?
Maybe RRCAT can give better answer, but I read earlier, I think some time back, fusion experiments have been conducted using the laser. Correct or wrong? I don't know. Yeah. Fusion experiments have been conducted using laser. But then this trade-off, how much energy you put for making the fusion happen,
yes,
and how much energy you get back, that I think RRCAT will give you a better answer.
Yes, sir. Thank you, sir.
Thank you. I think you wanted.
Yeah, in this alkali lasers, it's a gas laser, and even if you do pressure broadening, Doppler broadening, it will be still in gigahertz. And pumping with the diode laser is a nightmare because you have nanometers of line width. So how is it kind of a competitive technology, at least for us? Because
no, I also don't know because we have not started working.
Okay.
I just flagged it here because people are now talking of that laser to go to multi-megawatt.
Yeah, because so the only way you can keep it efficient is do diode pumping. And then you need to build this technology for extra narrow line with diode lasers also.
So I agree because cesium is being touted as cesium and rubidium.
Yeah.
Both require very, very narrow line width lasers.
Yeah. Even if you put to megabars or kilobars, which is possible, I think 10 gigahertz,
I
20 gigahertz,
I agree.
not more than that.
I agree. But people have demonstrated in US. So that means there is a possibility we still need to work on. Our country is not working yet.
So you have talked about spectrally combination to build the high power lasers. I wanted to know what is the limitation of combining these spectral wavelengths. Means, is there a wavelength limitation or the number limitation? So where we can go if we start, for example, with 2 or 3 kilowatt? What kind of power can be built up?
So one is the YB bandwidth is between 1030 and 1070. So in between those 40 nanometer, you have to build the lasers.
And what should be the gap?
What should be the gap? Now, supposing you take 1 nanometer as gap, then you can build only 40. You take 0.5 nanometer, you can build only 80. So there is a combination of the numbers that you can build and the power that you can give to each laser. And based on that, as I said, 300 kilowatt, they have not discussed how many lasers they have used. But even if you take 3 kilowatt as the laser, the individual laser, this is still 100 numbers they have built, or maybe more than that because there will be some power loss also. And now they are going to 500 kilowatt, means they can build so many, maybe 200.
Thank you. Thank you very much.
Actually, sir, we are talking about more than 100 kilowatt of output power from fiber lasers, but that will require at least pumping of 200 kilowatt nearby, or more than that. So, but there is no strategy for developing diode lasers in the country. So how that will take?
No, I flagged it. No?
Yes, sir.
We have only today the country's capability is 9 watt.
9 watt.
Single emitter, and those single emitters combined together, SFO has produced a 30 watt laser diode component. This 9 watt has been scaled up to 60 watt by this. We are still at 9 watt, so we need to work on that technology, and then of course those 60 watt emitters putting together and still maintaining the intensity that we require, the laser beam intensity that we require. That's a technology we need to still work on.
So that's we need to emphasize on development of diode lasers in the country. I think it's
if we really want to excel in lasers, I think we need at least 1,000 crore investment. At least 1,000 crore. Who will give that kind of money? We'll still find out.
Thank you. Anybody? Okay.
That is the last question.
I can hear you. What sort of laser used for? Narcotics. So that is UV, ultraviolet.
Okay, so I think that brings us end for this presentation. I'm sure Professor will be available on lunch and you can discuss with him further. Thank you very much.
Thank you, sir.
So that brings us to next speaker, Dr. Lalit Kumar. And
Dr. Lalit Kumar is Managing Director of Laser Science Services Private Limited, and he has background in chemistry, but he took up the challenge of creating this company, and he founded this Laser Services India and established this firm as laser-based services industry in India. And he has published many papers in national and international journals. But most important is that now we have a company which provides services around lasers. So
Forward reverse.
we'll hear Dr. Lalit Kumar.
This one.
Thank you.
Reverse. This is pointer.
So it's my pleasure to be here for Engineers Conclave. In fact, this is first time I have ever been to this conclave, and thank you for the organizers. Particularly, I would like to thank Dr. Nakhe, who talked to me a few days back and invited me to give a small talk here. And thank you, Mr. Chair, for giving an introduction. So I will not be talking about the technology because I think all the three speakers today have dealt a lot on the defense side and the use of lasers into defense. My company is a laser supplier basically. So we have been supplying lasers in India when probably lasers were not known in India. So it's almost 4 decades. After my PhD from IIT Bombay, I started working in this field and supplying lasers to different research institutes. Of course, those days only a couple of research institutes were known to be working in the lasers, and BRC was one of them, and another one was probably Tata Institute of Fundamental Research. And I think little work was being done those days in IIT Kanpur. So beyond that, everything I have seen growing. So that is how I started my journey through these lasers, and from scientific lasers, of course, industries and military lasers and defense were not known those days. So we have been supplying lasers to all the places, and I will give you a little introduction before I go to this talk, because the talk is more like it's a commercial overview what is happening in photonics and laser market in globally as well as in India. I think that will be very important to know, particularly for the organizers of this conclave, because then they can take the message what do they really want to do in this field further. So, of course, I'm sorry, Dr. Dasaratham, that I don't have a presentation on the system which we have built for you, but we are the people who built that system which Dr. Dasaratham has talked about, and this is one of the largest build volume system which we have developed in India, and I think one of the very first in Asia as well. So fortunately, it is working now very good. It was a very big challenge for me, and I was very reluctant to take that project. But my team really convinced me to take that project, and we have successfully delivered it and installed in IIT Hyderabad. So similarly, we have been doing few projects with the defense, mainly on the DEW. So we are the laser suppliers, and we have been supplying lasers up to 2 kilowatt power range single mode for DEW applications. And last year we completed quite a big project with BEL for supplying these large number of lasers, which have been already, I think some of them have been deployed also and demonstrated also successfully. So our role has been to, of course, we source the lasers from foreign companies, and then we have done the mill qualification of that in India. So that has been a major challenge for us, that lasers we have seen working only into the air-conditioned atmospheres, the temperature controlled labs, environmentally controlled, and now we have made this lasers working in the very harsh environment, and we have done that qualification test on our side and then delivered it to BEL. So photonics, I will talk about global perspective and its growing market segments in India. So photonics, you all know what is photonics, but it's just a one-line definition that generating, controlling, and detecting photons, which are particles of light. So lasers have come, of course, the photonics was known much before the lasers, and lasers have come into play only for last 63 years. In 1960, there was the first laser which was demonstrated, and after that, the photonics field has become very prominent all over the globe. So photonics and lasers, of course, they are inseparable because lasers is light and photonics also light, so lasers is playing a very important role. I'll go directly to the market size. So global perspective, if you see that market size of photonics globally is almost $1 trillion, and this is a huge number if you think the size of the photonics. And that is what message I want to give to this audience is that what is the available markets globally and in India, so that you can take a message from there. The key sectors, of course, telecommunications, healthcare, manufacturing, and the driving countries for this growth is China, Japan, South Korea, and now in India. So most of the activities are centered around Asian countries. So these are some of the major segments of the photonics. Optical communication, which is of course very popular all over the world now. The tons of lasers are used into this, and the fiber optics and the cables. And this market is supposed to be 482 billion by 2027. And then the consumer electronics is another market which is consuming a large number of photonic components, including lasers. Healthcare is another big segment, almost $100 billion. Industrial, which is the manufacturing, automation, process, so all this welding, cutting, marking, surface treatment, and all this is covered into that. And that is about $90 billion globally. Defense and security, this is a big market globally, and now in India, particularly after our government has announced Make in India and Atmanirbhar, a lot of activities are happening in defense and aerospace sector and the security. So this market is almost like $70 billion globally. So this is the growth part of the market. So it started going, and now in 2020 it stands. This is the worldwide laser revenue. So that's what photonics. And if I come to lasers, then the laser revenue worldwide stands at $16 billion in 2020. And then if I take it further, then this market is $27 billion, and we say in 2026 with a CAGR growth of about 6.5%. So these are the different segments on the lasers, the use of lasers, communication, data storage, display and light source, sensors, instruments, R&D. Of course, this is also a big segment, almost $918 million, so close to about $1 billion market. Military, it's a $4 billion market. Medical, again, is about $2 billion market. Then photolithography, marking, micromaterials, and macromaterials. So combined laser market globally stands at about 27 billion with a growth of about 7 to 8%. Now, if you see in India, what is happening in India? Of course, India is an emerging market for lasers, so there has not been much activity in many years back, but now the industrial side of the market is growing very, very fast. Worldwide, if you see globally, the scene is like that. Almost 20% market is R&D and 80% market is the industry. So India is still catching up on the industrial side, but already there is a sizable market. And in last year, 2021, the market size is about $3.5 billion for the lasers. So this is at a much faster growth than the global growth. So India is growing at a rate of 12%, and the market is expected to be $6.9 billion by 2027. And the growth factors in India is healthcare, defense, telecommunication, and industrial. So this is an overview of the market in India. Currently stands at $1.31 billion, and it is expected to be $3.02 billion. Major markets of course, industrial lasers, medical lasers, defense and aerospace, communication, research and development. And this is the data which is published, so I have picked up from there. Now, what is the all different markets? So industrial laser market, That's mostly for industrial applications, mainly in automotive sectors, then medical device manufacturing, the smart car industries, diamond industry is one of the major users of the lasers actually. So all these segments contribute almost to $227 million in 2020, and suppose it's likely to be $287 million by 2025. CAGR growth for this market is 4.8%, but I'm seeing post-COVID the market is growing much faster. So my personal estimate is that this market is growing right now in India at the rate of almost 15%. Medical laser market, of course, we are a 1.4 billion people country, so this market can never be low. It will be only growing with time. So more number of people, more devices and the diagnostics, treatments are required, and lasers are going into medical field in all kind of surgery, dermatology, ophthalmology, dentistry, and LASIK, ophthalmology, of course, LASIK. So there are many, and then bioinstrumentation. So this market at present is about $47 million, which is likely to grow at 12.8%, and by 2025 the market size will be $87 million. Defense and aerospace, of course, you have heard 3 talks and everything is based on lasers, it seems nowadays, so a lot of activities are there, and particularly with Atmanirbhar Bharat and Make in India, the defense is one segment where not only we are building our own requirements, but also, according to our Prime Minister, this is going to be a big export from India. So the target is the export, means Dr. Haribabu Srivastava has touched a lot of aspects of that, and it's really a big market which is growing very, very fast. And I was in a defense expo last year in Ahmedabad, and I was surprised to see the products which have come from the defense sectors into, means if you compare 20 years back and now, the scene is very, very changed. So lasers are used massively into defense sector for cladding, surface modifications, direct energy depositions, and now of course in the DEW. So this is one area which is growing, which is also very important for our country. Of course, somebody asked the question whether we need the destructive weapons, but it also depends on where we are sitting and what are your border conditions and things like that. So I think India is in definitely dire need of building these capabilities to defend ourselves. And this market valued at $231 million, likely to be $358 million by 2025. So it's a big market segment for lasers in India. Telecommunication laser market, this is a well-established market in India and going on for past about 15 years or so. And there are a lot of key players from abroad. There is some fiber manufacturing in India also for last several years, but majority of these are coming from abroad. And my company Coherent is also one of the major players into this. So we have a big telecommunication sector and we supply all over the world. And then other players are Lumentum, 26. 26, of course, 26 and Coherent are now together. So 26 bought Coherent last year, and the combined company is now called Coherent. So then Fujitsu and Sumitomo. So this market is 1.5 billion in 2020, likely to be 3.2 billion by 2025. CAGR growth of this market is still very high in India. It is 16.2%. So scientific laser market. This is where I started, and I know it has grown from 0 to this level now. So scientific laser market is driven mainly by research activities in various research labs, and you can easily see that why the market is growing. First of all, there are number of research institutes have multiplied in last 10 years or so. So when I was in IIT, there was only 5 IITs, and now there are, I think, 23 IITs. And similarly, there are a lot of other research institutes, ISER, NICER, and all are working into various research areas where lasers are heavily used in spectroscopy, ultra-fast research, then life sciences, biological research, microscopy, and many, many other areas. So laser market in scientific area is $85 million in present year, which is expected to be $150 million by 2027. The CAGR growth for R&D in India is still very strong. Globally, of course, the scientific market is not growing that much. I think the CAGR growth globally is about 8 to 9%, but in India, because we have taken very late, means we started late, we are now having sufficient funding, our government can give lot many projects into the research and development area, so the growth rate is pretty high, and it is about 15% in R&D sector. So this is future outlook. So indigenous development of lasers and laser-based machines, very much needed in India. India, there is not much manufacturing right now, so most of the things are imported, and of course, like Dr. Srivastava has said, that some of the companies have started making some lasers with the help of defense R&D, and for example, SFO is doing some activity. And I want to tell you that we are also doing a very similar activities, and we have reached a power level of about 2 kilowatt already, single mode. So we are working on the high power, because this is quite a challenge. So as we have given these approaches, we are using right now an approach which is oscillator amplifier approach, and go only up to from 2 to 5 kilowatt or 5 to 10 kilowatt. But of course, in the future, we may be looking into a spectrally combined approach also. Yes, but in order to, what is needed in India, looking at this market size, we need to think now seriously why India is not having manufacturing activities in this area. So my purpose was to give this market size so that you are forced to think that there is a need of building all these lasers, optical components like translation sensitivity, galvanic scanners, optics, controller, software in India, so that we can build our own lasers and own machines. Fire lasers, for example. Fire laser is a need of today's need into the laser industry, into the whole industry actually. Every industry we talk about, whatever is the market, 80% of that market is fiber lasers. And the range of fiber lasers which are used into industry is from 1 kilowatt up to, let us say, up to 20 or 30 kilowatt. And these lasers are available commercially globally. But in India, when we talk 2 kilowatt, this is still not available. So we have to build these lasers. Single mode, of course, is the requirement for the defense. But for the industry, the requirement is multi-mode. We don't have even multi-mode lasers in India. So, because the technology has to be developed. If the technology is there and it is transferred to the industry, I think that is the right way of going for the manufacturing. Otherwise, we will be only looking for the joint ventures from foreign companies and bringing them there and building those lasers in India. So fiber lasers, diode lasers, he said diode lasers, 9 watt single emitter and 30 watt diode. So today the situation is that my company Coherent, they make a single emitter up to 65 watt, and we are already having a diode module up to 500 watt plus. So the diode lasers needs to be DPSS for industrial applications. Indian market demand is sufficient to start large volume production in India. Research institutes must develop the technology, and the recipe or the technology transfer should be done to the industry. I think this is something which we need. And industry is ready to even participate in this program. We are ready to fund some of the projects if research industry is keen. So funding, partially funding, of course. Defense people are there, they get a lot of funding in any case. But we are ready to participate in these programs and do a joint development. We are already talking some joint development with BEL and CHAS Hyderabad, and we are actually working on some programs there. But we need the larger number of manufacturing now, in large manufacturing in India, so as to cater to the industrial demand as well as to the defense and aerospace demand. And of course, R&D is one area where a lot of lasers of different kind are used. My personal feeling is that R&D
demand is always at a very high end of technology. So we can probably still leave it to the foreign companies because this requires a lot of efforts. But I think for the industrial use, the laser should be made in India. So with that, I will end my talk. Thank you very much.
Thank you.
Thank you very much, Dr. Lalit Kumar. Quick questions for Dr. Lalit Kumar. I know we have our lunch is waiting for us. No questions? Yeah. Okay.
Thank you, Dr. Lalit Kumar. First of all, coming on short notice and giving very illuminating talk. What is the breakup of optics, sensors, that is detectors, and laser systems per se in the photonics market typically? That is globally
So
and in India.
I have all this data with me.
Okay.
I can share it with you by email because I don't know the numbers often. But I have, I think, a lot of data with me. So on every sector, means whatever segment you like to have some data, I can share with you.
So one quick question from my side. Many of the speakers have talked about critical materials, obviously. So which are, I mean, some of the materials which come to your mind, what India should invest in, looking for them and things like that?
So materials for laser manufacturing is, of course, the yttrium fibers. These are the raw materials basically, and the material can start from fiber manufacturing. But also for the solid state lasers is the neodymium yard or neodymium silicate or phosphate glass. Those are the glasses.
So right
some of these glasses we are already making in India.
Okay.
Yeah,
I see.
Because CGCRI is making some glass, and I think RRCAT is having a joint program with CGCRI probably to make these glasses.
Okay.
But more and more materials are required also for example, frequency doubling and tripling. So when you are doing this, then you require some crystals, high-end crystals. It is also some programs are going on, but we really don't have a commercially ready product out of the lab where we can say, okay, we pick up this technology, we start building that.
So that should also be included in the recommendations.
Right. That's right.
Crystal is only one company in the world.
Crystal, everybody is importing from Record.
And everybody is growing also.
Yeah, so I think this should also be included in the recommendations because that is can become a bottleneck. Yeah. Okay. So I think we have come to the end of this very exciting session. I thank first of all the speakers for very illuminating talks.
Thank you.
All of you for participating in this discussion and making it what everybody is doing. Thank you. Your number is there.
Thank you very much.
Thank you very much.
Thank you.
Let us also thank the chair of the session for this very informative session. And I request Dr. Nathe to please hand over the memento to session chair. Photo.
Thank you very much.
Thank you all, and we'll begin our next session at 2:15.
Okay.
Thank you.
Thank you.
ये ऑडियो है ना, पर इसमें
आपका ऑडियो जैक है कुछ कंप्यूटर का?
हाँ, पर इनका
ना फिर हमारा शेयरिंग का इशू आएगा, ऑनलाइन स्ट्रीमिंग कर रहे हैं ना, उसका इशू आएगा।
ऑडियो यहाँ से निकाल लेंगे।
मिक्सर से लाइन लेके यहाँ डाला हुआ है, दैट वी आर यूजिंग इट। ओके, अदरवाइज ऑल अदर ऑडियो विल बी डिस्टर्ब्ड।
ओके, इसीलिए हम लोग बोल रहे थे कि इस पीसी में आप लेंगे तो हमारा कुछ भी डिस्टर्ब नहीं होगा।
हाउ टू टेक नहीं
लाइन इन
आपको झूठ नहीं बोल रहा हूँ मैं।
नहीं, मुझे कुछ वो नहीं है। अब वो सर और ज्यादा अच्छे से बता पाएंगे।
कंसर्न नहीं है, बिकॉज आपका भी ऑफिस का कुछ पॉलिसी होगा।
नहीं
सर इनको कुछ दे सकते हैं क्या?
ऑडियो का
1.26 GB है
इस मोमेंट पे सेटिंग
1.26 GB है फाइल।
ठीक है।
नहीं, yesterday we have downloaded
नहीं, sir.
video through G drive, approximately 1 GB.
G drive I can't upload it.
Okay, you can upload it.
1.26 GB.
Okay. No, yesterday we have downloaded it.
Yeah.
Some
इसमें पेनड्राइव
person
डिटेक्ट
from
नहीं
ISRO,
होगी। अच्छा,
a person from ISRO has sent the same thing.
And on the other hand, if I send it also, the fonts are not there with it.
Yeah,
everything will go topsy-turvy.
No problem. The main problem is you can display this to here also,
Yeah.
but since we are sharing it, we are streaming it,
Yeah.
so we have issue in those.
Yeah. This is the audio.
I'm not able to hear.
Let me see. Did you detect anything? This audio is there, right?
This is the audio.
Okay, so let's see whether it works here. This is what I'm here now. Is this button? And Wi-Fi here is what? No, for streaming it online, I can stream it also from here, right?
नहीं घर जाऊंगा ईशान भी घर पे ही है। हाँ This one is there in this instrument.
Okay.
It's connected.
सर मैं निकलूं लंच के लिए?
हाँ आप जाइए, आप कनेक्ट हो गए ना।
क्या ऑडियो आ जाएगा?
ऑडियो यहीं से लेंगे।
अच्छा, ऑडियो यहीं से
हम ऑडियो लाइन डिस्टर्ब नहीं कर रहे हैं।
अच्छा, ठीक है। नहीं, ऑडियो पोर्ट कौन सा 3.5 है?
हाँ, नॉर्मल पोर्ट है।
3.5 तो 3.5 का अपने पास वो भी नहीं है। ठीक है, इसी को यूज करें तो ज्यादा बेटर।
ये अपना ऑन है ना?
क्या?
हाँ, कनेक्टेड।
Connected?
Yeah.
No internet. No internet. Charged.
I can connect it through my mobile also.
Okay, fine.
Signal very, very bad.
Baat VC link. And network will be poor here.
बहुत poor. You have the VC link?
Yeah, we have the VC link. I just need to ask.
I think I have it here. VC link is there in CV Paul.
So what will happen is when you
Regarding the connection.
there's a lot of research done in let's say optics on lasers.
It's only YouTube link is there.
Yeah.
You have expertise in that.
Your session is at Just after this or?
Yeah,
To the share?
can you see the program ones? Or to CVS Kiran? First one is mine. Yeah, first one is
Hyderabad. You delay mainly
rockets.
rockets. Okay.
We build rockets.
Okay, so you are developing rockets for ISRO.
No, for ourselves.
For yourself.
Yeah.
Okay.
We have our own customers and everyone.
Okay.
मैं जा रहा हूँ मैं जाता हूँ सर
सर ये तुम्हें से बात करना पड़ेगा
मेरा पहले ये तो मेरा तो फिनिश ऑफ वन थिंग राइट क्या उसको अटैच करने के लिए टॉम को बुलाओ ना क्या बात हुई
we need to give internet connection and Bharati link.
मतलब बाकी सब भी ऑफिस ही है लेकिन
So this is the map here. Of course, commercial oil companies who are there. अभी इसको we are publishing it in that AM Chronicle.
उसका भी आया ना उसने भी जितेंद्र
But that is only for DED. ये पूरा है PBF. Only companies who are making it. So anyone is missing? किसमें है वो?
DD में हमारा लाइसेंस है
उन्नति 5D है उसका लोगो देखना पड़ेगा
गेट पे खड़े हो कहाँ रखते हो इसको कहाँ रखते हो सेशन डे 2
Session
नहीं अरे राजा का तो बुझा ना नहीं राजा का गलत जगह है राजा का सेशन 4 है
सेशन 4 देखिए एक बार 4 में क्या है
खाली होगा नहीं
अनिल
अनिल बर्फ के साथ है राजा का बाद में उसका आया उसने दिया बाद में इसलिए जैसे almost every institution wants to work with such kind of so there will be some gaps. If there are gaps, then we will find something to do this question.
Yeah, sort of partially started. At least here it is coming now. You have to see how it goes on to the.
We'll ask him, but after this you have a.
I'll tell you, I'll meet you for lunch upstairs.
Yeah.
We have not had lunch yet.
No, we'll come.
I'll meet you.
Yes.
When Tom is not picking, we'll go up.
Yeah.
Come.
I'll.
Yeah, that's fine.
आलोक हाँ नहीं नीचे विक्रम साहब है हाँ आ जाओ आ जाओ आ जाओ मैं इधर ही हूँ ओके अरे इसका चाबी है क्या तुम्हारे पास चाबी तुम्हारे पास है और निशान अंदर रखे हैं वैसे
सर किसका किसका था? ललित कुमार का था फुट है? अच्छा ठीक है, उसी ने कनेक्ट किया होगा। ठीक है, ओके। कनेक्टेड है ना, पीपीसी कनेक्टेड है। इसको हटाना होगा ना? उसके प्रॉब्लम ये है कि वो प्रसारण नहीं होगा उसमें, प्रसारण तो अच्छे से होगा ना, ये तो इसमें कई कुछ और भी चल रहा है। मुझे एग्जैक्टली पता नहीं उन्होंने नहीं, ये तो हो गया ना, ललित वाले तो हो गया, ये हो गया, बस यही है ना। उनका प्रसारण नहीं आने देते हैं, उनको बोलेंगे आप लैपटॉप को इधर से इधर कनेक्ट करो। नहीं, एक्चुअली वो क्या आईटी वाली टीम थी ग्रुप वगैरह, उन लोगों ने कुछ किया है भी नहीं इसमें कुछ। Load my talk. Okay. Yes, sir. Yes. ये तो connected है. Yes. Let us load this. You have C. You need this C type. So I'll get that after. Yes. USB tool. मेरा बैटरी निकल गया. कहाँ पे सर? लगा हुआ है क्या? मुझे तो लगता है वहीं छूट गया. नहीं? है. ये वाला. नहीं. ये तो सब अभी यही है सर यहाँ तो. यहाँ तो नहीं इधर ये छोटा तो बोल्ट है. पेन ड्राइव सर हाँ है. इसमें छोटा सा. Mine is in the last session, so it's not not a big deal. But we can try. But we can share. Yes, it is. Copy both of them. I'll decide which one I'll choose. Okay, no problem, sir. This sorter and this engineer. Yeah. Yes. These two? Yeah. But how will you know my name? Yeah, I will copy and I will put it in Ravi. I will create a one folder. Put it called Ravi. Yes. Ravi. That's it. And then I will copy to this place. Can I just check how it looks? Actually, sir, this transmission people is right here. Yeah. So yes, we can open over here. No Look problem. At the shorter one. This is the. Okay, just go to F5. Yes. Screenshot. Next. This should not be here. All these are hidden. Which one did you take? You took the shorter one? Yes. This no. I just the first one. Let me. This is engineer skill. Take the shorter one. Yes. This is shorter. Yeah. Okay. Okay. Just go to F5. Okay. Slowly, I am doing one by one. Yeah. Perfect. Yeah. I just removing your drive and giving it. Sure. Maybe we can actually delete this other. Yes. I will. No, we'll do it later. Okay. Doesn't matter. Yeah. Thank you. Welcome, sir. ओके जैसे आप चाहें नहीं इसको हम कॉपी कर लेंगे यहाँ पे
नहीं फिर वो एक्चुअली वीडियोस नहीं चलते
ओके ओके।
वही तो ना, तुम मुझसे पूछा ही नहीं।
हाँ हाँ, तो आपका कब है आपका?
थर्ड नहीं, प्रोफेसर पॉल के बाद।
प्रोफेसर पोल के बाद है ना? तो मैडम अच्छा अभी आप जस्ट चेक करना चाहते हैं? आ जाओ भाई आ जाओ। मैडम का क्या है ये जस्ट चेक करना है। पेन ड्राइव में लगा देता हूँ, आप चेक कराइए। मैं लगा देता हूँ, ऊपर ही लगा देते सर। हाँ ऊपर है पोर्ट।
हाँ वही लगा दीजिए, बना रहने दीजिए अगर एक्स्ट्रा पोर्ट है आपके पास।
ये देखिए ओपन हो गया, यहाँ से ऑपरेट कर सकते हैं।
हाँ कर सकते हैं।
रवि सर का भी आ गया है, प्रेजेंटेशन फोल्डर में रखा है। ये फर्स्ट वाले हैं? पता नहीं अभी ये लैपटॉप नहीं, एक्चुअली ये सब बोल रहे थे कि यहाँ से फिर रिकॉर्डिंग में जाएगा।
So let it be there. So let the pen drive be there. Don't copy anything.
ओके ओके, या आप अपने पास रख सकते हैं मैडम, वापस लगा देंगे।
बट उसमें लोड करने में टाइम लगेगा जैसे अभी लग रहा है।
हाँ थोड़ा सा टाइम लगेगा।
या तो अच्छा लगा रहने दीजिए, अगर आपके पास एक्सेस पोर्ट है तो। एक्सेस पोर्ट
सर इसका क्या ये पेन ड्राइव से रन करेंगे?
चलेगा चलेगा, वो तो बेस्ट
छोड़ सकते हैं ना?
बेस्ट है।
ठीक है।
आपका सेशन अभी है ना?
थर्ड इस सेशन में थर्ड लेक्चर।
वो प्रॉब्लम होगा ना, ये संदीप, ये केबीएस के रन स्काई रूट हो गया। हमने आगे वालों को भी बोला कि यहाँ से नहीं करना है, सेक्रेटरी को नहीं करेंगे, क्योंकि अपना ये वीडियो नहीं चलेगा बाकी
आज के सुबह के 4 लेक्चर का देखा
बैकअप है इसमें चल रहा है। इसमें भी चलता है, ऑनलाइन भी चलता है, यूट्यूब पे भी चलता है।
स्लाइड का
नहीं, हाँ तो आप कर लीजिए, लेकिन एक स्लाइड नहीं है उसमें। हाँ चलेगा। उन्होंने वो बोला था कि वो डिलीट कीजिए सर ऊपर लगा।
हाँ इसी में डाल
डेट इसमें किसने रखा इसी टू कमेंट।
हाँ डेट बाकी चीजें भी हैं, पता नहीं जो जो कॉपी कर
मैं इसमें डाल देता हूँ, पेस्ट कर देता हूँ, है ना? अभी लेटेस्ट है।
हाँ ये एक समस्या तो क्या होगा?
रिजेक्ट नहीं कर देता।
मैडम का भी कॉपी नहीं करना है ना? मैडम ने कॉपी करने का मना किया है, तो उसमें पेन ड्राइव लगा है मैडम का।
मैडम के पेनड्राइव से थे।
पर वो उस पे नाम लिखते हैं एटलीस्ट, तो मेरे को समझ में आएगा।
नहीं पेनड्राइव में है ना उनका, वो कॉपी नहीं की है।
कौन से नंबर का सेशन रहेगा ना मुझे नहीं पता।
नहीं वो आएंगे ना, मैडम आएंगे।
शुक्ला मैडम, अच्छा आज इनका थर्ड लेक्चर है
ये जो बोलेंगे वो पेनड्राइव से ओपन करके उनको दिखाना। हाँ इसको पूरे स्क्रीन पे रखो।
हाँ
स्क्रीन पे रखो, स्क्रीन में रिकॉर्ड कर रहा हूँ, विंडो विंडो नहीं करता हूँ। इसको हटाता हूँ
क्या डिस्प्ले
जो भी खुले अभी कैप्चर डिस्प्ले करते हैं। इसके बाद अभी पेंटिंग में क्या है, मैंने चालू नहीं किया चालू नहीं, बट वन इम्पोर्टेंट
क्या
Vikram S, which was launched last year, the first suborbital mission, Vikram 1, Vikram 2 and Vikram 3, where the payload capacity ranges from 480 kilograms to 815 kilograms. The Vikram 1 uses 3 solid motors and an uppermost liquid stage. Vikram 2 uses the same 3 solid motors and an uppermost cryogenic stage. And Vikram 3 uses the same 3 solid motors, cryogenic stage and strap-on boosters. With these, we are able to cater to the demand-driven nature and also are able to modular upgrade from one system to the other system depending on the necessity of the customers in very short time, and assemble and launch within 3 days. And it also requires minimal launch infrastructure because these are small satellite launch vehicles. With keeping all these things in mind, we had the successful Vikram S launch, which is a small video what you can see here. Where we had the successful testing of the solid rocket motor before it was flown. Solar Industries, Nagpur. We had 4 spin thrusters, which are also based on solid propulsion, fully 3D printed, mounted on the circumference as you see here, and successful testing of that to initiate the spin of the launch vehicle. Full carbon fiber composite body. We had customer payloads on the first flight, one from Armenia, Space Kids India, and N Space Technology. And we also had some cards which flew from every employee of Skyroot to space because it was the first flight. And finally, on 18th November last year, we had the first historic flight. The onboard camera shows beautifully the coastline at Sriharikota. And in this slow motion video, you could actually see once the launch vehicle leaves the launcher, at that point we actually have the spin motors being fired. And these 4 spin motors initiate the spin of the launch vehicle. So at this point, you'll be able to see the spin motors being fired. So this initiates the spin of the launch vehicle. And through the whole process, we were able to also say we had a successful liftoff. We said hello to space, and we also had a moment of triumph, and also proven a lot of our own systems for the Vikram 1 orbital launch, where we also had laurels from the Honorable Prime Minister of India and the President of India, where the Honorable Prime Minister spoke over 3 minutes about Skyroot Aerospace and the launch in Mann Ki Baat. And we also had a lot of laurels from the national and international media. Recently, we were also bestowed with the Forbes Emerging Innovator Award for the first successful launch. And in all these things, we have embraced additive manufacturing in all three major propulsion technologies. So as all of us know, we follow the standard chart of regular product qualification to final inspection, where we use for critical components a Renishaw machine. The reason for using Renishaw machine, it is having a pulse laser instead of a regular continuous laser, wherein we are able to print ultra thin walls. We have sometimes even printed walls of the order of around 150 microns. And then whenever we qualify these things, most important point what we always face is the standards. So very important point what we can see is general quality standards apply to additive manufacturing. In addition to that, we also have the aerospace specific industry standards. Then we have the production manufacturing standards. Then comes the AM specific standards for that particular material. And also the original equipment manufacturer and the company which is actually making the design also have their own qualification standards. So all these standards have to be incorporated into a proper framework of standards for printing any component which is going to be in production. So this is very important for additive manufacturing. In addition to all these standards, there are a lot of parameters in additive manufacturing which are very critical. Unfortunately, this slide looks very, very messy, but all these parameters ranging from surface roughness to the volume availability and the flexibility of platform. I can't read all these things, but you can see that there are plethora of points which are very, very critical for every application and which depend completely on the product, whatever we are going to use. So product actually defines what we want to qualify. And all of us know that there's a very good standard available, the NASA 030 standard, which is globally used for qualification of additively manufactured components. So from certification and qualification, both of these things are equally important in additive manufacturing. And both of these things have to be differentiated. And people, especially in India, we have to learn to differentiate between certification and qualification, because some of the systems what we use are from vendors. And in addition, if we talk about production, what platform are we 3D printing, what material are we 3D printing, and what is the process what we are following for 3D printing, and what is the component what we are using for 3D printing. This is the entire basis for production of any 3D printed component on a regular basis. And of course, we have a lot of discussions whenever we have discussions with service providers. Some major points are very important, especially the wall thickness of the component. What minimum wall thickness do we require? What is the smallest hole dimension what we have? What type of DFAM software, designed for additive manufacturing software, is the vendor using? And how experienced is the vendor in aerospace components? What materials here the company has printed, and what tolerances have been achieved after printing? These are some of the criteria which are very, very important whenever we qualify any vendor for 3D printing. And with all these things, after discussing with lot of service providers, we were able to successfully print the components whatever we have showcased before. And by doing all those things, we also had very nice interactions with a lot of leadership team of the country, where we had interactions with the Prime Minister, also the ISRO chairman, the InSpace chairman, and Jitendra Singh ji. And we also won the National Startup Awards. And we also won the trust of the investors. And these are our investors. And this is one of our facility which is there already existent, and it's going to come up very soon. We also have quite good recognition from the international space agencies. And finally, to sum up what you see, this is our journey of Skyroot. We started in 2018, where we were established on 19th July. 2019, we did design and manufacturing, where we produced the first injector system. Then 2020, we had manufacturing and qualification. 2021, we did successful testing, and also did sign some launch service agreements. 2022, we had the first historic launch on 18th November. And 2023, we are aiming towards our orbital launch this year. So as an outlook, where additive manufacturing is going, or what the industry, especially the space industry, needs. Some points are put forward here. Medium-sized additive manufacturing components are going to increase, especially in their demand, 1 meter height and 1 meter diameter based components. Large additively manufactured components are also going to increase 3 meters and 1 meter diameter. Bimetallic components are going to have lot of interest, especially taking in insights of copper-based systems, because of the fact that they are very high conductivity, which is very useful or important for high temperature applications. And interfacial studies, what happens between copper in combination with superalloy copper in combination with stainless steel, become very important. And printing of exotic superalloys are also going to be very, very important. Meeting aerospace standards, especially catering to the needs of quality, reliability, and repeatability, is going to be very, very important. How do we repair a additively manufactured component we did not qualify? This is also going to take a major role. And how to qualify a rejected component, especially after repairing it. I don't have answers for these things. And how do we repair an in-service component? And how manufacture parts economically, efficiently, and carry out optimum defam. These are some of the challenges which are going to be very, very important, especially in the next 5 to 10 years. So with this, I thank once again everyone for your patience.
Okay, we have time for some questions.
Not in situ techniques are there, but we don't measure it in situ, we measure it post on the component. So whenever we do initial simulations also, we check wherever residual stresses are existent, and depending on that locations, we carry out residual stress analysis.
Okay, I think
many times people say that additive manufacturing is not very great and lot of problems, etc. What is your take on this after working almost for 2-3 years, right? Because during that study, but there also many things were brought in.
So whenever we embrace any new technology, it is always the beginning. Somewhere we have to start, and these hiccups are always there. And how do we overcome these hiccups is the only challenge. Of course, we also have a lot of challenges like that. For example, one of the component where we had one missing layer came up. How do we repair it? We repaired it, we reused it, we qualified it, and it successfully also did the firing. So. Yeah, so you have seen the second slide where I presented different types of additive manufacturing. There are wire arc additive manufacturing is one route which people try to do in combination with DED or direct DED to different layers, or laser powder bed in combination with cold spray additive manufacturing, or DED in combination with cold spray. To the best of my knowledge, where everyone recommend is DED in combination with cold spray, which works better. But very important, whenever we do such things, metallurgically there are, I'm a metallurgist by the way, so metallurgically there are some phases which are very, very critical, and when it comes to the fact that any Laves phases or intermetallic phases form, it leads to catastrophic failure. So one has to be very conscious about the interface. That's the reason interfacial studies become very important.
Hello. What are the problems you faced as a startup? And at the time of the starting, maybe 2018 and presently?
So when we started, there was no policy at all. There was no space policy. So when we started, we were always thinking of how, what. But luckily, we had the Honorable Prime Minister announcing the space policy, opening all the space activities for the private sector, wherein immediately things have changed. We were able to access the facilities of ISRO. We were able to access the facilities of other organizations which came forward for giving us, the opportunity to test our things at their facilities like DRDO. So it was quite tough. But in the whole process, the regulations are the main hurdle. But now InSpace has been formed. InSpace takes care of all the regulatory aspects, and it also consults with all the other bodies within the country, and it has been given full powers to negotiate or talk to all other parties and get the necessary acceptances and everything. So that way it was very good for the first launch. But in addition to that, there are a lot of things which we can't foresee as a startup. And one thing, major thing is everyone tries to build a startup with the technological idea and does not think about the business model of it. That's the most common mistake which people do and where people fail. So however good the technological idea is, without a proper business model, nothing works.
Okay, thank you, Dr. Kiran. Again, please.
Thank you very much. Thank you. Thank you very much. नहीं और इसी में है ना उस मेरा हो गया Yeah.
Okay, shall we move on? The next speaker will be Shri Yatiraj. He is General Manager at Wipro 3D, Bengaluru. He's taken part in the Executive Education Program of IIM Bangalore. He holds a Bachelor's in Mechanical Engineering. His area of expertise is in aerospace and automotive domains. He's had a variety of different achievements and awards. He's been design engineer, turbo tech, defense and aerospace, and so on. A series of things. Okay. Mr. Yatiraj, please.
You want it? Yeah, good afternoon, ladies and gentlemen. So I was thinking why the room is dark, but now it is bright. So Dr. Kiran spoke a lot about how additive manufacturing is being used in space industry. I'll probably take the next step. Like I am actually going to cover how the additive manufacturing has been used in India and abroad for space, aerospace, and defense. So that is going to be the focus of the next 20 or 30 minutes. So I come from Wipro 3D. Wipro 3D is an end-to-end additive manufacturing service provider where we do both metal and polymer, where we provide metal and polymer printing services for both prototype and production parts. You have the clicker. So the way I have structured my presentation is I am explaining where the additive manufacturing is being used, which means which areas it is being used and why it has to be used and how it is going to be used for both prototype and production purpose. Focus is going to be mainly on the production. So these are the areas where typically the additive manufacturing is being used in aerospace for various applications. Like if it is aircraft itself, typically structural components are cabin parts, both metal and polymer. They do use it in the aircraft level, and even at the helicopter level, various structural parts, mounts, rotating parts. Engine, it is used very heavily. In fact, probably in the aerospace, the engine OEMs use the additive manufacturing to the maximum extent, more than anybody else. So GE recently had launched the engine called catalyst engine, where one third of the engine was actually 3D printed. So all the external cast parts were 3D printed. I was part of GE before moving to Wipro. I worked there as Asia Pacific leader for AdWorks, which is their group for consulting. So this is why we have to use additive manufacturing. So there are various reasons. I'm sure Dr. Previous speaker actually covered some of this, but these are the main things why we should use it. So additive actually allows you, additive manufacturing, when you embrace it completely, you really can actually customize a lot of parts. Customize for efficiency, for weight reduction, for size reduction, for improvement in efficiency. So there are many things which you can actually do. I mean, there are many reasons why you have to actually customize when you have to do the manufacturing through additive manufacturing. So some of the advantages like weight reduction, optimize post processing. You can actually reduce the post processing effort also if you have designed the part well. So functional performance, toolless production. So Dr. Kiran was mentioning, he can actually realize the parts within days, whereas it would have taken 6 months. So that is mainly possible because you go with a toolless production, which actually enables you to cut down the cycle time. And cost-effective iterations. So when you're able to get the prototype in your design phase, when you're able to get the prototype in weeks rather than in 6 months, you'll be able to optimize your designs much faster, and hence you can actually design a better system at the end of the day through cost-effective and faster iterations. So you can do a lot of topology optimization and complex geometry. He did show you examples of how he has integrated the tube and everything, and the cooling channels and things like that. You can achieve monolith. You can combine many parts and make it into a single part. This is another big thing. I mean, all these 4 things: supply chain issues, maintenance, repair, and overall obsolete and legacy parts, and flexible production. So once your product is launched, especially in aerospace, once your product is launched, the product is going to be there for 30, 40, 50 years. I mean, if you see Indian defense scenario, we have so many aircrafts which are like more than 50-year-old, and the OEM is not able to supply those parts. And there lies the opportunity, another opportunity for additive manufacturing, where we are coming into a picture to do the reverse engineering and the digital inventory, digitalization of the inventory, and we are able to actually make the parts which are not being able to sourced from the OEM, because either OEM has phased out those products, or actually some of the OEMs have even gone out of business. So these 4 areas are big trigger points when it comes to the aftermarket. So this is a typical additive manufacturing process. This is the how part. I mean, how are we going to do the manufacturing part? So it starts with a design improvement idea. Then you do a lot of application-based simulation. So when I say application-based simulation, when you do combination of parts or size reduction or weight reduction, how is it going to perform in the field, whether it is meeting the functional requirements or not. So those are the application-based simulations, and during that you will also add in your additive design considerations. There are many design guidelines which you need to honor when you are designing the part for additive manufacturing. Otherwise, the cost is going to be prohibitive. So if you are taking care of these design rules during your design phase, the additive rules during the design phase, you can actually have a very optimum system which will be very cost effective. So once you have the additive design, you will then move to the AM process simulation, where I will simulate the building of the part to understand how to orient it, how to optimize the batch, how to avoid the, let's say, the recoater issues and things like that, or even for that matter, even the quality issue. So some of the critical areas which needs a better surface finish, I have to take care during the build planning, and this AM process simulation becomes a very key step in that one. And then we go to the process planning, where I will do not just the additive process, including the how am I going to remove the supports, achieve the final tolerances which are required for the functionality, and then also how am I going to do the quality inspection. So
additive actually gives you a lot of freedom. We all would have heard about the design freedom which additive gives you, and engineers do go crazy when they actually design for additive manufacturing. They design a lot of lattice structures and unique structures which are not possible with conventional manufacturing. But when you are using those kind of features, you also have to see how you are going to inspect those features during the process planning. So if you are not able to inspect a particular feature, then there is no way you will actually qualify that particular part for a functional deployment. So you have to do all those things during the process planning. How are you going to print it? How are you going to machine it? How are you going to actually inspect it? And then you do the 3D printing. We do definitely a stage level inspection. At every stage, we do the stage inspection to see if the part is still on the right track or not. And then we do post-processing. It is nothing but the conventional machining to achieve the tolerances and finishes which are required by the part. And then finally, we do the quality inspection. So this is just a 3D manufacturing process. But is this all we have to do? Definitely not. So for every industry, there are guidelines or certifications which are required to be honored by everybody in the industry. These certifications or certifications basically are meant to make sure that the quality standards are adhered and the OEMs do not have any problem in actually making sure that the part, when the part is realized, all the aspects are really taken care. So these are some of the certifications which I have listed here. So main one is ISO 9000, which is like a basic quality management system, which kind of gives the assurance to the OEM or the customer that, okay, the organization which is ISO 9001 certified will actually abide by certain process, and if the contract is awarded, there is a guarantee that the product will be going through a certain process compliance. Similarly, building on that one, AS 9100, which is basically ISO 9000 plus aerospace related additional qualification criteria are there, which makes it AS 9100. And then this is the for the transportation, and this is for the oil and gas and marine industry. And this one is probably a very special one, NADCAP accreditation. So this is a very tough accreditation. Only 14 or 15 companies in the world have that NADCAP accreditation. Till last month, Wipro 3D was the only company which had the NADCAP accreditation for additive manufacturing. Now, last month, one Chinese supplier also got the NADCAP accreditation. So this NADCAP accreditation is very important. While ISO 9001, AS 9100, TS and IS 13485, they are all QMS and process level audits. NADCAP, they do the technology maturity audit. So they make sure that we do understand how the technology works and what are the implications of certain decisions. Certain decisions as in how am I monitoring the powder quality, how am I storing the powder, what are my procedures to store the powder, recycle the powder, reuse the powder, handle the powder, invert the powder. How do I prepare my machine? What is the impact of impurity in the argon? How do I control my argon gas or nitrogen gas? So those kind of next level verification is done in the NADCAP audit. It's a very tough audit. Last time when we got it, we got a silver accreditation, which means that 3 times we have passed this accreditation without any non-conformances. So these are some of the certifications, industry certifications, which kind of gives the OEM an assurance that the company will make or manufacture and deliver a quality product. So this is the qualification process, generic qualification process, which we typically use for space, aerospace, and defense customers. We do the raw material. RM is raw material there. So we. Anybody who has to cater to a regulated industry, like all these industries which I just mentioned, space, aerospace, or defense, or even healthcare for that matter, they have to control the suppliers, especially the powder being the raw material. That plays a very critical role in the quality of the printed component. There are powder specifications which are developed, which goes to the extent of what should be the particle size distribution, what should be the chemistry, what should be the flowability, density, and moisture level, and things like that. So we create our own specification. So Dr. Kiran also highlighted there are layers of standards, and the final one which comes is the OEM standard, which should be the most robust one. So going by that principle, what we have done is we have developed our own powder specification, which is actually tighter than any industry standard for that matter. Yeah, that is what is written here. And then we do the in-house testing of the raw materials. And then the manufacturing plan, which I showed you in the previous one, we make sure that the manufacturing is done as per the approved process sheet. And then the metallurgical or mechanical characterization is done at a coupon level. So what we typically do is there are three phases in additive manufacturing. One is powder level, one is the printed alloy, and last comes the application. So powder is qualified here. The printed material is qualified here for both chemical, metallurgical, and mechanical requirements. And then you actually go ahead and print the component, and the component is typically tested for at a rig level. First for the geometry level, it has to meet all the drawing requirements, and then it has to go into the assembly and do the subsystem and system level testing, and it has to qualify. So typically 2-3 hardware would be required to reach the qualification phase, and then only it will actually make it to the flight test and get a production approval. So now the question is, we all have showed how difficult or how laborious the process is. So are there any parts which are actually qualified in the globe? Of course, yes. So this was the very first part which received the FAA certification. It's a famous part from GE Aerospace, the fuel injector. The tip of this fuel injector, only this part is actually 3D printed, not this stem and the connector and everything. Only this tip, which is the size of the walnut, is 3D printed. So as we speak, it actually goes into every LEAP engine which is manufactured by GE. And as I had read last time, around 1.5 lakh components are already into the field, and there is a website where you can actually track which LEAP engine is going where, and every one of those LEAP engine, almost 19 or 20 of these components will be there in every LEAP engine. So if anyone has a doubt whether additive is ready for production, here is the answer. And this part was qualified around 7 or 8 years back. Then this is from my another alma mater, Honeywell. So I worked in Honeywell for 15 years before joining GE. And this particular component, this is in public domain. This is a engine which was almost reaching the obsolescence. And this is a bearing housing, again another critical part. These two examples, why I'm showing is both GE and Honeywell, they took an approach saying that we will not start with non-critical parts and then graduate to critical parts. Bearing housing is a very critical part, fuel injector is a very critical part for any turbo engine. And both the companies took the approach that we will start with the critical parts, and once that is approved, the engineering community and the chief engineers, everybody is going to be very confident about adopting the technology to a greater heights. So this part was also FAA certified airworthy part. Another example from Rolls-Royce. I didn't work here. This is from the public domain, but I just wanted to. The reason I picked this particular component is the size of the component. So there is no material restriction which is impeding the qualification of the components. There is no size restriction which is impeding the qualification of the component. There is no criticality requirement which is actually impeding the qualification requirements. High critical parts, all kind of materials, all kind of sizes have been proved and airworthy, I mean declared airworthy, and they are into service today as we speak. Not just metal, even polymer parts are qualified as airworthy. A lot of cabin parts, duct parts, environmental control system parts in the aircraft, they all have been qualified as airworthy here. So that's all the global scenario. What about India? Are we really catching up, or are we there, or where are we? So the answer is we are not doing that bad. So Dr. Kiran showed the fleet cluster which was launched by ISRO as part of GSAT 19. This is a GSAT 19, and this was launched in 2016. And this was the first ever 3D printed part, metallic part, to reach space from India. And I mean, I'm really proud that this part was actually designed jointly by Wipro 3D and ISRO. This was actually SAC Ahmedabad, Satellite Application Center Ahmedabad, and Wipro, they jointly designed it. And I should really congratulate the scientists in ISRO for two things. I mean, this was the first ever part, but still they took a lot of initiative in doing a lot of things for the first time. It was a monolith part where they combined close to 19 parts or so into single parts. They were courageous enough to completely design the part for additive manufacturing. If you see the conventional part, it was a sheet metal part which was having a squarish looking these channels or ducts, but whereas here it is a conical or hyperbola or whatever it is. So this kind of a design is what they went into, and they integrated a lot of cooling features also inside. And you will also see a lot of design for additive manufacturing features here to avoid the support and things like that. So completely designed for additive, printed in metal and launched around 7 years back now. And this has been functioning very well in the space. It is still there in orbit. From 7 years, it has been feeding communication signals to the northwest part of India. Second example I want to show you is inner ring. It's a A286 heat resistant steel component, which is again goes into Chetak helicopter for an engine called R2 engine. Again, the problem here was the supply chain issue. HAL was not able to procure this component in time, and they have to hold almost 2-year worth inventory because there was no proper supply chain there. And for that reason, they were holding crores of worth inventory to avoid any issues on the service of Chetak helicopter or the availability of Chetak helicopter. And they identified this for indigenization, and Wipro proudly partnered this particular part. This is a great example of reverse engineering, where we started with identifying the chemistry of the alloy. So we were not knowing what is the chemistry of this particular alloy. We started with material analysis. We created the powder specification. We identified a supplier who could actually atomize the powder to the specification what is required. Powder specification, understanding of the alloy, powder specification, powder manufacturing, qualification of powder, then development of the printing process. So since this alloy was totally new to the additive ecosystem, we have to even develop the printing parameters. So once the printing parameters are developed, we will have to qualify whether the printed material is meeting the mechanical properties and requirements or not. So we did qualify the printed material, then we printed the first inner ring, and then we proved the machining and every process step, and then the part was qualified. It took us almost 1.5 to 2 years to complete the entire phase, but it was the first ever Semilac certified airworthy part, which is approved for serial production. And after this first part, which was certified by Semilac, Semilac is Center for Military Airworthiness certification. So they are the authority to qualify parts for airworthiness in the military world for India. So we didn't stop there. We have qualified multiple parts. All of these parts, which I'm going to show you in this chart and the next chart, every part is actually qualified for production, serial production and deployment into the field. So these are some of the components which are qualified in space. ISRO is the customer here. So exhaust casings, pre-burner impeller, which is a rotating component. This one I just told you, the instrumentation cluster. All of these parts, you can see the alloy. Alloy is also no bar there. Aluminum, zinc-on 718s. You will see many alloys in the next chart as well. So we have qualified quite complex parts, and all of these are certified and into serial production. So this we are able to do because of the certifications what we have, especially the NADCAP, the AS9100. Those certification is actually what making us not divert here and there, and helping us to stay on track while we are printing or producing these particular components. So these are other 6 components which are airworthy for aerospace. The customer could be ADA, HAL, or Air Force. So there are critical components like this nozzle disc, or this is a part of the landing gear system. This is a part of environmental control system. This is a helicopter engine part. So here I'm showing 10 parts, but there are another 4 or 5 parts which are certified already, but I'm not having the liberty to show those parts. But the point what I'm trying to drive home is these parts are very much there, which have gone through the journey of rigorous qualification and certification, and there is a way to actually address the qualification and certification if you address in a structured way. So additive is, we should not be thinking that additive is prototype technology fit for prototype. It is definitely capable of producing the production components, field ready components, and into serial production. So this is a glimpse of the center what we have in Bangalore. You can see we have metal machines, furnaces, machining centers, and things like that, and a lot of qualification and characterization equipment to characterize both powder and printed material and things like that. So with that, I just want to close my talk. So production through AM is here and now. It's not really a technology which we have to see that it is at research level. It is very much arrived, and here it is. Any questions? Yes, sir.
Question I have got, these standards to be there for the aerospace function.
Yeah.
But what is the applicability of the standards for the general industry like power plant?
Yeah, so ASTM has formed a committee called technical committee called F42 ASTM, and they have been functional for almost 7-8 years now, and they have released a lot of standards. So there are material standards as in both printed material standards and powder standards for all the alloys which are of high demand. There is a specification for printing process, how the printing process should look like. So there are a lot of specifications which are already made available by ASTM F42. But the thing is, ASTM F42 is at some basic level. So if you want to control it in a better way, you probably will have to take that as the foundation, and you will have to build on top of it. But straight answer, ASTM F42 will be the good starting point for you.
What are the tests you do on the component level?
So component level testing depends on the functionality of the component. So every component we will create a qualification plan. So depending on the criticality of the part, we will say what are the mechanical qualification needed at the printed material level. So for example, if it is a rotating component, you need to have a fatigue test and other things. If it is a structural, depending on the where it goes, not every part you may require a fatigue analysis and fatigue study for every particular part. So depending on the criticality, we will create a material qualification plan, and in consultation with the customer, we will create the qualification plan for the component depending on the functionality of the component. Correct. So once we typically go with the terminology called FAIR, first article inspection. So the FAIR is a very important thing which kind of gives the customer or the design owner the confidence that the manufacturing process can deliver the component which is meeting the design intent. So when you do the fair, it kind of gives that initial assurance, but later you will have to do much more tests and trials to satisfy yourself. I mean, I'm assuming you in the role of a design owner. So you have to create that plan to satisfy yourself that okay, I'm okay with all the manufacturing process and what the manufacturing process is delivering to you. See, when you are designing, you would have gone ahead with an assumption. You would have gone ahead with an assumption that you will assume certain yield or fatigue or things like that. So the printed material and the manufacturing process has to deliver to those assumptions. So that is the verification you will do. So we have a machine which is 400 millimeter cube, and we have gone up to 390 millimeter. There was a large build around 6 months back. It went non-stop for 19 days. That was the largest build actually we had in the country. No, it was a huge component. LPBF is slightly time consuming because the layer thickness could be anywhere between 30 to 60 micron. That is all you can deposit at a given point of time. And if the exposure area is large, typically it will take time. And what happens is there are multi-laser machines which are available. Where with the multi-laser machine, you will have another variable which you will have to worry about, which is overlapping or stitching. For critical components, typically the customer doesn't want the stitching and he wants to work with the single laser. And with single laser, you can only melt so much.
Sir, as a research engineer, I'm involved in AM part. So can you just tell me any potential issues that you have faced while printing through AM, metal AM?
Yeah, so metal AM, the main, I mean, once the parameters are proven and locked, the issue, I mean, if you're talking about an application, from application to application, the issue would be typically the orientation, which will result in the stresses inside and the distortion. So we typically what we do the process simulation to understand the distortion which will come into through the manufacturing process and provide for the compensation. Which means, let's say let's say there is a cylinder or a conical shape what I'm interested in printing. For example, the exhaust casing. So if it is a large part and a thin wall structure, what will happen is because of the internal stresses, the part will deform after it is printed. So the AM process simulation will actually tell me upfront that okay, there is a deformation which is expected. And what I do is I provide pre-distort it so that I get the nominal geometry. So internal stresses during the printing is one thing which you have to take care as during the production, I would say. Sure, I'll catch you later.
Sir, just one question, sir. If you permit, sir. Sir, I just wanted to know, like, if there is a major challenge between the NDTs we are doing for the casting forging, normal casting forging, and for the AM generated items, because the faces are very, like, number of faces are there, na?
Yeah.
That's what I just wanted to know, sir. If
Correct.
any specific challenge is there, sir.
Yeah. So NDT definitely is a challenging for any component, a heavy bulky component. So see, the thing is the defects are going to be much lesser compared to normal casting. I wouldn't compare with forging, but normal casting, if you are considering, the defects are going to be much lesser. But at the same time, there could be defects. The community, today the big question in the minds of community is how am I going to detect a very small porosity? So while the designs are made for casting, the porosity is actually accepted. But when the designs are made for additive, the porosity, nobody wants a porosity, though it is going to deliver much lesser porosity. So one of the question in my previous company, aerospace company Honeywell, was how do we actually detect this micro porosity? So that's a question which is unsolved. But what is the impact of that is nobody to answer. So why do you want to really detect a very, micro porosity, which you are not worried in casting?
So if since your question was directly in comparison with casting, I'm saying if you're not worried about the microporosities in casting, why are you worried about it in additive manufacturing, which is anyway going to give you much denser material. But if your application is requiring no porosity, like for example semiconductor manufacturing, they don't want any porosity because any trapped gas could, since they operate under extreme vacuum levels, they don't want any trapped gases inside. So there it is a very genuine question, and they're not, I mean NDT methods are not robust enough to detect the microporosities as of now. Sure. Thank you guys.
Okay, then the next speaker is Dr. Christ Paul from RRCAT. Dr. Paul holds a PhD from the University of Waterloo, Canada. He's been working in the area of LAM challenges holistically and promoting this for strategic research areas, looking at next generation additive manufacturing and so on. He received the Homi Bhabha Science and Technology Award in 2018 and a DAE Group Achievement Award in 2016. Dr. Christ, please.
Good afternoon. It's a pleasant gathering here, and we had two prominent speakers, Dr. CVS Kiran and after that Yatiraj from Wipro 3D. So now it's time to talk about additive manufacturing from RRCAT, and probably the difference here we'll see when we were talking about Kiran, then he's the guy who is the primary user of the technology, and then when we were talking about Yatiraj, he's the guy who is making and using the technology for building the parts. And we guys, like at RRCAT, when we conceived the idea of working on this in 2003, so idea was this, that we were knowing that our DAE will not be allowed to work on the strategic material, so we need to have machine, recipe, everything built, and slowly things started moving, and 2009 onwards we are working on this. So we built from machines, process, qualification, and the entire range is done, and many of the things done, and in the journey we learned many of the things. And probably I'll be focusing here what we did specifically for nuclear energy applications, so that we have clear-cut idea away from aerospace and defense applications. So the presentation is like, we'll talk introduction, challenges, global scenario, Indian scenario, and then the efforts what we have done, and then finally we go up to the recommendation. If you see, global energy demand is expected to grow by 50% in 2050, and industrial sector, including manufacturing, refining, mining, agriculture, now we need to have more than 30% increase in energy usage. So this is basically rise in demand. And when we talk of DAE, we always say that now the basic increase in the rise of the energy demand would be from the developing nations, so they have to work on a lot of things in this side. And again, they have to take care of the CO2 emission level down. So again, they have to work on a junction when you have a clean and scalable energy technologies, and the solutions, so definitely you have to work with the nuclear, solar, wind, and energy. And these are the areas where we have to talk of. Traditionally, we have boiling water reactors, pressurized water reactor, and pressurized heavy water reactors generating electricity since 1950. And the problem with this, whenever we talk of developing this, the challenges is we have a very large capital investment, and it is not that, you know, when we talk of the solar energy, probably people are able to put the plants in a 2 months or 3 months time, everything. But here we're talking of 5 to 10 year scale. So there is always a challenge. How can this technology be more smaller, simpler, and more efficient nuclear power units, so that thing can be done? And this is a lot of discussion being done globally, and especially in India, about taking up these things in a form of a small modular reactors or generation 4 reactors like sodium metal phosphate reactor, molten salt reactor. So many things are being done at PRC and other places at IGCAR also. So the idea is that when we talk of this, we need to work on the technologies which are capable of manufacturing component in a new way, so that things can be taken to the next level. And another point that we have facing is like we have plants working almost for more than 35 years. So we need to work on a maintenance, repair, and overall technologies. There also the thing comes, and here the specific reason when we can think of taking additive manufacturing into that fold. So what is happening is like when we talk of introducing additive manufacturing, especially from nuclear power and nuclear power perspective, it can be a very good if we can work on the realization of complex design. See, when the things were done in the initially, more or less we were counting on the thumb rules and doing the design, but today we have advanced softwares and capability available. So it's important to go with the feature-based design and manufacturing and come with the components which are really complex, and how to realize it, how to reduce the labor part of it, how flexible it is, whether we have to go faster way to adopt the design and deploy it to the applications. And we also think of it, is it a potentially scalable technology or not? And again, the most important today is key, whether the technology is meeting the green norms and norms. So therefore, what's happening, if you see all the points, probably additive manufacturing takes the lead and brings to the next level, and where we can work on, make the things to it. This is the primary definition. I'm not go to this. Yeah, advantages when we talk of this, because the challenges I threw, one of the major advantages when we say additive manufacturing is buzzword, complexity for free, simplification of part fitting because we use a non-contact type. Then we go for the mass customization. Every part can be different. That is the third advantage you can have. We can think of now integrated components. So you can have some sensors put into it, or you can think of using multi-material part of it. That is another part is material design freedom, which is possible, which was not done in the past. Logistic freedom, you can have a model, send it somewhere else, get it printed, brought it here. So, to again the I 4.0 compliant technology. And most important is that very good nesting can be done, which is not possible in conventionally. You can think of how these eight samples are placed together and built together. So that is the beauty of technology that we are talking here, just for the new guys who are here. Now, issue is when we talk of this technology, what is the global initiative across in this particular area? So all countries across the globe, and if you talk of India, we are having Make in India initiative. A lot of things are being done and pushed, and every country is coming up with their own ideas, and these things are taken to the next level. So if you see the initiative, and then we take up to the things to the level where things are standing in across the globe. If you talk of the aviation and automobile, we are somewhere here. System produce near production environment. We are here. In the tooling space and drone defense, we are pilot line capabilities already demonstrated, and we are a pretty good lead in the dental, medical instrumentation, implants, and artistics. That is the status today across the globe about the metal additive manufacturing. Now, when I talk of the global scenario, we also have to come down and see what are we doing in India. So in India, we have very nicely placed a national strategy for additive manufacturing, where they are targeting that by 2025 we should have a 5% global share, contributing $1 billion to GDP. 100 new startups, 10 AM sectors, 1 lakh new skilled manpower, and 50 technologies in material, machine process, and software. So this is the bit ambitious target, and definitely as a people who are leading the additive manufacturing domain, especially metal part, these are the target for us, and probably we all have to divide and see how can we achieve this and make it by 2025. So this is it. Now when I talk of the partners also, who are the companies working in this area, Kiran showed about the private players, and I'm trying to give a comprehensive, including the government side and the academic part. So if you see the private sectors, mostly on the plastic, some academic institutions are coming and joining with the laser-based additive manufacturing R&D. Metal machines are with the RRCAT, CMTI, ERCA, all these are the government institutes, some IT Kharagpur, IT Bombay, Kanpur, so many people. We have also many private players, Wipro 3D, Honeywell, 3D Incredible, Dentcare, GE, Objectify, L&T, they all have machines, many more are joining to this. Now issue is these machines are imported, either they are from EOS or SLM. Most of the machines are PBF machines, powder bed fusion machines. and few machines are, maybe one or two are from DED side. Now some companies, some institutions are making, developing these machines, and thus RRCAT, CMTI, IT Bombay, Hyderabad has come up, Jodhpur now has just declared, and private player also coming up, Intech and AMS. Now some startups are joining from RRCAT, they have license, and now 3 companies are again joining the race to make who can make the machines in India. So our endeavor is to start, I told you, from the system design development to material processing, material testing, quality validation. And since we have a chunk of students working with us, we are also have a good presence in the multiphysics modeling. So this is the whole area where RRCAT is focusing and working on it. We have developed both the technologies at RRCAT, DED and powder bed fusion, and these machines are already developed and working on it. And DED machines specifically started 2009 onwards, and 2014 onwards we are deploying at different components for the in department and in-house applications. Powder bed fusion machine, the first machine we built in 2015 for our internal usage, and now maybe in 1 year time again it will start commercialization of this machine into the Indian market. So this is the machine that we have, a powder bed fusion machine built here. We have already tried SS316L, 304, 625, Inconel 7, all these materials, and one machine we are already sending into BARC, and now technology transfer and incubation is again being initiated. So very soon we'll have this machine into the commercial domain. The direct energy machine depositions already there, like I told you, 2 kilowatt based machines is developed. Few components, a lot of materials have been tried and tested, and again these other recipes can also be developed on demand. And today is the one similar machines we have already supplying to BARC, and 3 industries are incubating this technology, and I'm happy to share that all these machines will be launched in December and January. These companies will be launching this. So again, there would be a big change in the scenario what we are talking in material manufacturing domain. We are not stopping here, because whenever we talk of here, we are always talking the volume of 400 by 400 or 250 by 250. Again, as Kiran identified, we need to have a component more than 1 meter in size or 2 meter in height. So we are also gearing for it. So here you see that presently we have 110 kilowatt fiber laser based additive manufacturing systems using a 1.6 meter diameter and 1.4 meter height. So that is the volume that we are targeting and making the things happen. And since we are in the machine development, we also thought of why should not we have something to deposit on the ID of the tube, because when you talk of the elbows and bends, many times we may choose some high performance material and deposit there, so that the whole component performance can be increased. So we built a special heads which can go inside the tube and do it. Presently anything which is more than any pipe having a size more than 45 millimeter, we can send our head and do it, and up to 2 meters we have already tried. We see the PBF system, we developed many components, and this is the sum of the features which are featuring here. When you try to build it, for example, every case has got its own story. For example, if you may try to make a gear with honeycomb structure, conventionally if you try to make it, probably it will take 3 days or 4 days to build it, and we built it in 7 hours. So the story trues here, whatever you are doing in days can be done in hours, and whatever you are doing in months can be done nowadays. So that is story here. So many things are done, and again all these components are first process is developed, then after the component is built, then their mission inspection is done, and whenever things are done, accordingly things are monitored. We are also going for making a smart component. For example, here we have now conformal cooling dies, and this you can have some sensor put into it, and you can think of having a control, how you can have control heating cycle and control cycling within the component itself. So that is again that one which will increase the production rate, and that will again make the and will be the true advantage of technology. So all these things are with the powder bed fusion. Another things that we did is in the powder bed fusion is one of the good technologies, mesh type spaces for BARC. Earlier they were making this component using EDM wire cut. So they used to take 5 working days to build 3 of this. So almost you can say 1.5 days for this. Now we do it in 2.5 hours. So that is this, and not only this part, but again when we talk to the designers over there, earlier they were just thinking of a circular shape because it was very convenient for them. But now since the technology has got more advanced, they are thinking, can we have some other flowery shape or something which can again strengthen the design and bring more freedom to the work. So they are working on it. Once it's finalized, probably we'll be helping in that also. So what I'm saying is, it's not only making the mesh component, but also sending the information, taking the confidence from the people on the other side, so that things can be taken to the next level of vision. Honeycomb geometry orifice. This is done for the IG car. Especially these are things are built. People have tried with many technologies like investment casting and JTAW and foreign. Though the component looks very simple and small in the size, but the challenge is with the making the ribs and the studs and making overhang, and those are the things which need to be very careful in bringing the dimension tolerances and planning how the supporting structures has to be done, so the thing comes and weld into this. All these are the challenges that we did, and things are done very nicely. Another application that we work for the high temperature reactor programs, and this particular we try to make a micro channel heat exchangers. So you have a very heat exchangers with the channel size of 2 millimeter by 3 millimeter and having a length almost 300 millimeter in the depth. So you can have so many channels made, and conventionally we cannot make it. Presently only one company in UK makes it, and they charge a lot of money for it. When I was told that 1 unit of 300 by 300 sent by that company costs around 50 lakhs rupees, and we tried to build and really estimated with our government rates, the price came out to be 6 lakhs rupees. So where is the 50 lakhs and where is the 6 lakhs, and that makes this. And not only that, it gives another confidence to the designer at our end, because they can know that whatever we can build, they can always go back and do the math to redesign the component and make the things to the next level. So that is the advantage of LDD technology that we have built, and all this technology will be used for many nuclear applications. One of the things is post Fukushima, they wanted to deposit silicon carbide on the zircaloy 4 tube, and here challenge is the tube thickness is 0.6 millimeter thick, 10 millimeter diameter, and we just try to do something, and you want to have a very thin deposit of 0.2 millimeter silicon carbide on it. So you think of it, 0.6 millimeter tube, you are depositing 0.2 millimeter of silicon carbide. We tried a lot of efforts were done, tricks were tried, how can we achieve it. Finally we could get very nice, you see how the silicon carbide has come, and very nice 0.4 millimeter very solid segment. So this already deposited. Now test trials and then tubes are given to the BRC for the further applications. When we talk of the different materials, so again the functionally graded material is always a challenge, and when we talk of the copper and stainless, it's always stainless steel is always thinking how to do it. So we tried to work on this, and we had SS and copper direct deposition once then we made also 50% and then 20% gradient. All these things were tried out with the machine, and we did all the colorization, and we found that this can be done. See, many times we say that whenever you are working with the copper, there is a lot of porosity comes at the interface. But here it's not to get discouraged when it comes. We have to find out where is the sweet spot. And it takes time, it takes energy, and people have to stand on the lab and think on those and put, scratch your head and think on those. Probably, that is a solution. And if in the first glance the thing doesn't happen, right away, really, but if you get that sweet spot catched, then things can be done, and we have achieved function grade materials into this part. Another application from the Cheers Institute, deposition of molybdenum on copper chromium zircaloy. This is done, and initially we started with a small piece, and now recently we have given them to IPR some 250 millimeter by 250 millimeter block of moly deposited on this, and we know that moly is not very friendly with the copper. Then again we deposited a very thin layer of the nickel, which is not possible in conventional process, and this is being done, and now very nice things have come out into this part. In another project with the IG car, we try to have how can you join to dissimilar material, for example SS304 with the Inconel 625, and especially this is very important when you are thinking of making a joint and go for a deformation of it. So we did a lot of co-deformity studies of two alloys like Inconel 625 and SS304, and very nice results have come. And to achieve uniformity, we did the gradient on this part. You see how beautiful the hardness is changing when you change the composition from one to another. So that sort of things we achieved in our bimetallic joints. Another application is also deposit tungsten carbide on SS, and this is for one applications. And here the basic challenge is if you talk of the absorption of 1.007 micron to the tungsten carbide is 70%, and the base material on which you want to deposit is 30%. So when you put the laser and you don't want tungsten carbide to be melted, and the material is taking maximum energy from this. So here comes the trick and how to play with the water flow rate and the process parameter so that your maximum power can go down, do the wetting of the surface, and then you can have very smooth deposition. So a lot of things were tried. We made a pretty large number. Around 450 pieces were built in this, and after that it is sent to the BRC and some other applications. So a lot of things being tried. Another is in deposition. One in applications, we also thought of why should not we try to work on ceramic deposition using DD, which is again a very good. So we worked on the albuna and we started depositing, and we found what is the thing, whether the porosity and other stuff. And many times, the process always prove our conviction as a wrong. I mean to say, we were thinking when you are working with the ceramic EL203, so the power requirement would be very high. Maybe I was thinking, maybe 1.8 kilowatt or something like that. But the reality is when we were working with the EL203, the power requirement came down very less. Up to 450 watt was enough to start the work, and here was the sweet spot. So that is the way things are, and it's already built and deposited. We also worked on the transition joint of stainless steel with the titanium. So many things are done, and it's not a single material, so many other materials for deposit so that we can have a very good strength. So idea is when we talk of the technology and especially metal additive manufacturing, we know that it is a very good solution for the customization, and it gives really very low cost, And when you want to try something, see whether things are going to do it. So we can apply not only for the prototyping but also for the production, and all these things are going to give you a very rapid stuff on this. Earlier there was a question that can we have a gradient of the different materials, specifically we talk of 2 material or 3 material or 4 materials, it's possible. And we can also have in situ, mixing of the material. Now the machines we built is having a on live, on site mixing and change of the composition. So that helps us, you can change the composition of the material on the fly. So that sort of advantage now we have, and it is really going to help us having generating very good gradient and making a complex 3D compositions. You can think of controlling the phases and grain sizes, because you can have some preheating stuff, or you can have some deposition strategies. So all these things are the key you have now, so that the things can be done and make on the other pattern. Now when we talk of all these things, again from the nuclear point of view, we can always think of performance enhancement, specifically from the radiation swelling point of view. How can you work on this and things can be done better? And how can we work on the energy consumption reduction? So these are the things that we have learned during the process, and how the thing can be done. Yes, there is a scope for a lot of things, because when we talk of the automations, definitely sophisticated in situ monitoring and feedback controls really required to have a reliability on the consistency of the process, because whenever there is a small change in a parameter anywhere in the process, then things try to be unstable. And today, since we have skilled people in the lab, they are able to fine tune it and bring it back. But again, you need to have some things that we are working on this, so things can be more reliable on this part. So if we divide the whole domain, I can divide it into the 9 parts. We have a machine and software development in one part, process development and control on the part, feedstock and development part. So these are the 9 domains on which the whole metal additive manufacturing is working across the world. And you see, our strength is probably all green things we are now good at. And wherever we have average presence, and this is where we have no presence. Really we have to work on. So up to the 1 part, 2 part, or maybe 5 part, we are able to have some quality control and assurance part. But when you talk about a large number of the components and all these things, again we have to think on this, and we need to work on it. Again, if we want this to be more more commercially viable or more attractive into the industries, we need to tackle all the 9 part on. One thing I have learned all this in this journey is, it's not important to build a machine. Probably more important to build or prove the application whenever we talk about the metal additive manufacturing, because the clients are not ready on the other side to adopt the things as it is. And specifically, whenever you are talking to change some in shape and design, they're more bothered about whether it will work or not. And that viability studies have to be shown and take to the next level, and which we need to work on. So thing is, we have a lot of challenges for the adoption of this technology into this. Now, if you talk of the international level, a lot of things are done. In India is also getting for it. We have done our job for the machine and a lot of things that we could do it. We also collaborated with a large number of institutions so that a really impact can be done and brought into it. And presently, if you talk of the challenges for the nuclear energy applications are unavailability of material, specifically refractory metals and ceramics, specifically the laser additive manufacturing. That is the biggest challenge. Now, if you talk of some alloys which are commercially available, people are ready to give. But whenever it comes to some material which are bit off the weight, again, you have to pursue a lot. One of the example I can share with you, we wanted to develop some process for a structural material, P91, one of the nuclear material. When we started talking with the powder vendors, they say that no, we cannot build 10 kg or 5 kg, they cannot give. Somehow we negotiated with them, we said, okay, if you give it, we'll buy 3 tons. Because finally, if you ask them to make some 100 kg, then after that, if composition is not good, that is not of use for us. So finally, they agreed. So what I'm saying, the volume specifically in the zone, wherever we have materials is one of the biggest challenge to us. There is a limited awareness, skilled manpower and expertise. There is a limitation on this, specifically with the customer end. When you talk of this, you go and talk to them, people may know what is the 3D printing and all this. But when it comes to apply on it, specifically in the strategic or nuclear area or maybe some plant where the access is not readily available, people are not ready to change it, and you have to really put a lot of effort to these are the game challenge on it, and really we have to work on. There's a problem with the material internal properties. Whenever we talk of the any person, especially the designers at Hall 7 or maybe the IGCAR or ADG people, they'll say whether the material is listed in section 3 or not. And if it is not, then they will probably, you have to really work on this and make the things different. So this is again a big challenge for us. And if whatever the materials are coming, what is the property would be there, because we have a different phases and how will we achieve it. Probably one thing we could convince to the people, if we are able to generate the similar microstructure and phases by post-processing, what they get with the conventional one, people are still accepting it. So again, so you have the two-step working. First is you do it with the additive manufacturing, and it proves the applications. If it works fine when the simulated load condition, if it is not, then you have to probably prove the material to bring it to the same level so things can be done into that level. So that is again a challenge. And this, there are standards available for the process qualification for the things which are popular, not for the things which are, suppose if we talk about anything which is relevant to the nuclear or any other applications which is the niche area. Presently there is no standard, and this is again a challenge. How to proceed ahead is the big bottleneck for us to it. Again, there are issues with the regulation and the licensing procedures, whatever we are doing, how to do it, and all these things. Again, whenever there will be a deployment, all these questions will be asked to us. And again, whenever we're talking of making a commercial product, how to go for the manufacturing it, what should be the criteria. So with this, what we want is we need to have a awareness program, countrywide initiative, leaving the comfort zone of each of us. National skill development program on additive manufacturing. A lot of things are being done, but still, all these things are in the silos. They need to have a, more collaboration among the people and the silos that we have, so that people come out of it and have a really national program on this. There should be a program on the knowledge and technology sharing mechanism for the faster commercialization, because what is happening, what mistake I did, probably somebody in the Bangalore or Coimbatore do the same. So we need to work on this. This again, some mechanism should be there. Especially when we talk of the nuclear component, design optimization has to be done. A specific additive manufacturing technology and equipment for the nuclear application has to run. Definitely R&D cannot be left right. A lot of things has to be done for the material and the material data development. We have to work on this part. And again, AI and ML, everybody talking of, then we need to have a feedback system so that all these things can be deployed. With this, I stop here. Again, regulation part, already I talk of it. Establishment of technology development, application demonstration. This is the most important part, because I'm not saying buying machine is not a difficult task. If people can buy and put it on this, but most important for anything to go into the field, you need to prove the application, whether it will work or not. So probably one of the advantage people have with the working with the national labs and for the handholding for a longer period, at least they are confident that some knowledge will be given to them. If there is some problem, you have experts at backhand who can support and bring the things to that level. So it's not buying and putting the machines on. If tomorrow machines started selling into India, it won't help us a lot. But application demonstration, people behind the machines who can prove the application, and if something goes wrong, they should be able to come with the solutions. So they need to have some technology development application demonstration centers. Definitely, lot of things we are talking of hybrid process. There is nothing on those part we are talking of individually, but no things we need to work on those part. Definitely, we need to work on the manufacturing chain, which is important. All these things are required to be established. This can be done on the individual level, or maybe this institutional level, or maybe the country level. Unless all these things address, metal additive manufacturing is not going to be a permit. With this, I just put the name of a lot of collaborators we have, and the team acknowledgement, our director, then our group director, and the team. We have pretty balanced team, students and the employees, so that a lot of things can come out of this. With this, I stop. Thank you very much.
Thank you. Okay, we just have time for one question. So,
One big question. How many times from your experience can we reuse powders?
This is a very tricky question. See, what we do is specifically for DD applications, we mix only 30% in one time, and 70% is the new one, and we cycle for the 3 times. So that's the way if you are using it. But if you're doing more than the property goes down, and we need to work. But again, it is established with our experience, and we tried it to do it, and it's working. Maybe for the nominal nickel alloys that we are nickel and Fe alloys that we are working, it works. It may not work for many alloys. Thank you, sir. Thank you, sir.
okay, the final speaker in this session is Professor Shobha Shukla from Department of Metallurgical Engineering and Material Science, IIT Indore, Mumbai. Sorry, she'll be talking. I'm sorry.
I thought I changed my institute.
Yeah, she'll be talking about direct laser lithography for 2D and 3D functional nanostructures.
वापस निकाल के लगा दीजिए. So I know you all must be waiting for your tea. I am standing between you and tea. And another different point that I have is I come from academia. So I'll give a little bit science gyan as well before I'll move towards the technology that we have developed in my lab at IIT Bombay. So today we are going to talk about these 2D as well as 3D pattern nanostructure using this. I would like to draw your attention to 2 other things that we have made, and you see the scale that we are talking about. Other people, the 3 talks before me, they were talking about the minimum feature size in this range. Here we are talking about entire thing in that range. So that is the scale we are talking about. Our national emblem here and our institute logo here. So I'm representing here Nanostructure Engineering and Modeling Lab. As you can see, this is where we strive for. We want to take ITB as well as to certain height wherever we can, and we are working on this 2-photon lithography primarily for all the fabrication related things, and then we are using it for as many applications as possible. I'm a trained photonics person, but when I joined IIT Bombay, I had a huge amount of interest in using something which can directly benefit to the society, not the indirect. Indirectly, we scientists, academicians, scientists in the national labs, we benefit to the society, but something which you see quickly get benefiting the society. That is how I started working on the water, because I had previous experience in the graphene, and when I came back to India, I thought many people were interested in graphene, so we started working on this material and use this for initial part, and then I combine this as well. So now this circularity has been complete even in the science term as well. I'm very thankful to all the funding agency for generously funding my dream to make this possible. The work that I'm going to present is specifically the photonics part is done by the student in the circle. This is slightly old photo, but would work for me. So this is how actually my femtosecond laser assisted photolithography work. I'll just give, this is more of a snapshot of everything that we are doing. I'll tell you how it works in a couple of slides later. These are the few applications that we are utilizing. As you can see, some of the structures are not really passive, they are active structures as well. This very well known chiral structure, metamaterial structure that some people might already be knowing. We made some of these structures which are like micro QR code, very tiny one, mostly for anti-counterfeit application. So this can be active, this can be passive, depending on the need. This is mostly utilized for the ICs, but depending on who wants to use where. Three-dimensional photonic crystals, plasmonic crystals, and so and so. So not only passive, we make optically active structure, even multifunctional structure, where the dimensions that we are typically, we know about X, Y, and Z space. You can introduce other dimensions responsive to the temperature. We as a human body, we are multimodal, right? We respond to temperature, we respond to pressure. We can see, we can sense, we can taste, we can hear. So that is the kind of functionality if we can bring to the structure. That is the smart structure. That is actually the goal of any of the engineer's dream or scientist's dream. I think the boundaries are very blurred. So I would not like to call myself as an engineer or myself as a scientist, somewhere in between. At least I lie. So this is going to be the outline. Since I would like to finish by 4:20 at max, I would request Chair to just give me a hands up around 20 minutes later. I'll just try to wrap up wherever I'll be. So this is how I'll proceed. Why the need is there, which I think you all are already aware of all those things. So I'll very quickly cover these two parts and then move towards the kind of thing that I wanted to show you, the kind of strength that we have developed over the period of time. This is a very famous line. Anyone can identify. Front row chhod ke. I know front people are Richard Feynman. Yes, somebody already said it. Such a visionary in 1970s, right? Early, actually before that. He said something, and we have already, it took us 30 years to visualize whatever the challenge that he had posed and the kind of award that he had raised for that. But then here we are, and now already the Moore's law, the people who are into the semiconductor industry are already be aware of the Moore's law, right? It's broken or not broken. Intel claims it's not broken. In principle, it has already been broken long back, but we are still making sure in terms of stitching, quad core, different types of stacking things that we still keep on increasing the computation power. Eventually, it will not be sufficient. We have to go into the third dimension in terms of the interconnects. We are already using some technology that is in there, but the additive manufacturing will play a huge role over there. This is something which I very strongly believe in next 10 years, your computing will not be only dependent on the electron movement, but the photon based technology will be the reality. So plenty of room at the bottom means more opportunity. So that means everything will get smaller, you have to get 3D interconnects, transistor will increase, and these are like various newer applications that will emerge out of it. So standard technology that people use for these kind of small scale fabrications are these. So these are the top down approaches, these are the bottom up approaches. They all have their own limitations. Mostly these are fairly slow, fairly small throughput. These are even slower because this is how bottom up approach is a nature's way of building things. Nature's way of building thing is it will make most beautiful structure, but it will take years altogether, right? Caves takes centuries to get built. We don't have that time. We are impatient people. So how do we do it? So the proposal that we have come up with something use a combinatorial approach where we can utilize the strength of the bottom up and utilize the strength of the top down approach and make something very beautiful, the kind of thing that we have already talked about earlier. We have heard the initial speakers, the additive manufacturing. So it's the marriage of the nanotechnology and photonics that we are doing. So photons earlier people were also using, but we want to do it at the nanoscale, and it can give rise to so many applications. So opportunities are enormous. So some of the applications that I want to cover are but before I go towards that, I just wanted to tell you about the colors in the origin. Colors in the nature are not really based on the pigments on dyes. Typically when I give this lecture, it is typically like for the communication or the kind of conversation that I would like to have with audience, but in the benefit of time, I'll skip all those things. So these are all structured material. There is no pigment in there. So these are based on the patterning at the micro scale or nano scale, depending on the whatever the thing that I want to do. But the problem here is it's a nature's way. We are trying to use it and make something along that line. But nature is not only making something which is a passive. Nature makes something which is active, which can change itself and merge with the environment. And that is the most of the difference need that is moving towards. Whether we are talking about the optical one, which is shown here, it can be infrared or the microwave or any other range, and that can also be achieved only with the additive manufacturing. There is no other technology which can provide these solutions. This is another nature-inspired electronics. I'll not go into it. You might already be aware the moth eye and this strain-inspired changes. So how to do it? This is what I was talking about, the Moore's law. We know the number of the transistors are increasing, but if you see the performance and the frequency, power, these are all tapered off long back. So somewhere around early 2000, Moore's law has already been broken. It's just we have the Intel had determination that okay, Moore's name has to go. So something like that, we just kept on moving, and we are still working towards it. But this is something which has already come across. We have already reached to that level, and that is how we will have to come up with the photon-based solutions. So writing micron or smaller structure is what is needed for having any kind of color changing material or a strain sensing material, even for any of the therapeutic or the health related application. That is what is needed, including the semiconductor one. Then writing 2D, 3D, flexible, multimodal patterning, large area, low cost. The solution is definitely a combinatorial approach where you are building things from the bottom, but you have a very good control using photons. Surveillance structure, 2D, 3D structures, on whatever that cannot provide. Along with that, the large area, low cost, scalable, one-step, facile, and aggregation. So how do we do it? It's the science of high intensity beams. Let's take it as simple as that. So if you have something which is very intense, and the material is not absorbing in that range. So then what would happen? If the material is not going to absorb in that range, you can go inside the material and make whatever you want. Wherever you will move the beam, it will follow the path. And that is what has happened here. You have grating, you have mesh, you just imagine it. Limitation is your imagination, limitation is not with the technology that we are talking about here. It doesn't come at low cost, it's a lot of work, but let's go one by one. So this is how actually it works. You have a linear absorption. That means a material, typically all the materials have certain absorption window. So if a material is going to absorb in that particular window, the absorption is going to go, material is going to go linearly in this range. But if I have something where the material is not absorbing, so there the non-linear effect comes into the picture. So in the non-linear effect will only take place, it's like a Chi-3 phenomena. So I'll not go into the details of how it works. So just trust me on that, it's a phenomena where the intensity of the beam is very large, then only material is going to respond to it. Otherwise material will see it as nothing is passing through. And that is what will happen here. Okay, this video has already run, so let me. So wherever in the blob of material, the light will shine, that path will be traced, rest of the material will remain jelly or any kind of thing that you are keeping it. So more or less like what previous speakers have been talking about the powder bed, but in the powder bed you were talking about at the surface only. But here you can go inside the powder bed, and wherever that light will be intense enough, that will be solidified. People who work on the stereolithography, they will find analogy here. I don't know how many people are aware of it, so I'll just skip that part as of now. So this is simple schematic of the system that we are working on. So we have a kind of a composite system. It can be simple photopolymer, it can be a composite one. You with bunch of optics, you will focus the light, and you can make structure as small as lambda by 8. So typically we are writing with 800 nanometer, and we can focus the light to very small area, and you just see the finish. You just look, there is no undulation that we are talking about. It's a very fine things that we can make. Actually, the roughness is of the order of nanometers. So with the nanometer roughness, very large area, we can make really good structures, even three-dimensional structures. So this is how actually a real system looks like. The previous was the simplified picture. In the reality, it's slightly more complex. We have developed it in-house. It took us a couple of years to develop this system, automate this system. We develop our own material system as well. So it's an entirely in-house, literal make in India kind of a system and the technology that we have developed here. And this one, if you see, these are hanging ropes. So there are, especially varying kind of a photonic crystal, if you see in the zoomed in. So there are ropes below these things. So it's a freestanding kind of a cube we can make, the pyramid. And then with this kind of strength, okay, before I go into the how different application works out, let me tell you how actually it works. So it's more like kind of a relay race. So one material, so you have a photon that comes onto the material system. This electron gets excited, but before this electron goes down, another photon comes. So it's a kind of a relay race. You are passing the baton, and then it goes to the other one, and that starts the polymerization process. So, and that is how it goes on. So this is more of a microscopic picture or the atomic scale picture. In the reality, if you look at the macroscopic picture, wherever you are shining your light, that part will get polymerized and the rest of the part will remain the kind of jelly it was. So you are shining the light, that got polymerized, wherever you are not shining will remain unchanged, and that is how you will just keep on writing the structure. This is a video of how the real-time writing takes place. So it's a three-dimensional pyramid structure that we are showing here. So it's a entire blob is there. We don't put lots of material. We just put a small 100 microliter. So the kind of story that Dr. Paul was telling, we never bought the material. We got this because we just wanted. No? Oh. Okay, I'll come little bit.
Can use this one.
Sure. Am I audible now? Okay, wonderful. Thank you. So this is a small, so what I did was I called this supplier, and he said he wants to sell the entire trunk or the bucket of the system. So 20 liters was the minimum amount that he wanted to sell. And I did not have that kind of a need. So I asked him, okay, send me sample. So he sent me half-liter sample that I'm using from last 10 years. So no need of buying anything, and that is how science works. So I shouldn't be telling this in this area, in this room, but that is what you need, very tiny amount, right? And then eventually, because we are talking about nanoscale fabrication and that. So now, as I mentioned earlier, we are not really talking about the passive. We work on the like any epoxy acrylate, ceramic, graphene oxide. So it's more like a story of the three little pigs. So in the three little pigs, you like three. I'm sure the people who have kids already know. The people who have, I think it's okay. Oh, sure. Thank you. So the first pig makes a small straw house, and then wolf comes and says, "I'll puff you, and blow your house away," right? And then the second pig makes a better house, and then again wolf comes and says, "I'll puff, and your house will be blown away." And then the third one makes the best house. The similar kind of story here. We can say first we made the dye-less system because the dye was expensive. And industry people said, no, it's not, when it's expensive, then technology will not move forward. We made dye-less. No, this is also not good enough. Make a functional structure. So we moved towards functional one. Then again we got, no, ceramic is the thing to go because semiconductor mission has come and the ceramic patterning is important. So we moved towards ceramic. And recently now people are talking about you work with graphene. So why don't you work with graphene system, and that is what we have been doing. So wolf keeps on coming and pigs keep on working. That is what has been happening here. Lots of application, lots of things. This is a spatial grating. Very fine, very nice finish. This is a very old picture, but still you can see that we can work on it. These are the functional micro needles, rather nano needles, because the tip is of the order of 200 nanometers or so. The base is roughly around few microns. And you just like, that's what I said, you just think of a structure, make a CAD file, and we can make it. I'll skip this part. So this is a zoomed in image of the needles. We made some bridges and to show the kind of, this is the bottom, this is how the tops look like. You cannot distinguish, that's why the three-dimensional imaging has to be performed. This is, you can make tapered, you can make hollow. So hollow is not easy to visualize using the confocal system. So we did SEM of that. I'll show you maybe a little bit later. This is to show a high throughput of the system, few mm by few mm kind of structure that we have made. To showcase the strength. We can make anything. You talk about the fixed spacing there. That means the purity of the color that you will be having. You want variable, we can make variable chiral structures. To show again the kind of quality, we always make the diffraction pattern. We always take the diffraction pattern because SEM or TEM, you are only looking at the few hundreds of micron by hundreds of micron. Whereas in this one, you are shining light on the entire mm by mm kind of a structure. So this is what I was talking about, the hollow needle, the full needle that I had shown earlier. So these are the kind of a hollow needle for the therapeutic application. This is a mosquito nose, micro ring resonator. So any type of structure that you want to utilize for any application, that we would be able to make it. These are few of the applications that we are currently exploring. Metamaterials. I will just show some of the applications. Whatever I can cover in next, I believe 5 minutes are left for me. So in those one, so I think I have some small video on this one because this typically people like better. So it's a fluorescent QR code that is hidden below the non-fluorescent QR. So multi-material kind of a printing. So you have a material that is written here, and then it's a very tiny, small 50 micron by 50 micron, and on top of it, you can put another bigger micro QR code, which anybody can scan, can do it. But this is very important for the any counterfeit application, specifically where the reliability is a huge problem, like kind of a defense of the space application. So then you can have, you can see the shroud, actually that way you can identify something is hidden below. And even those lines that you are seeing, these are not these like kind continuous line. You cannot counterfeit because we can even control whether they will be pillar or they will be merged. So any QR code that we will be making this way, we will have a very good control over the system. So there are another application that we tried was the microsensor for near real-time monitoring of the heavy metals. We have made microsensors for all the heavy metals that are commonly a threat for the human being, whether it's a lead, arsenic, mercury, and so and so. Okay, so yeah, here actually what you are seeing is just the robotic arm dropping all the samples, and then you can see it moving and wherever. So entire like 1 inch by 1 inch, you can do close to thousands of tests, and thousands of tests not because of the sensor. I cannot make it smaller. It is because of the cage that is going to hold this 50 microliter of the water sample. So here the water sample requirement has come down. You can take the aliquot from any running line, any industry, and you can continuously monitor anything. So this is to show the methyl arsenide, so basically which is an organic arsenic that is the most difficult one to detect. So there is another day will be when you are more interested in the water related technology. I'll be very happy to discuss the kind of different water technologies that we have developed. This is something for the fentanyl. Fentanyl has recently been put on a regular sale, and US has declared this as an epidemic. Lots of death, even in India. I'm sure you all, at least young generation, has seen Urta Punjab. So something along that line. So narcotics detection is very important. Why? Because if you will not provide the antidote within few minutes or whenever it's a threat, the person will die, and that is what has been happening. So in this one, the limit for the detection is fairly low. We are talking about, typically it becomes dangerous when we are talking about the 20,000 kind of a ppm level. So we can make very long needles. So this is like almost like a 800 micrometer long and 200 nanometer tip. So you can do anything with that. We can do lots of processing, and we have performed very rigorous testing for these kind of sensing. This is a 2D picture of the same thing. This is how so basically we are using femtosecond lithography for the mold making. After that, we just replicate it on a different polymer substrate, and we can functionalize, we can add different kind of ligands or whatever the active groups that is required. So these are a few different applications that we are exploring. The top one are the one that we are exploring extensively, and the other one is not. So my major funding is coming from the water center. So I have to run this video where I have compiled all the technologies that we have developed for the water related technologies, and with that will be my last slide. But yeah, my recommendation slide sans that. So here we just, because the audio is not coming, I have to say it. There is some voice. I don't know how to increase it. So this is a graphene based filter for the dye purification. There is even a dye sensor that we have developed. So all the things that we are showing here have been developed by us, including the electronics part. These are the electrospun membrane as well as the solution casted membrane for oil, water, or the water oil kind of a separation. So the oil is in the water or the water is in the oil, that kind of separation. So either water can be standing or the oil can be standing. So we have, this is a standard 3D printed system that we have used. So these are for the continuous emulsified oil separation, because industry is not interested in the floating oil. They are more interested in the emulsified oil, and that is why we developed this kind of a magic foam as well. That is again a kind of graphene foam. We developed even a conveyor belt based on that, so, which is only going to absorb oil, very selective, super hydrophobic graphene foam that we have made. We then developed electronics for it. It's a GPS enabled, IoT enabled camera. This is a real feed from the camera that of the skimmer that we have developed. As you will see, it will only absorb oil, no water, and very selective. It will drag it, and then later you can recover the oil or any other thing that you want to it. So it's a recovered oil that you have got it, and then you can use it for any other things. So heavy metal sensor, as I mentioned, we have developed the strip-based sensor as well as the micro sensors that I had shown earlier. Micro sensor is based on the 2-photon lithography, whereas these are strip-based sensors, so simple spin coating. You just have a cage, you just put this material system, and it's a PPB level detection. So mercury is a huge problem for many industries, and specifically the people who are into the export of any of the chemical thing. These kind of testings becomes very important, and typically extremely expensive testing of the mercury or the lead. And that is the industry standard that one has to follow. Currently, single test costs 5,000 rupees, whereas in this case, the strip cost is 300 rupees. And this is a solar thermal desalination unit, so you can have, so we have utilized even graphene foam for all these applications, but maybe for some other day. This is the latest group picture of my group. I have a small daughter, which is here, and son, I think he's the taking picture. So I have been asked like all other speakers, but I think most of the things have already been discussed. I very firmly believe, I think Professor Paul resonated more with what I have also proposed, which is a very good thing that we who are working in this field are thinking along the same line, that we have to have some industry standards for 3D printing. Because nanoscale, microscale, when we don't know what we are talking about, what kind of finish, what kind of technology that has to come in. Other thing is sustainable printing and disposal of the byproduct. The last question that you asked to Professor Paul. So how are we going to dispose of? These are highly active material and expensive as well. So we have to have some sustainable practices for these things. We have to have an industry specific roadmap, because additive manufacturing is not going to be limited to one particular material system. So it will go to the metal, it will go to the polymer, it will go to the ceramic, and it will impact all the kinds of things that we are aware of. Houses are built using additive manufacturing, your laptop will be built using additive manufacturing, everything. So, but that same kind of norms will not be applicable over there. So we have to develop these things. Also, we have to incentivize in-house development of the hardware as well as the software, which is extremely important. Because whenever we are talking about that We can always import, definitely the kind of 3D printers that we are talking about. $100, you can get a basic plastic fiber fed 3D printer. But if somebody has to develop it here, it's going to be expensive. So some incentivization has to be there for that. We cannot get rid of the AIML. So it has to be integrated specifically for stitching errors, specifically for machine errors. So that thing has to be covered using this AIML, and that as well as the predictive failure thing. This thing, multi-material printing, is going to hold the future, and that is what is my submission to this presentation. With that, I'll stop. This is our own micro chest that we have made using photolithography in the free time. We do all sort of things along with the diffraction pattern. Thank you very much. I'll be happy to answer.
Thank you. Any questions?
I was very clear.
Yeah, you were actually. Not. Okay, thanks.
Yes, I will. Let's also thank our session chair for chairing this session. And I request Dr. Nakhe, Director RRCAT, to present the memento to the session chair.
Thank you so much.
Thank you very much. My request to all of you is to have a quick tea and assemble at maybe at 4:50 in the main auditorium for the plenary session.
उसी पर हाँ वो एंड कर दो हाँ एग्जिट कर दो हाँ पूरा हाँ एंड कंफर्म कर रहा हूँ कंफर्म कर दो हाँ कंफर्म कर रहा हूँ हाँ अंदर से जाके करूँ क्या हाँ मैं दे दो ना इसको 2 मिनट के लिए निशांत
Usually make a presentation at 11, but surprisingly, this time you made I completed them so good. Because game भी था हमारा I'm making entry for me. नहीं चलेगा भाई क्या करते रहते हैं केबल में चल रहा है ओह ये इंक्यूबेशन भी चल रहा है प्रिंस केबल में चल रहा है तो इंक्यूबेशन बहुत पहले प्रिंस केबल डिस्कवर किया था
दोनों ऑन होने चाहिए, ठीक है, माइक इज ऑन।
Good afternoon. Welcome to the third plenary session of Engineers Conclave 2023. In this session, we'll have a plenary talk by Dr. Shankar V. Nakhe, Director of RRCAT. The talk is on lasers for engineering applications, the journey so far and the avenues ahead. To chair this session, I request Dr. Sanak Mishra, past President INAE, to please come onto the dais. I also request Dr. Nakhe to please accompany.
Hello.
Dr. Sanak Mishra, the former president of Indian National Academy of Engineering and of the Indian Institute of Metals, and a former member of the board of the Nuclear Fuels Complex. He is currently the member of the Governing Council of the Steel Research and Technology Mission of India. He is recipient of Distinguished Alumnus Award from the Indian Institute of Science, where he had secured BE degree in 1968, and also from University of Illinois, USA, where he had secured MS degree in 1970 and PhD degree in 1973. He is credited with the discovery of magnetic clusters in micromagnetic spin glasses systems through experimental susceptibility data which he generated at and below liquid helium temperatures. He is also separately credited with the discovery of texture memory effects in steel. One of the top metallurgists of the country and an icon in the steel sector, in 2018, he was conferred the Lifetime Achievement Award of the Ministry of Steel, Government of India. Earlier, he had received the National Metallurgist Award in 2003 and Metallurgist of the Year Award 1988. He was recipient of the Platinum Medal of the Indian Institute of Metals in 2011 and JRD Tata Award for Excellence in Corporate Leadership in 2012. Dr. Sanak Mishra is Fellow of the Indian National Academy of Engineering, National Academy of Sciences India, Computer Society of India, Institute of Directors, All India Management Association, Institute of Engineers India, Indian Institute of Metals, and an elected member of the Asia Pacific Academy of Materials. With this word, sir, I hand over the session to you.
Thank you. Thank you very much. Yeah, right. Your topic is. This is a plenary talk by Dr. Shankar V. Nakhe, who is actually the director of the Raja Ramana Center for Advanced Technology, where we are sitting here. And of course, he has played a very key role in organizing this particular convention. And so I will just briefly introduce him. And what's going to talk about is lasers for engineering applications, journey so far, and avenues ahead. Dr. Nakhe had BE Electrical Engineering degree, and then he had an MS Engineering Sciences degree from IISc Bangalore. So we share something in common. Both of us are alumni of the Institute of Science. Yeah, right. And then he received a PhD, honorary PhD from the Oriental University. And the areas of work are design, development, utilization of various laser and electronic systems. And at RRCHE, that is this particular center, he has developed various laser and electronic systems. Many laser and photonic systems developed under his leadership are being used at various institutions in India. He played a key role in the development of fiber Bragg grating inscription facility at CAT. This unique facility is being used for the development of specialized sensors for niche application areas of temperature and strain measurement. He played a pivotal role in the transfer of technologies developed at this center, and he also took a leadership role in setting up incubation center at the center. He has served as the president of the Indian Laser Association, has authored or co-authored about 70 peer-reviewed journal papers and about 140 conference papers. And I think I should add that, this afternoon, some of us had the pleasure of visiting the center, particularly saw the synchrotron and also went to the some of the laser buildings. So it's very impressive. And your leadership, has played a key role in the growth and evolution of this center. So my personal congratulations to you and look forward to your talk. Yeah.
Hello. My seniors here, thank you for your guidance throughout my career, and I'll give brief introduction of activities here. I will not talk of other programs of center. I'll concentrate only on lasers, and that too particularly related to the engineering applications. And this is the work of large dedicated team members that are contributing with me in developing and taking the program ahead, along with other support activities that are going on here. So those who are new here, I'll give just a brief introduction. Department Raja Ramanna Center for Advanced Technology is Department of Atomic Energy Unit with thrust areas in the lasers and particle accelerators and related technologies. As you know, this with these lasers and particle accelerators, these are multidisciplinary areas where we require state-of-art power supplies, RF systems, vacuum, and cryogenics technologies. And all these have their own spin-offs and have their societal applications. And RRCAT is working with the motto that photons serving the mankind through science and technology. And we are working with this motto and trying to take our lab developments to the land and utilize it. And as on date, the center has the distinction where maximum variety of indigenously laser systems are developed and also deployed in the country. So this is my plan of presentation. I'll give very few basics of laser because some of here may be new to this area. Then laser systems developed at RRCAT, some selected applications, international scenario, and way ahead in the form of some recommendations from my side. So this is basic laser action, and I'm showing here because it will give many more clarifications subsequently. We have a gain medium, that is the laser medium by which the laser is named normally, as we know, diode laser or CO2 laser, like that. This is the gain medium. Then we excite the material, so that is the atoms that are at the ground state gets excited to the upper level, and when they come back, there is a stimulated emission, and that is with an optical resonator, it is harnessed as a laser from this system. So we have gain medium, pumping mechanism, resonator, and control on this to get the laser output. And this is the reflectivity of the mirror. This is gain of the medium. There are certain losses, and this is the length of the lasing medium. If this product goes 1 or above, we have amplification in the medium and we get laser. And this is the only equation I'm going to show. We'll proceed further. So what is difference between laser and normal light? Again, I'll give only 4 major characteristics. One, it is monochromatic. As we see from torch or any ordinary light, there are multiple wavelengths that are coming. Laser is normally monochromatic. There are some tunable lasers. Then it is a coherent. So there is all radiations that are in perfectly aligned or they are in phase. It has low divergence, so that once the beam comes out of the laser source like this, it is perfectly directional. Of course, there are some diffraction limit is there and the beam will diverge, but otherwise it is in moving with low divergence. I would like to add here that lasers from Earth are sent to Moon, and there are reflectors from where the signals are received back. So this is the distance, and that can be covered with the laser beam. And if you see the torch at the end of 10 feet wall, it covers full wall. That is not possible. And this is another very specific point I'm going to highlight here, temporal intensity control, because as we are controlling the pumping mechanism here, we can have very narrow pulses from femtoseconds to continuous wave, and any modulation on this intensity is also possible. Even there is a polarization control is possible. So there are so many controls are possible on the laser's output as a light, and which has its own dedicated applications because of these properties. So this makes laser and normal light differentiated. And these are the, as stated earlier, there are laser medium, different gain mediums are there. So we can have gas-based lasers, liquid, solid, and plasma. So, and there are some other materials which we normally refer as metal vapor. Then there are semiconductor diode lasers, fiber lasers, and even free electron lasers are there. So RRCAT has worked on all these laser mediums, and we have in-house developed lasers on all these laser medium. Then there are different pumping methods are there. So there are optical pumping as indicated earlier. So these fiber lasers are pumped by diode lasers. There are dye lasers are there, tunable dye lasers. They are again pumped by other lasers. There can be pumping by electrical discharge. Most of the gas discharge lasers are pumped by electrical discharge. There can be chemical pumping. There can be thermal pumping also. These are called gas dynamic lasers. And very high power CO2 lasers were developed once using this gas dynamic principle. And there can be injection current, which is a phenomena in pumping diode lasers. So this gives the basic idea of laser systems, its nomenclature, pumping, and how to proceed further. So I'll give some of the highlighted developments that are carried out at RRCAT during this last period of around 30 years. So I'm highlighting only the end of the product. So there are many other intermediate developments that I'll just mention those, but I'll introduce the only highlighted systems here. So this is a 20 kilowatt average power CO2 laser developed around 20 years back. So this at that time was the highest power laser, CO2 laser in the country at that time. And this chamber is almost 5 feet, more than 5 feet high. So one can walk into the laser assembly here and all mechanisms were inside. Of course, before that, we have a 100-watt laser, 500-watt laser, 1 kilowatt, 2 kilowatt. This laser also has been developed here. This has been used for many material processing applications, and including cutting and some of the welding applications. This is another laser. This is called as a pulse CO2 laser. This is used for bend stripping application. This is a transversely excited atmospheric pressure CO2 laser. The earlier laser shown was a continuous wave laser, but this is pulse laser operating at around 200 Hertz with pulse energy of 1 joule. And this has been integrated with robot, and it has been used for bend stripping application. And this is particularly required for stripping applications where these radioactive materials are there, and those are to be taken out without any contamination to the atmosphere. So the contamination that is getting collected can be properly disposed of subsequently. So this laser has been supplied Tarapur facility for their testings. We have line tunable CO2 laser. Normally, as I said earlier, each laser has a fixed wavelength, but there are certain laser media where the wavelength can be tuned. And the CO2 laser is one such laser. Of course, it is most probably used at 10.6 micron for maximum power applications, but there are other laser lines that are possible which can be excited, and we have developed that expertise also. And this laser has been used for laser isotope separation of carbon. So C13 separation, this laser has been given to BRC. Earlier, this laser was getting imported from South Africa. There was no technology, but ARAC had developed this laser and given to BRC. We have worked on other gas lasers also. This is one laser. This is a nitrogen laser, and this is at that time the smallest nitrogen laser in the world, which was used for TB treatment application also. So this has whereas there is a drug resistant TB is there, and there was some treatment was devised, and this laser was utilized for that. This is excimer laser, and this is a very special laser which gives output in the UV range, and this output, there are multiple gases, argon fluoride, krypton chloride, etc. And wavelengths are different for different gas mixtures. And being in UV and very high quality beam, this is used in lithographic applications. So this is, I had a here that although we have developed this laser, but all the lasers commercially used in India today are imported. So although we have developed to a certain level, but we could not go to the application level, particularly for this, because there are some critical imported components are there. Next. So this is another gas laser. We have RF excited CO2 laser. So earlier the laser systems were either pulsed or DC pumped, but subsequently to make those compact, RF power supplies came up, and these are the compact systems where 2 kilowatt system is there. Otherwise, earlier the system used to be almost 4 to 5 times having higher volume than this. So we have developed this RF excited lasers subsequently, which has been used in many applications. This is another laser that we have used, developed here. This is a copper vapor laser pump dye laser. As stated earlier, these dye lasers are liquid lasers where rhodamin 6G and other dyes are flowing into a liquid media, and that laser is pumped by another laser that is pumped, developed at here, that is called as a copper vapor laser, which is a metal vapor laser. Again, a high-end technology. This laser was denied to India, and this was very much required for laser isotope separation program. And we developed many such lasers, copper lasers, dye lasers, and these lasers were supplied to BRC, and they are utilized extensively for studies in this area. So this is the copper vapor laser. It has two wavelengths, 510 nanometers and 578 nanometers, one in green and one in yellow, and both these wavelengths are used there. Although this was tried earlier for uranium isotope separation, but because of economy reasons, we have stopped that activity subsequently. But now it has been used extensively and very appropriately for medical application of lutetium-177 production, and the isotope generated where this laser system has been used and subsequently processed at BRC by other nuclear techniques has been injected into around more than 500 patients. So it is not that it is a lab thing only, it has gone up to the patients, and that is the big advantage of combined efforts of RRCAT, BRC, BRIT to take this level and this science and technology ahead for the societal applications. Another laser is ND-YAG laser. This is now a workhorse for most of the industrial applications. Of course, there is fiber laser is also coming, but particularly for welding applications where there is a need of very high pulse power, we go for this laser. And this is one of the highest power that we have developed, 1.5 kilowatt and 30 kilowatt of peak power. So Of course, beam quality is not very high here, but that is good enough for many applications. And such lasers we have used for many NPCL applications, that is NMOS coolant channel replacement, some critical welding and cutting applications. I'll come to those later. We have worked on glass lasers also, ND glass lasers. And at early days, we started with a vision or say dream of having laser fusion activity also here, but soon we realized that it is a two-fetched dream, and we stop in between that pursuing fusion activity, but we are pursuing high energy laser program as such because it has many other applications, particularly for Department of Atomic Energy. So this laser facility has given earlier 100 joule energy per pulse, and it has been used for certain equation of state studies. And now we are the bottleneck here was the laser glass. So that was not available in India. Earlier we had some Japanese and Russian glasses with which this we had demonstrated, but we are now developing this laser glass with CGCRI. They have come to a certain level, but we have to go ahead. The certain further improvements in the laser glass are required, with which then we can move ahead. But now the configurations are changed. We'll not go into the rod-based system. We'll now go into the disc-based system. And we are going to follow this program because this is a very crucial program for India's strategic activities also in long-term basis. So we have very small lasers. We are having diode lasers, which can sit hundreds of lasers on your finger. And we had this large laser, which is almost occupying a basketball stadium. And this is only laser activity, and there is a almost equivalent room below which is having the power supply. So we have very small to very large systems, and all laser media we have tried, and we have expertise in that. We have gone into the diode pump lasers also. We are having diode pumped YAG laser, and this is a pulse laser which we have developed again for the laser isotope separation program. And this gives pulse laser. It is a replacement of copper vapor laser because copper vapor laser is a bulky system and it's not energy efficient. So this is a very efficient laser, and we have developed. Again, this laser was denied to India. We developed it here in RRCAT, and we are giving it to. And this is for industrial applications, ND YAG lasers, continuous high power laser. We are working in the area of fiber lasers also because these are required in, this is the laser that will be used now in the applications that are going to come. CGCR has also developed 1 kilowatt laser with their fiber. We are also interacting with CGCRI, and these fibers are taken ultimately by Sajanan Laser Technologies. They are also coming with their own models of this, but we have all our technology developed here in-house except for these fibers and the pumping diodes. But now we have all control on these parameters and thorough understanding of this system. So we are not only gone into the CW fiber lasers, but we have gone into narrow pulsed, high repetition rate, and where the pulse shape can be modulated as we desire. So that is the expertise that we have achieved. This laser has been used again for many welding and cutting applications. Next. So the earlier fiber laser shown was a lab model, but we have gone into the engineering model subsequently. So our engineering models are following the lab model. So we have 250 watt engineer model. This we have given to the NPCI sites. So these lasers are working at site. And the advantage here is that since the mirrors are integrated part of the fiber itself, there is no problem of misalignment. Otherwise, laser alignment is an issue in the field. But these being fiber lasers, there is no problem of alignment. These are very rugged system for use in the field applications. So we had given this 250 watt laser in the field application. It is working very fine. We had gone with 500 watt fiber laser, again engineered model, and will come with engineered models of next lasers also. And this is a plasma laser in which we are generating argon plasma, and this is pumped by a very high voltage source around 200 kV. And gives X-ray output 46.7 nanometer. So this is a plasma laser that we are having. And to complete the spectrum of the lasers, I'm showing this free electron laser. This is a combination of accelerator and laser, because here the electrons are free, they are not bound, and the high energy beam is coming, and that beam, when it turns, it gives radiation, and that radiation is harnessed with mirror at the end, and that optical radiation builds, electron beam is dumped, and we get a tunable radiation from these sources. So they are continuously tunable lasers from 12 to now we have gone up to 50 microns. So the wavelength can be continuously tuned here, and they are very narrow, high power lasers. Although of average power is low here, it is in the range of milliwatts, but the peak powers of tens of kilowatt or 100 kilowatt range. So they augment very well our synchrotron facility in this IR regime. So there are many interesting studies, those can be taken up by utilizing this IRFEL. And this is the only IRFEL facility that is operating in country. And this is designed, and most of the parts are developed here. Next. So I'll just list out some of the applications that we are doing, and I'll show some of them. So we are doing on-site remote cutting applications for nuclear reactors, because this nuclear reactor, the channels, coolant channels, they had a definite life, and after life they have to be replaced. And the life of a reactor is much longer as compared to the life of the channels. And if we replace those in time, the reactor life can be. But replacing those coolant channels is not an easy task. Earlier that was done manually, and that used to take around 40 to 50 days of downtime during the reactor's shutdown period. So after say 1 year, 1 or 1.5 years time, when reactor has to be shut down for routine maintenance, and that used to take around 40 to 50 days time just because of replacing these coolant channels. And when these laser-based systems are deployed, that job can be done in a 7 days time. So it is net recovery of those many working days, and each reactor gives typically more than 1 crore revenue to NPCIL. So if we are reducing the downtime, definitely there is lot of earning. And more than that, what we call as the exposure to the workmen. So if persons are going there and working physically in presence there, they get radiation dose, so they cannot be deployed again and again. So there is a need of lot many workers, but that has been reduced because now these lasers can be delivered. Our operator goes, he fits the mechanism within less than a minute, comes back, and the operation can be completed for each channel. So within this last around 15 years, we had replaced more than 1500 channels in different reactors. So this is big achievement from our CAT. We are doing again for industrial applications, that is very specific cutting and welding applications. There are some locations in the reactor where they are not accessible. So they're gone bad due to some operational difficulties or some material problems, and those are to be replaced. So there is a remote cutting where there is no access, so laser can be delivered, and those operations are carried out. There are strategic applications also we have handled. There are biomedical applications where we are working. Then this is machine vision is a photonics application. I will not discuss much on this, but this is big achievement from RRCAT. And these systems are working round the clocks, and millions of parts are being tested, which are very small parts, and there is accuracy of less than 10 micron that is required. And online data report is generated, and they're testing now all the parts that are going into the nuclear fuel assemblies. We are working into fiber optic sensors also. And why I'm telling fiber optic sensors as our product, because these fiber optic sensors are developed here using our laser systems. And this fiber Bragg grid inscription system that is developed here is unique. And advantage here is that we can have the sensors as we desire, those can be written here. So we can have the particular period here, so its sensitivity can be defined. And as you know, these fiber sensors are multiplexed. So in single fiber, you can have 20 sensors, 5 sensors, 10 sensors at the location where you want and the sensitivity as you desired. So if we can do that, it is a great sensor for very specific application. And I will not discuss on this application further, but lab to market, one of the startups at ISC Bangalore, they have contacted, and they are working with railways, and they are developing very novel applications which are unique in the world at this stage. And they give credit to RRCat because we are giving the sensors, they come out with the systems that they could deploy. And we agree our contribution is small, but it is very critical. After the sensor, they are developing packaging, electronic systems, IoT, and data analysis. But they are very novel systems that are getting approved now from RDSO and will be deployed. And laser additive manufacturing is another area where we have a very strong presence. And many technologies are transferred, and we are going for incubation activities. And some of the major MSME players are with us and will be coming with good machines in the market. I'm sure that will make a mark. So these are some of the applications. I'm just showing photographs. So we have done, as said earlier, we had CO2 lasers of high power. We have done laser welded automobile transmission gears. We have done some other material processing also. Earlier we had developed and given this surgical CO2 laser, which was 40 watt CO2 laser, DC and foot operated. This was given to surgeons here. It has been operated, and more than 100 operations were carried out. Particularly they preferred this for thorax operation in the hospitals. But now again we are not going ahead with this medical laser applications with this. This is another application which we have handled well, and this is the way ahead where we can take our expertise and contribute to the program. This is for 5 minutes. For India Security Press, we are having this CO2 lasers. They are using CO2 lasers, and it was a CO2 laser based system, and the lasers were going bad, and that is standard that they goes bad within 2 years. And each laser refurbishment, they are charging almost 60 to 70% of the original cost of the laser. But we developed the technology, and it has been replaced within nominal cost, I would say 12,000 rupees or so. But we have developed this technology, and we are giving it to the now industry. This is again, as stated earlier, for a fiber optic sensor inscription. This is a in-house building system. This is the application where these lasers are being used. Of course, we should aim for developing this type of full system subsequently, because we cannot start initially with total import. But I think this is the way we can go for import substitute into major systems. These are the lasers which we have deployed at VRC, diode pump solid state lasers, green lasers. This is again for fiber bracketing application. These are the lasers that are deployed at NPCIL sites, and we have developed very specialized mechanisms by which these lasers can be deployed for NPCIL applications. Next. This is another application of welding. We are welding these brachytherapy capsules, which are very small. As you can see, it is a millimeter size, and this has to be helium leak tight welding to be done. And this we have done, and this system is given to BRIT. We earlier transferred the technology for welding of pacemakers. This laser system was given to Shri Pastronics, one of the industries here, for welding pacemakers. This we have developed and given earlier. Again, it was demonstrated in the hospital, but we could not go for mass production or technology transfer of this. Of course, there are queries coming again for this application. We are going for underwater cutting, which are very strategic applications for our lasers. This is the laser additive manufacturing system that we have developed, and this is technology is transferred. Dr. Paul has elaborated quite on this. This is another technology of laser additive manufacturing, and these are the very specific parts that we have developed and finding applications. We have into another photonic applications. This is called OncoDiagnoscope. This is very relevant product for India. It is for oral cancer detection. it is deployed. And now, so far so good. It looks we are done very good. There are picture is rosy. We are progressing well, but I think we have to go much ahead, and where we are looking for and how we should contribute. I think that is the view we should take in this conclave and go ahead. So this is the LIGO facility at USA, and India has now approved our LIGO India project and will be taking this. RRCAT is taking a lead role in this and will be completing the facility by 2030 now. So that is good achievement, but if you see technologically, we are at least 15 years behind and still we are not building many parts of it. So we should think and act so that we can move ahead. This is the National Ignition Facility, very big facility. There are 192 laser beams, each of around 16 to 20 kilowatts, and first laser fusion where there is energy positive has been demonstrated. Of course, it is jokingly said that the laser fusion is always 30 years ahead than to implement it. And it was said 30 years back also, and it is said even today also. Although such big laser systems are developed and such fantastic results are delivered. But there are other strategic applications of high energy lasers, and we should pursue that, although if we are not pursuing the fusion program. UK is also funding their lot high energy programs. This is now 2020 Vulcan, they had a 1 petawatt facility, now they are upgrading to 20 petawatt facility. So if we have to dream big, really, there are such systems that are available. We are not manufacturing diodes which are having extensive applications in Indian lasers. So we have to go ahead with this. So this is the point of worry that at present most of the lasers, detectors and optical components that are high-end components are imported. We have to act. There is a very little capacity to manufacture those in India. But the silver lining here is that there is a good amount of expertise within the country to address the issue. If wherever we take the activity, we can go ahead with that. And our demographic advantage has limited time window, that is maybe around 2 decades or 3 decades. Within that, we have to take advantage of its full advantage and go ahead with the engineering skill level so that subsequently we can have that advantage continued. And here I think the lasers will have a very great role to play, because then the productivity per person will be increased substantially. I can tell you one simple example. If a cobbler is cutting a shoe, he can do 2 or 3 in a day, but if he's equipped with laser, he can do 50 or 100 per day, and that too with very consistent quality and excellent performance. So that is the advantage. And here is the India, where we can call as manufacturing power development index. We have to improve on this, and at this point I think laser can contribute much better, and we can contribute with our own technology on this front. So there is need to have collaborative efforts. We have universities, institute of national importance had shown their advantages. Of course, there are weaknesses also, but government R&D institutes, there are top class subject expertise and better infrastructure. Industries, they have ability to impact. So if all 4 of these institutes, if they can combine together, then we can really move ahead. So these are my recommendations here. I'll have 2 slides for after this. So you can have these technologies that we need to have within India, and there can be some more things. And there is a coordination of efforts is required in the area of materials development. And at present, there are, I think, many sub-threshold activities are going on. So although there are a lot of efforts, but there is no critical effort. And that's why we are lagging in development of, as we say, India rods are not developed. So many other things are not developed. But there are so many persons in the area of materials they are working. So we have to go with proper coordination of the efforts. There is need to systematically support the ecosystem of the R&D institutes and academia and concerned industries to develop Indian lasers and laser-based applications. With these incubation centers coming up, I think there is a good startup in that direction, and it will move well in future. And there are certain R&D areas where there will be no immediate deliverable, but those we have to nurture as a strategic areas, and there are long gestation periods. So I remind this famous quote by Vikram Sarabhai. So we must be second to none in the application of advanced technologies in the real problems of man and society. And we work with this aim in mind so that we can contribute in the best possible way. So I feel R&D institutes, academia and industries working together with innovative ideas can write success stories for Atmanirbhar Bharat. Thank you.
Thank you, Dr. Nake, for a brilliant and very comprehensive presentation on the state of art of laser technology and the pioneering contributions in this country of the Rajaramana Advanced Technology Center in this particular field. And also, you have also given a very comprehensive picture of the array of uses of laser technology. And finally, what's happening in the world in the, in the context of laser technology. So I thank you, and let's give him another big hand, please. Yeah. Now I would request the speaker to take a few questions. I can see Dr. Goel raising his hand. Yeah, Dr. Goel, please. Yes.
First, of course, I appreciate the work that has been done. Is really has raised the pedestal of this country. But when I look at overall, pardon me, I just got a feeling that we are everything. Kind of feeling in CAT. The developments which have been done, unless we really make laser-based industry a viable industry in the country, these will remain on the lab. And that's where, I'll give a few examples. Let's say we are making a laser gyro in ISRO. And today we are making one of the best laser gyro in the world. And without the laser gyro, the Chandrayaan 3 and all that would not. But the laser is important. And obviously, if we come to you, you make a few. But we will looking at numbers because ISRO will need probably 100 lasers for that class and all that. Similarly, when I look at the future warfare, the laser is going to be component of future warfare as a weapon as well as a sensor. But for that you need industry. So unless CAT actually builds a big industry, whether it's a private or not, in fact it has to be cluster like IT cluster. It has to be a laser-based industry cluster. That part I somehow felt that has to happen. I would like to get comment. Of course, you have mentioned some of the points. But actually, if you really see that someone will take initiative, in this country, no one else will take. You have to take. So you have to really build a large laser-based industry setup or ecosystem, which I feel is a must. I would like to get your comments.
Fine. Your observations are perfect, but we are moving in that direction. And one thing I think that we have to keep it in mind that to start with, we cannot have everything within India. We have to go step by step and improve our speed of development so that ultimately we can go with the indigenous systems. When we talk of Europe, at many countries the technologies are not available in all the countries fully. They cooperate very well and come out with products. At present, India is a vast country. We have to have that type of technology.
India is bigger than whole Europe.
Yeah. And when we have to go, say like, as I said, this passport printing application, the industry that they are not approached us earlier, but when we detected the problem, no, I'm saying, coming to that issue, how to go ahead with that. So earlier that everything was imported. Now we have understood what is the problem with the laser. Now we have gone with the replacement of the laser. Now we have confidence that we can do. We can integrate rest of the system because the other printing mechanism That is a security printing mechanism. It is not a laser printer per se. They are printing very specific security features on passport. I would like to add, if you have a passport which is printed after 2018, then there is definitely a role of RR-CAT laser in that printing.
That's
And
great.
now that laser has been integrated, we can go for full mechanized system for laser printing of those security features in that. So of course, RR-CAT cannot pursue with that. So there has to be a partner with that, and we can go ahead. Along with this, now we have developed sealing technology for the CO2 laser. If there is a person from laser industry, they can add to this. You must have seen yesterday's presentation of Sajanand, but all their tubes are imported. At present in India, almost 20,000 laser tubes are imported, CO2 laser tubes are imported. They're used in very small villages also for wood cutting, leather cutting, and other applications. And after around 6 months to 1.5 years, the tubes are dumped. But we have developed technology that the tube can be revived, and that technology is now ready for transfer, and good industries have come. They will take this and deploy this product. So if we have wish, proper market also is there, then industries can take. Otherwise, most of the applications which are at high end of scientific and technological areas, there is no market. Even we are lagging on semiconductors, because if there should be a semiconductor factory running all around 24/7, and there has to be continuous improvement so that we'll be leading at global level. If semiconductor industry or that foundry is closed for one day, it will take 3 months again to revive. So this type of complexities are there when we are going for such advanced systems. But we can definitely take these applications step by step. We have to improve our contributions and its speed of contribution, and then we can go ahead, definitely.
See, if I want to buy a laser 5 kilowatt or up to 25 kilowatt, let us say, with multiple junction for a, let's say, laser gun, if I want to shoot out an aeroplane, I can get a laser only from industry. No category will give me from USA or Europe. Question is, how do we create that kind of an industry ecosystem in the country? And that responsibility, I believe, is only CAT can do. No one else will do. If you expect a Ministry of Science will do or some other ministry will do, that don't happen. So
No,
I think that's initiative has to be taken
yeah,
by.
so I think there has to be a proper consortium. We have to identify applications which we can take step by step and move ahead. So there has to be a contribution from industry also to take it, R&D institutes, and trained manpower.
Ekajan, your very comprehensive, very excellent presentation. I am taking the same thing further. You have shown two visuals, one of UK facility, one in USA. Are these government initiatives, or the combination of four segments of the expertise together? This is one thing which we have to understand, because in India we have very good talent in the government, especially in scientific institutions, no doubt about it. But it is not consistent. For example, we were the pioneers in atomic energy, 1954. This was the beginning anywhere in the world. But how much nuclear energy we are producing and using, it's questionable. Thank you.
Yes, sir. Because you have pointed out rightly, 1954, when the Asia's first nuclear reactor was installed in India, Apsara. At that time, even bicycle was not getting manufactured in India, but Department of Atomic Energy could commission nuclear reactor with our efforts. So, but where are we today? Where are we today? China has gone ahead. Other countries are going ahead. So we have to channelize our efforts and move ahead. There is another story I can tell you. Say like heavy water. Heavy water is a good product of Department of Atomic Energy, and when our earlier reactors, they need heavy water, we were not having enough quantity, and we were charged. That is, there were allegations on that. We imported clandestinely heavy water from Korea, and we were blacklisted. But Department of Atomic Energy has developed multiple technologies, plants on different technologies, on three different technologies. Heavy water production plants are developed, well established, and commercially operated. And now we are the highest manufacturer and the best manufacturer of heavy water in the world. So if there is need and there is effort, we can do and deliver the systems. And as your first question, both yes, Vulcan 2022, NIF and LIGO, all facilities are funded by government of their respective governments. Not my industry. They are R&D institute. They are R&D activities basically. But now there is an interest from private industries to go for laser fusion. I think they are looking for many other spin-off technologies out of that which can be utilized.
Anyone else? Any other question? Okay, I think Dr. Nake, thank you very much for your lecture and also for your responses to the questions.
Thank you, and I request Dr. Mishra to please present a memento to Dr. Nake. Let us thank Dr. Mishra also for conducting this session, plenary session. Thank you very much. And I request Professor Indranil Manna to please come on to the dais to present a memento to Dr. Mishra, please. Thank you, Professor Manna. Thank you. Now we will proceed to the fourth parallel technical session. After this technical session, we'll have a cultural program in this auditorium, which will be followed by the dinner. So let us assemble in the two halls where the parallel sessions are happening. Thank you. Thank you, everyone.
सुनो 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 हाँ हाँ Somebody has forgotten the key on the podium. Car key. Hyundai car. Please collect it from the reception.
Hello, 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 hello.
इसको तो यूज नहीं करेंगे।
Hello, 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 hello. ठीक।
हेलो 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 हेलो
Welcome to the fourth technical session on the theme based on lasers. To chair this session, we have Dr. Tessie Thomas, Madam. I request Dr. Tessie Thomas, Madam, former Project Director Agni of DRDO, Bangalore, to please come forward. Thank you. Dr. Tessie Thomas is an Indian scientist who served as the Director General of Aeronautical Systems and was previously the Project Director for the Agni-4 missile at the Defense Research Development Organization, and she was born in the month of April 1963. She is the first woman scientist in the Indian history to be the lead of the missile program. She pursued B.Tech from the Government Engineering College, Thrissur, and the M.Tech from the Institute of Armament Technology, Pune. She joined DRDO in 1988 and worked on the design and development of new generation ballistic missile Agni. In her work spanning more than 32 years, she has contributed in various fields such as guidance, control, inertial navigation, trajectory simulation, and mission design. Dr. APJ Abdul Kalam appointed Tessie Thomas Madam for the Agni project. Besides, she was the Associate Project Director of the 3,000 kilometer range Agni 3 missile project. She was the Project Director for Mission Agni 4, which was successfully tested in 2011. Later, Tessie Thomas was appointed as the Project Director of 5,000 kilometer range Agni 5 in 2009, which was successfully tested in the year 2012. In 2018, she became the Director General Aeronautical Systems of DRDO. She received the Lal Bahadur Shastri National Award for contribution to the field of missile technology. Dr. Tessie Thomas was also awarded Dr. Thomas Kangan Leadership Award at the Faculty of Management Studies, Institute of Rural Management, Jaipur in the year 2018. She is the first woman to lead the missile project in India. She is known as the Missile Woman of the India. In 2018, she became the Director General of Aeronautical Systems of DRDO. The Lal Bahadur Shastri Award was given to Dr. Tessie Thomas in recognition of her efforts to help India become independent in the field of missile technology. She is the Fellow of Indian National Academy of Engineering, Fellow of Telangana Academy of Sciences, Fellow of Institution of Engineers India, Senior Members of IEEE, Life Member of Aeronautical Society of India, Life Member of Indian National Society of Aerospace and Related Mechanisms, Life Member of Indian Society for Advanced Materials and Process Engineering, and Life Member of Society of Aerospace and Quality and Reliability. With these few words, ma'am, I hand over the session to you.
Thank you. Very good evening to all. I think we'll start the technical session 4, where the theme is laser applications in high-end technology. I would like to welcome the first speaker, Sri Anil Parab from L&T. He is a whole-time director and senior executive vice president, L&T, Heavy Engineering and L&T Valves. He is a mechanical engineer, passed out in 1982, and presently the senior executive management education, London Business School and Indian Institute of Management, Ahmedabad. Areas of his research work are on modification, revamp and upgrades of process plants, digital manufacturing, and he brought in Industry 4.0 in L&T. Major achievements and awards: member of CIA Manufacturing Council, chairman of Capital Goods and Strategic Skills Council of India, fellow of Indian National Academy of Engineers, member of Program Advisory Committee for the Department of Science and Technology. Is also Senate member of IIT Jammu. I welcome Sri Anil Parab to give a talk on growth of laser industry in India. Please.
This is slide reverse.
This is forward.
Forward reverse.
Okay.
And this is pointer.
Yeah. Thank you, Dr. Thomas. Good evening, ladies and gentlemen. I'll be talking more on the subject of application of lasers in high-end technology and the industries in particular. Go ahead here. No, it's not working.
You are going back. You have to go forward.
Oh, this is forward. Okay. Thank you. So actually Indian laser market, if you see, it is not very large currently. It's about US dollar $1.31 billion, but expected to grow exponentially 3 times, almost to $3 billion, and it is growing at compounded annual growth rate of 18%. Applications of laser, if you see, they are almost all pervasive. Automotive, heavy industries, electronics, high-speed internet, infrastructure, defense, and healthcare. Especially, I will like to draw your attention, this high-speed internet. It is, in fact, there is no industry which is without that. So really speaking, if you see, when we talk about high-end technology, I think every high-tech industry or the research, lasers are integral part of that. When it comes to medical, the applications I have listed few. In fact, in your day-to-day life, you must have made use of this. Cosmetology, ophthalmology, dermatology, cardiology, dentistry. Many times you may not realize you are actually making use of lasers, but you may not have full knowledge about that. Engineering and technology, metrology, LIDAR, manufacturing. In fact, every single precision machines which are used in industry, any industry, the calibration is done with the lasers. So really speaking, if you see, it is that fundamental. That means nothing you can achieve in high-tech industries and the technology areas without the application of lasers. Security and defense, navigation, guidance and control, weapon systems, night vision equipment, there are many applications. Telecommunication, high-speed internet communication, it has actually changed our life. If you really go back in 1990s, when the internet speed was not so good, in fact, not many industries were there. But today, if you see with the data transfer internet, where lasers, optic fiber lasers are available, you have live streaming, you have e-commerce, then you have the AI, ML, and going forward, blockchain. So really speaking, if you see with the advent of lasers, more and more new industries are coming, our lives are changing. Now, I would like to show you that in 1970s, we used to have, we used to have hard disk and a floppy disk. You see the data, what we used to have. Then came your CDs, 550 MB. Today, high-speed internet, 10 Gbps. And in fact, this is not the end. Today, if you really see expected data which is going to be there in 2025 is going to be 175 zettabytes. And IoT is going to consume 51%. And with the implementation of blockchain, this will only go on increasing. And one of the best example, if you really see the Chandrayaan, the way our ISRO scientists predicted,
6 p.m. 4 minutes it will land. How that is possible? There are so many devices which are based on laser application for such critical mission. So I would say that yes, it is in the scientific endeavors, it is there in the industry, it is there in our life. So lasers are so important. Actually, I will now dwell little upon industry, what we are doing. See, the industry 4.0, this is what is being talked. In fact, the kind of productivity it has revolutionized, it is unbelievable. In fact, I come from heavy industries. Today, our workmen, one workman is able to man 3 to 6 smart workstations. And that is possible because of high-speed internet, Wi-Fi enabled, artificial intelligence, and really speaking, if you see, there is no need for them to come to factory. It can be done even remotely with the kind of 5G networks which are available. So I would say that the way industry productivity, quality, reliability is getting transformed with this high-speed internet and the communication is phenomenal. And another example, if I have to say today, the UPI payments, what Aadhaar, the eKYC, all these applications of digital, finally it is dependent on the really large data transfer in real-time basis. And that India could do. Again, the basic foundation of that is optic fiber laser network. There are some applications available in industry on laser autonomous welding, where you don't need an operator. Laser will keep tracking and artificial intelligence, the welding station will continue to weld uninterrupted. Similarly, the metrology is another area. In fact, many of these applications, if you ask me, the possibilities existed, but the problem was there was no necessity. COVID was a wake-up call. When the COVID was there and you can't have your entire workforce capacity, you had social distancing, you had to stagger the shifts, you have to sanitize between the shifts. Our business, 60% was international. Customers can't come here, you can't go there. So actually all these digital technologies, though some work was started, it really got accelerated during COVID. And today, what you can achieve through this is an eye-opener. This is laser metrology. In fact, these are some few applications I don't want to take your much time, but what I am trying to tell you is, in pre-COVID, we used to do everything assembly, and you will find out interferences. Today, nothing is required. You just do the laser scanning of your different parts. Virtually, you match them and you know whether they will fit, what you need to do. A lot of efforts are saved. And in fact, one of the big reactor cryostat what we sent to Cadarache, France, it went into 52 parts, total 3,500 metric ton. Everything was virtually assembled using laser scanning, reassembled in Cadarache, France, not a single rework. That's what you can achieve using that. And I would say that this 5G networks is further revolutionizing. What I read, though it is not yet implemented, there is another network which is going to come, which is called as Li-Fi, which is laser lamps. If you are below the laser lamp, all Wi-Fi is available to you. In fact, you don't need any other network. LEGO project, I think Dr. Nakhe talked about that over there. So I am not going to dwell more time on that again, but L&T has shown interest to be part of this research project between US, India and Japan, and we will be very happy
to really support the RRCAT to implement this by 2030, what he talked. In nuclear technology, also there are a lot of advancements. In fact, Dr. Nakhe talked about lesser nuclear fusion. He said it is more like very futuristic, but a lot of work is happening across the globe on this. And we are also in touch with some foreign Western countries to work on this. Lesser nuclear fusion is another one where instead of having uncontrolled reaction, you can have a control where accelerator driven system you can have, which will improve enhance the safety. And this is particle acceleration where RRCAT works a lot on these linear accelerators, but they have application in industry also. Lot of welds, what we do, we need this linear accelerator when you have thicknesses of the parts which are being joined, which are more than 60 millimeter in thickness and as high as 400 millimeter. You need the linear accelerators for ensuring that these welds are defect free. 3D printing, in fact, I came little early this evening and I think there was one whole plenary session on 3D printing. So I will not spend much time on that, but one of the section what was being talked on wire melting layer by layer additive manufacturing, there L&T and IIT Bombay, what was mentioned L&T IIT Bombay, we are doing a joint research on this and the machines are built and now currently we are in the phase of taking trials. Lesser hybrid welding, in fact, this is one where Dr. Nakhe talked was more lesser cutting, which he talked of coolant channel. There the limitation what he talked is up to 8 millimeter thickness. But the hybrid lessers you can go as thick as 70 millimeter you can weld with narrow groove. So that's another area we are working. And lesser hybrid overlay, where partly it was talked where you can do some coatings, overlays. So this is another area where L&T is doing some work. So that's all what I wanted to talk on applications of lasers in high technology areas in industry as well as scientific community. It will be my pleasure if you have any few questions. It will be my pleasure to answer that.
Thank you, Sri Anil. I think forum is open for questions. He has covered almost all the industrial applications with respect to the laser.
Yeah. Actually, these CO2 lasers what are talked. The MIG welding you can do up to 70 millimeter thickness if you have the hybrid lasers. Yeah, there are two different lasers. You use that, and they are currently in the trial phase, but the welds are done up to 70 millimeter thick. In fact, we wanted to use them for this ITER project, what I talked, where this thickness was similar, but actually most of the times one of the difficulty which comes when you talk of these new technologies, always the scientific community will ask where it is used in past. Okay, so obviously if it is first time, they generally do not take chance. Yeah. No, basically it is a CO2 laser mixed with some gases. Yeah. Yes, correct. Yes. Actually, it produces a lot of energy because of that.
Any more questions?
I think we are in touch with Dr. Nakhe, Dr. Sendil Raja. See, what they want is they will need an industry partner. One for those special tunnels, kilometers of tunnels with mirror finish polish and the micro sensors, and also build a facility which is seismically isolated, because when you really want to detect those gravitational waves, no vibrations should come. So it's not a conventional construction. It's a very specialized construction, a lot of techniques. I think only once or twice such construction is done. So obviously we thought a company like L&T, we would definitely like to work with them.
Definitely, the world is looking at to know more about the unknown. So I think if L&T takes up such work for an observatory, it will be really great for our nation.
We always do take some research project.
I know. Thank you, Sri Anil.
Thank you. Yeah. Thank you. Yeah, thank you. Thank you.
Our second speaker is Dr. Ravindran Kumar from TFIR. He will be speaking to us on the extreme science and exciting technologies from the laser side. I would like to introduce him. He is with BE Honors Mechanical Engineering, MSc Honors Physics 1983, PhD Physics 1990, and postdoctoral 1992. Major areas of research work are in the studies and interaction of intense ultra-short pulses of light with single molecules, studies on behavior of hot and dense plasmas created by femtosecond light pulses, nonlinear optical materials, and achievements and awards are in very large umbrella science. Yeah,
yeah.
And many publications. I think we'll get into the topic.
We get to the topic.
Yeah, extreme science and.
Thank you.
Thank you.
थोड़ा सा लाइट लगा सकते हैं. It's true. Yeah. हाँ ये वाला. F5 कीजिए. All right. Thank you. Wine. Right. Thank you. It's the end of the day, but lots of exciting stuff. I hope you'll stay awake. So makes me wonder how I am here as a fundamental scientist. I underlined the fundamental part, but I must say that I have an engineering degree. So some, commonality, and also I would like to say that my visit was engineered by Dr. Nakhe, when he made the sudden phone call, I think about a couple of weeks ago. I'm glad to be here, and it's very exciting to hear, to unlearn, to clear some of my ignorance about what Indian industry is doing right now. I was thinking that nothing is happening, but lots is happening. I'm glad to know that. So this is about extremes in which are created in the lab. That is, most of the universe is extremes, as we know, the stars are full of high temperature, high density stuff, continuously churning, exploding, stars are dying, new stars are being created, etc. But how do we do it in the lab? This is the one question, high temperature simultaneously with high density, which has become possible in the last 20, 25, 30 years, I would say, with femtosecond lasers. So this talk is not about continuous kilowatt lasers or gigawatt nanosecond lasers. This is about femtosecond lasers and the story of extreme light. So this is ultra fast femtoseconds and the pulses look like this. So it's a huge amount of energy, significantly large amount of energy squeezed into a small time duration. So this is what is called, all of you know spatial focusing at a lens. We call this time focusing or temporal focusing, which makes it the monstrous power, which is what is called the peak power. So 100 terawatt peak power that we've been, CAT, us, VRC have been having for a while. When you focus it down to a small spot, you have time crunched and now space crunch it. So that becomes 10 to the 20 watts per centimeter square, which is really whopping. This morning somebody was saying you need 10 to the 7, 10 to the 8 watts per centimeter square. This is a trillion times larger, and this leads to spectacular effects. But I don't want to talk about all the basic science. I just want to tell you how this laser technology has progressed. We all know, depending on the area we work in, we keep track of what kind of lasers we are using, how they have moved on. But if you look at the smallest laser that was made, the first laser, to the big laser, the biggest laser, highest pi power laser that we have in the world now, that's 10 petawatt, and that's actually, it was installed and started in 2020, just after COVID, in the Extreme Light Infrastructure Nuclear Physics Facility in Romania. One of the 3 pillars that has become active of the ELI facilities. So that's 2020, and now we are going, people are talking about multi-petawatt, so 5 petawatt, 10 petawatt, and so on, routinely. So I think it's, this is the kind of laser that we have, that CAT has, BRC has. So we are proud owners of this kind of a laser, which is tabletop, small, compact size, reasonably. And with this, if you shine it on anything, you take anything, metal, polymer, whatever you take, liquid, whatever you want, and then you focus it, and then this place here explodes into a very, very high energy density plasma. And that plasma then starts spewing out lots of particles. And the technologies that I'm going to talk about, which are of the future, are all based on what comes out of this excitation. So extreme excitation leads to exciting possibilities among using all these particles that are being generated. So just to put a perspective so that you have something to chew on, I plotted temperature here and density here. Look at most of the things that you can identify in the universe, like from ultra cold neutral plasma, so very low density, low temperature, and all the way to solar core, high density and high temperature. So the inertial fusion, a 40, 50-year-old effort led by the big countries in the West and Japan, almost reaching somewhere, but 50 years and billions of dollars later, we still have not managed to achieve what we wanted to, but it's up there, right up there in terms competing with densities and temperatures, which are in the stellar domain, right? And planetary interiors, whatever you think of, they're all, some examples of that are plotted here. So now let me just say that I now want to start what happens. I'll just give you 1 minute of what we do in TIFR, and then I'll move on to technologies. So you see here there are lots of things which are blinking, and if I can move my mouse on the, could you just help me by, so move the mouse, for example, on this red dot here, which says protons, red dot, below, yeah. So this is work done in India, right in TIFR, where we actually, many years ago, 10 years ago, my colleague M. Krishnamurthy actually made a neutral atom accelerator. You have an accelerator here, but that is for charged particles, right? And this is a neutral atom accelerator which drives neutral atoms to mega electron volt energies. So this is the kind of, and this is pure science. It was an accidental discovery. We understood what was going on. Now we can make technology based on MEV neutral beams, use them wherever you want, lithography, probing something, heating something, whatever you want to do. And MK discovered this in clusters first, and then he discovered it in almost anything, any target that you can excite with. You can generate neutral atoms from the excitation. Now go home. There's a home icon there. Yeah, go home there. Now click on something like, for example, X-rays here. X-rays, yeah. So this is again bright X-ray sources which you can generate, which can compete with synchrotrons in their peak brightness, are all generated by using multiple areas of science like nanotechnology and excitation with high power pulses to generate very bright emissions, which you can, these are all pulses which are femtosecond duration. You can use it to machine, you can use it to image, you can use it to probe, you can do whatever you want. Go home again, please. I'm sorry, I couldn't manipulate the mouse myself. And now let's come to terahertz, which is the hot area right now. So if you have a laser like this, and everybody is looking for terahertz sources because of various reasons, I mean security reasons, strategic, whatever you can think of. This is an experiment done again at TIFR, where we took a moderate intensity laser, 10 to the 13, 10 to the 14 watts per centimeter square, put it on a liquid, water, acetone, whatever you can think of, and you can produce 60 microjoules of terahertz energy. Most other people using semiconductor emitters, gallium arsenide antennas and so on, they only produce picojoules and so on. Maybe if you put lots of arrays, you can probably put a few nanojoules and maybe sub-microjoule. But this, no great effort, no great lithography, no great fabrication, produces all, huge amount of terahertz energy. Okay, now we can go back. And so I will stop talking about our work right now. But the point I want to say, maybe we can move on. I'll move on from here. Yeah, thank you. So, so there's this rich physics that happens here, the rich science. The reason I'm emphasizing science is that often in our hurry to ask for what device have you made, we lose track of the fact that science is at the basis of all this. You understand what's going on, then you can manipulate things. And if you just ask me a question tomorrow, what kind of a device you'll give me, I don't even know. You sit on, you build up on the science that you learn here, and then it's easy for you to think of course we should think of, the engineering aspects, how do we make it commercial and so on and so forth. But let me now show you next generation technologies where I think we have a good chance if we leverage some of our capacities right now. We don't have to be also RANs, but we can probably join the race right now. So let me begin by paying respects to where I am standing right now. So I want to start with work done at CAT. This is an experiment done here to produce tabletop electron accelerators. And this is a slide I have taken very graciously offered by Dr. B.S. Rao. In fact, I stole it from him. So thank you. And so he made this wonderful slide where he said accelerators have been around for about 70 years now, and they're getting larger and larger, bigger and bigger, huge money, billions and billions of dollars. Now shrink the accelerator to tabletop. So let me just quickly scroll through this. Supposed to be the future accelerator, that unconventional technology, which will be tens of kilometers long, maybe 100. But if you now do this with a laser, and this is an experiment done at CAT long ago, right? And the field has been alive for about 25 years, but this experiment was also done quite early. So this is where they took a gas jet, focused the laser beam, and then they produced electron beams, very bright electron beams, collimated sort of, and then a tabletop accelerator. In fact, the length over which this is done is millimeters compared to tens of meters, hundreds of meters, and beyond that. So let me quickly scroll through. They produce this beautiful data. There's a lab. If you can get time, walk around and see this lab. And this is the result that they produced. And this paper attracted quite some attention, in my opinion, published way back in 2010, where they actually showed this near, you see this feature about monochromatic electrons being generated from a gas jet. And this is, I think, if I'm not wrong, Rao's PhD thesis or something like that. And so this is something that I've always admired. This work is really very nice. And then now the world has gone beyond. We of course had constraints of the laser. It's only 150 terawatt. Actually this experiment was done with a sub 100 terawatt laser. I think maybe about 7 terawatt or something like that. I'm not sure. But now with petawatt lasers, we can actually go to GeV electron beams. And GeV electron beams, like what you have in the synchrotron here, on a tabletop, accelerated over a few centimeters or maybe a centimeter or so, right? So there are challenges, but look at the possibilities here. And similarly now,
the same electrons can then be made to scatter off very high energy, a part of the beam, the electrons are there and they scatter, the laser is still there. So you bring the electrons and the laser beam together and then you produce what is called the Compton source. And the Compton source produces very high brightness electromagnetic, actually gamma ray emissions. And gamma ray emissions are very useful for various technologies in strategic, defense, whatever you can think of. So these amazing possibilities open up. And this is, I heard Dr. Nake gave a very nice example of the FEL, which is operating right here, worth seeing. And this is where you do not have a magnets as if you have a FEL, but the laser itself sort of provides some sort of a acceleration scheme akin to what you get in the magnets, or you can take the beam and then push it through, the electron beam that is generated by a laser, and put it through a conventional wiggler, and then you can get this wonderful X-ray emission. So again, 100 MeV protons, and I showed you a few MeV protons, but 100 MeV protons have been generated. Why are people talking of 100 MeV protons? Because they can kill cancer cells inside the human body exactly where the cancer is. They don't damage all the tissue while they're transporting through the body, but they go exactly where the tumor is and you can focus them on that and you can kill them. Europe is spending tens of billions of dollars trying to do this kind of a research. Again, so this is something that interests DAE. Intense gamma rays and neutron sources. You can also produce neutron sources. How do you produce a neutron source? On the target that I showed you, you have deuterated, you deuterate the surface. So you have D, you have the deuterium, which gets excited, which gets accelerated, which gets ionized and accelerated, and then collides with, they collide among themselves, and D fusion actually produces neutrons. So you get pulsed neutrons, which are picoseconds are shorter. So that is again great for so many applications. You don't have to go to a big, reactor or an accelerator to produce these kind of beams. So that's amazing. And look at this. So the conventional synchrotron, which is circling CAT, the big campus, can be shrunk to compact sizes, very, very small sizes, if you just use a laser and then you scatter the accelerated electrons, the laser scatters off, it gives you the scattered beam, which is highly bright and very high energies, wonderful for room kind of applications, tabletop applications. So MEV beams, I just want to spend a minute because I went to BRC a few months ago and they showed me a wonderful machine that they have made, but based on conventional acceleration, where they are actually trying to produce photon beams via Bremsstrahlung or whatever mechanism you can think of, but that is bulky. Now I'm trying to say that if you can produce the same kind of beams with a laser, something like 1 MeV photon beam, won't that be great? You don't have to worry about all that. The lasers also become big, but on the other hand, they're not as big as what they had made. So it's a new technology. This is the way the world is moving. This is tomorrow, right? We should be there well before it becomes the yesterday. So can be transported. MEV beams have huge advantages. They can penetrate through maybe centimeters of steel. They can be transported without loss over long distances. So huge advantages, particularly in the defense and strategic sectors. So let me just say this is all about how these materials interact. You can actually see behind the steel container what exactly, if there is some contraband material, you can actually see there. And everybody who has an X-ray beam immediately starts thinking of biology. Can I image inside proteins? Can I image inside the organic systems and so on, inside the cells and so on and so forth. This is one example where you can do phase contrast tomography, and many of these areas are actually being currently practiced in RRCAT, and they have had interest in all these areas. Now it's only a matter of scaling up and going to the next level. So this is again what happens if you use different particles. You can use optical image, which looks here, X-ray image looks like this here, and neutron image, you can image using neutrons, so that looks like that. So fantastic. And this is a very recent article that I just saw where they are thinking of how to scale up the neutron flux by just pumping up the laser intensity. So for example, here you have this is a scaling relation. So of the neutron flux as a function of the laser intensity, you see how beautifully it's scaling. So if you go higher and higher, you have larger and larger fluxes of neutrons. So I want to show you some things that a different branch of TIFR, a new campus of TIFR in Hyderabad. We have a new home in Hyderabad where we started with a small laser on way to a petawatt laser. So CAT actually has a petawatt laser right now that they are trying to do all these exciting things with. But we began with a kilohertz laser, and we started doing what is called, with the electrons that we can generate, the fast electrons that we can generate, can we use them for various applications? So this is an example of what other people have done using, trying to use these electron pulses or the X-ray pulses to look inside solids as things happen. Let me show you with the 10 kilohertz, very modest energy laser, what we have done at Hyderabad. This is my colleague M. Krishnamurthy and his co-workers. So you see the image of a leaf. You can see the leaf. So this is biological samples with very low opacity. Usually you can do what is called, if you have high opacity, you can get a shadow or you can do contrast imaging. But this is actually very low opacity, but still we are able to resolve the features there. And this is a printed, just to excite people who are in the industry, that, we are working in collaboration with GE, and somebody was mentioning GE this afternoon. So this is, we can image this electronic boards with these electron beams or the X-ray beams. And very, at 10 kilohertz, we are talking about, so the image is taken in no time because you have 10,000 pulses per second. And the flux that you get is enormous accumulated flux. So very soon you are just scanning samples one after the other. That is possible with this. So something interesting, particularly to us, given our and the way the environment is changing. A very exciting example is to detect radioactivity based purely on electromagnetic signatures. Somebody has put some dirty material there across the border, and you are here, you can't cross. But you can shine a laser on this material. The radioactive material actually creates a lot of O2 minus, oxygen minus ions, which actually lower the breakdown threshold of this gas. So if you now shine a laser there, it produces an avalanche of electrons, and you send a second pulse, and that pulse transmission is indication of how much of ionization is there. So just by using multiple pulses, which I show you in the next slide, you can actually, let me show you how this works. So you have this material, this dirty material producing this excess of O2 minus ions here locally, and then there is this pulse that comes, the red pulse comes and causes an avalanche here, and the blue pulse then goes through that avalanche, and the blue pulse transmission is modified by the electron cloud that is there. So the moment you know that somebody has done something, the opacity of that for the blue beam tells you that there's a dirty material there. Just watch out. You don't need to go anywhere. Probably this can be scaled up to tens of meters, hundreds of meters, and so on. And these are distance free space propagation of lasers in air. So that's very, novel. And early this year, the European group called Terra Mobile, I think it was the operation for the last 20 years from 2000 onwards, and they said that they have controlled lightning using lasers, femtosecond lasers. So you go and read about that experiment, the Terra Mobile 2023 Nature Photonics, and this is an experiment that we did in collaboration with the Israeli physicist Ari Ziegler, who had some nice ideas about this, and he came over to our lab to do this experiment. So we created this lightning channel in a corridor of TIFR, of course in the night when there's nobody, and being very safe and taking all permissions, no violation of any security there. But this amazing what you can do, the light actually breaks down the glass as it propagates because of filamentation. And now people are saying you can filament this light, you can transport this light over something like kilometers. That's the proposal. 50, 100 meters has already been possible. The light just guides itself by ionizing itself through the air. And this is what is called self-channeling of light, discovered way back in 1994, but very applicable in real life situation. Not only that, I'll tell you one more example. When this lightning goes through, suppose you create this lightning, it produces electromagnetic emission, and if you want to jam the enemy communications, that radiation can actually jam the enemy and make their communications totally dead. You don't need to blind people, you can just disable their signals by just shooting a laser in that direction. So these is amazing possibilities that are there. Now the question is, and there are strategic applications, I will not spend too much time, I think I'm running out. The shocks that can be produced by these femtosecond lasers can be enormous, and they are parallel are complementary to the shocks that you can produce with a nanosecond laser. So we have done a lot of work on this. If you are interested, I can tell you more. We can create terapascal kind of pressures in, with a 30 femtosecond pulse, and we can create much more than this, but this is one of the early attempts. And we published lots and lots of work. You can look up Google Scholar and find out what all we have done. So this is again interesting for DAE in particular, DRDO in particular, and these are all things that we should legitimately do in our own country. This is our future, our own future in Hyderabad, where there will be a petawatt laser at the end of December 24, and we'll be doing all these things and much, much more. And of course, also learning from what RRCat learns in their own experiments. So, but now I take 2 minutes to provoke, right? And I'm going, I hope you don't mind. So the technology challenges are global. They are for you and they are for anybody in the US, Europe, everywhere. The fact is that the rate at which these lasers fire is very, very low. You give 1 pulse per second is no big deal. The higher you go, the lower the rep rate. So maybe we should change our strategy of producing this high peak power. Damage to shoulder of optics is a serious problem as you go to higher and higher powers. Materials availability and growth. In fact, I learned that the National Ignition Facility had a 20-year program. There was a whole division just making, cleaner and cleaner glass, cleaner and cleaner crystals, no impurities at all. They spent hundreds of millions of dollars just purifying the crystals so that they don't suffer damage when the high power laser beam propagates. So we need to do all that. We need to do much more about all this stuff. And though I said tabletop, the tabletop is sort of going over the room now. I mean, it's going beyond the wall. So, you grab more land on the other side, or, you drive the guy out and you take that space. So we have to do some khosla ka ghosla, right? So, and these are all general things, but challenges for India are peculiar. And these are something that we should address now. If we are thinking of 2047, if you want to be a leader in many technologies, particularly lasers, I think this is what we need to do. I've seen many other people say this very politely and mildly and very sort of collegially. I will say it bluntly. I think we have almost non-existing manufacturing base in lasers and laser electronics. People say we are doing things, but lots of those things are actually coming from outside. When do we stand on our own 2 feet? That is a big question that we should all address in every aspect. Every aspect of the laser we should be able to make. We should make for the world, not for India. The Indian market is not big enough for us. We should make actually and grab the whole world's market for Indian. So, and this is another thing, people don't stress this often. We don't have enough people who can be employed in this industry, even if we make them, right? We have no training in optics, photonics or lasers in any university in the country. Most people's knowledge of optics stops at Jenkins and White, like maybe +2, and that's it. They know nothing more. And the world has moved on, people are doing very specialized things, and we have these absolute bright people, but no knowledge in optics, so we have to provide all that, so we lose a lot of time. And complete absence of high intensity laser activities in the university sector. So this is something serious. Unless we propagate this everywhere, it's highly expensive, but we are aiming to be a 3rd largest economy in the world by 2047. And how do we do that if we are scrimping on money? We can't scrimp on money. If you need 1,000 crores, if you need 10,000 crores, this is the time to put the money there and make sure that we are the leaders. So only in DAE, look at this map. I mean, I am happy that I'm a part of DAE, but I am not so happy that nobody else from the university sector joins this activity, because they have large number of people who can actually benefit from this training, and we need them to populate this area. Otherwise, we are just confined islands of this peak work and nothing else. So just 3 places in India, and that's it, no more. So that's a sad thing. And what does the country need to do? So my recipe, I will engage with you in debate at the dinner. Aggressively invest in building up optics, lasers and photonics manufacturing. It is not time to say you put your money, where is the money coming from private sector? No, this is not, this is as fundamental as health, as fundamental as education, as fundamental as anything else. 1950 was a semiconductor revolution. We are waking up now that we should have fab facilities. 1960 was the lasers. please let's not spend another 10 years saying that we should be investing in the technology of lasers and optics and so on. The PLI scheme is a great idea. I don't know much about it, but it seems to be working for electronics and other high-end stuff. We should probably get the best global companies, open the doors for them, lay the red carpet, get them to manufacture in India, make India a manufacturing hub for optics, photonics and lasers. That is the only way to go in my opinion. And the future, as very often as said by many other colleagues here, is fiber lasers. We can't do these big crystals, grow larger and larger, occupy bigger and bigger. Just wrap the fiber, do coherent combining as was talked about this morning, and then make very high power lasers both for the CW and the pulse domains. And this is the way to go, and we can jump on the fiber laser bandwagon right now. We don't need to do all the things that the West has done. Straight into fiber lasers, build up technology, and then we can compete with the world, I'm sure. And build up human resources. I can't tell you enough about this. Everybody is gaga about ML and AI. The future is ML, the future is AI, IoT, and whatever, armament IoT, whatever I heard this afternoon. But optics is fundamental, photonics is fundamental. You can't miss this and then claim to be world leaders in anything in future. So I'm plugging very hard, and I know I'm just trying to push my sales pitch, but this is what we need to do everywhere. I think we can't let this pass us now. There's no way we can let this go past us. And the suggestions for DAE, so I know that there are important people here, so who can mentor and advise us. This is the home of high power lasers. We can't lose the advantage that we have. So while the rest of the country is catching up, let us push harder in whatever niche areas that we have, and let us not slow down. Let's not pull the pedal off the accelerator. We need to go more and more and keep up. Even if there are just 3-4 of us, let us be on par with the rest of the world so that we don't miss out on anything in the technology, and focus heavily on science. And of course, I'm from TIFR, so I always talk about science. Without science, strong science, the next generation technology, you're always taking technology from somewhere. You do great science, you can do technology on your own. And an active startup system in partnership with young entrepreneurs, Bangalore, Hyderabad are teaming with them. Skyroot is something that I was delighted to learn what they're doing. Young people who are not scared of the Chinese or the Americans or anyone, and they should be the ones who are doing this, and encourage courses in universities. I'm glad to know that CAT is starting a program with IIT Indore, but there should be many more such courses, training people in optics, photonics and lasers, and huge community we need to build up. And with that, I want to thank you for listening to this.
Thank you. Thank you, Dr. Ravindra Kumar. I think he has taken us through a very exciting journey of future of laser applications. As he mentioned, I think the school level onwards, this topic has to be taught so that the youngsters knows the real application and the real wonders what we can do with this laser applications. Thank you. Questions from the audience side?
Yeah. Yeah.
So, what is the source you are using for the acceleration of the neutral atom?
Okay, it is just a piece of. Oh, the feedback. Okay, it's just a piece of metal. It could be something somewhere. I don't know where. So it could be. It was done with argon clusters. In a gas pumped through a high pressure nozzle, high pressure gas pumped through a nozzle, and that created these clusters. And these are argon, 40,000 argon atoms forming a nanometer size cluster. And the cluster got ionized, but there was a surrounding plasma. The plasma had lots of electrons which were exciting the neutral atoms in the sheath that was surrounding this plasma. And the highly charged argon got accelerated, which was kicked by the laser, and on the way it exchanged energy with the neighboring atoms. So this is what we call staying neutral under intense provocation. You know what I mean? That we kicked it very hard, it got ionized, but on the way it neutralized itself. It lost the charge, but has the energy. So now you can do it with a piece of metal. Give me copper, aluminum, steel, I'll just produce neutral hydrogen from there. Yeah. 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 I know. Yeah. I would say you are, this is where it happened. So the people are all here, talk to them. Fund them, please. They will give you, I'm sure they'll make an accelerator and give you. I think, the fact is that, as I said, my ignorance, how little I knew when I was saying nothing is being done in India. I ate some of my words this morning when I heard all the beautiful things that people are doing. But the point is that this is the first time now with the industry, people like you, L&T has been, you're working for ITER, that I've known for a long time. You should reach out to people and fund them, not wait for the government to do things, right? No, I'm just saying, put your money here, and they'll give you an accelerator. Yeah, he's right there. Yeah. True, but we have gone beyond that. Samir was still old technology. This is new. I think the table is ready for you to sign. No, I'm saying the table is ready for you to sign a deal right away. Please.
Hello. Excuse me. How you measure the terapascal pressure generated by shock?
So, but I'll just give you a one-line answer. So the shock propagates, and then it's pushing material. So we actually put a Doppler spectrometer at the other side, and we know the velocity at which the rear of the foil is moving, and from there we can infer what the pressure was. But I can give you the details. So it is basically motion spectroscopy, right? Nothing more. And spectral shift corresponding to a velocity, and the velocity will give you what is the pressure that is generated. Yeah. Please. I think a lot of work is happening, in DRDO, where you are.
Yeah.
Right? You are on the missile side, or I'm sure there's been a huge laser activity. Much of this is not known. But maybe Dr. Nakhe and colleagues here know more about that. But I think, maybe you should get people together. Though I'm a fundamental scientist, I do have concerns about, what we are surrounded by. The world is becoming very difficult to live in. So the science knowledge and the engineering that we have, the technologies that we have in CAT and BRC and CAT have been trying to transfer things to a lot of people. Nobody has picked it up in the last few decades. Now is probably the right time. So get a few of us together and we can tell you what we can do. And
I think we should look at it
very innocent manner,
Yeah.
Without telling anyone else.
Yeah. Any more questions? Thank you.
There's one last question here. Yeah. Fiber pulse lasers. I know only about the pulse. I think it's not been very successful. Most of the fiber lasers are in the CW, maybe nanosecond at the most. Mode locked fiber lasers are there, but people talk of coherent combining. This afternoon there was an excellent hint about what can happen if you combine lots of those fibers. But you'll have to combine them coherently. That's a challenge right now. But that's the future. What doesn't happen today, I'm sure will happen 10 years from now.
Sir?
Yeah.
Sir, so laser can be used to generate nuclear energy? Like I had that question.
You asked this question in the morning too, I think.
Yes,
Are you the same person?
Yes, sir.
So laser fusion has been on for a long time. I told you about the NIF laser cost $3 billion.
Okay.
Right?
Yes.
And before that there was so much. Now, of course, it's much more. I know. No, the laser itself cost about 3 billion, but the overall accumulated money is probably about 10 billion or so in the last few decades. So last year there was a breakthrough in creating fusion between D and T.
Yes.
In the capsule, and they have what is called a notional break even. That's really not a break even, but at the final stage they got more energy than what they put in.
Yes.
So it's a threshold that they have crossed. I can tell you more in outside. Yeah.
Yes. Thank you, sir.
Thanks. It's much more now. 3 billion. Thank you.
I would like to call upon Dr. Sendil Raja from RRCAT to have a talk on LIGO, Fundamental Science Pushing Engineering Limits.
Thank you, madam. Yeah, so let me take you to the other end of the Fourier spectrum. So Dr. Ravindra Kumar talked about.
Introduce also.
There was a slide. There was a slide, I think. So we'll continue the talk. So people are getting anxious for dinner also.
Okay.
Yeah.
Please go ahead, sir.
So as I mentioned, let's take you to the other end of the spectrum, from attoseconds, femtoseconds to extreme long coherence length, which is what LIGO does. So yeah, thank you. Okay. Start. Yeah. So LIGO is an acronym for Laser Interferometer Gravitational Wave Observatory. It's a kind of an artificially built acronym because you again write LIGO Observatory. So yeah. So LIGO is a good example how fundamental science push technology, and that is something I think we miss here. Dr. Ravindra Kumar tried to stress that point. Usually there's a kind of a catch-22 situation. You don't want to build some extreme technology because there's no application for it. But since the technology doesn't exist, the science doesn't go forward. So large projects like this try to break that catch-22 situation. And I believe NIF was never intended to do fusion. It was purely to put the break there, that you have a breaking of this catch-22 situation. You push technologies on glass, damage threshold of coatings, large KTP crystals, which aids other applications also, and creates the kind of ecosystem which allows the engendering of the laser technology and other things and all. And that is where part of the problem lies in the country also, I think. And so let's walk through this. Part of it is about how many things happen, and some on what we are trying to do to address some of that activity here. So just a bit of background. Gravitational waves are again extreme interactions. So you saw matter level extreme interactions. So these are extreme interactions which are much more extreme than what Dr. Ravindra Kumar mentioned. So it almost affects your fabric of space-time, and that vibration of fabric of space-time is what you detect. In fact, the GTR, the last proponent of GTR was the existence of probably a gravitational wave. In fact, Einstein didn't believe that it existed. He thought it was an issue with non-linearization of the equations. But by 1960, Isaacson kind of proved it that even in the linearized set, you would have a propagating gravitational wave in traveling the speed of light. And people started hunting for it. There was this binary pulsar study which kind of proved that it does exist in an indirect manner. But in 2015, for the first time after 100 years of the GTR, it was detected by a human or a mankind built detector, to be correct. And so this fetched the Nobel Prize in 2017. So this was something which was seen as a fool's dream. People believe that this will never happen. And so a lot of technologies got together to do it and pushing every aspects of engineering. So these are the two observatories that are currently operating. In fact, the O4 is running now, which is Science Run for 4, and many events are in progress. So one is at Livingston, one is at Hanford, and these achieve extreme sensitivities. These are just Michelson interferometers, glorified Michelson interferometers. I'll come to that. And intentionally, they were built across the continental US. I'll bring to that also. The first interest was to be able to detect gravitational waves and set GTR on a very sound footing, even in extreme gravity and extreme velocities of the binary mergers. But having detected gravitational waves, the idea was to do multi-messenger astronomy. And if you want to do multi-messenger astronomy, you need to point out from which part of the sky the gravitational wave event happened and where it originated. And with foresight, they built these detectors how far apart they can build. Probably they couldn't get land in Florida, so this is the longest they could build across continental US. And that is one of the reasons why we become interesting. And these are the first detected event from a binary black hole merger on September 14, 2015. And these are the waveforms as calculated and subtracted, and what you have is residual noise. And so the GTR and the detection do match very well. And this was the first merger of a neutron star merger. So when you have a black hole merger, there is no visible light or electromagnetic spectrum or any other event there. It is just the rumbling of space-time. But when you have a neutron star merger, you have what is called an associated kilonova. You get to do a lot of other interesting physics. You can do nuclear physics, you can do nucleosynthesis, you can do equation of state for the neutron star, a lot of other things happen. So this leads to what is called a multi-messenger astronomy. So multi-messenger astronomy essentially happens that you have a gravitational wave which sets out a trigger and tries to say that this is the portion of the sky, please look for the kilonova. But then you have follow-up from visible and infrared telescopes, you have radio telescopes trying to look for them, you have neutrino looking for events which can correlate with that, gamma ray bursts which can look for that. In fact, the first event that was detected set many of the outstanding questions in physics, at least 3 of them. One, what are GBRs, which are gravitational wave bursts? It was proven that it is a kilonova associated burst. The other was, how are higher elements like gold and platinum synthesized in the universe, because the iron is the highest point where the nucleosynthesis stopped, so they happen in kilonovas. And so these things, fundamental questions got answered with just one event. And so that's the kind of richness that you can probably see in the future science with gravitational astronomy along with multi-messenger, and that is where India becomes interesting. So gravitational wave detection is like an antenna. It doesn't give you a direction on its own. If there's one detector, it's just going to say that there was an event with certain amplitude and certain phase and certain time. But if you have 2 events and they're separated from by long baselines, like the very way with which your phone tells you that you're in Mahu or Indore by triangulation, you can find out from which part of the sky the event originated, and then you can get the other electromagnetic spectrum people to look at the sky in that spectrum, in that direction. And that is where LIGO India is necessary to be able to do this kind of multi-messenger astronomy quickly, and that's where the project comes in. Yeah, so as I mentioned, the LIGO detector is a glorified microsensor interferometer. So this is the microsensor interferometer, but 4 kilometers long. And as somebody mentioned, every precision measurement that is done is calibrated with a microsensor interferometer, displacement measurement. Only in this case, it's 4 kilometers long for observed reasons. If you have the average gravitational wave strength in the universe, or the near up to the Virgo cluster, if you have a meter distance of test masses, the average gravitational wave would shift this test mass by an order of something like 10 to the minus 23 meters. 10 to the minus 23 meters is an absurdly small number. So this is called the strain that the gravitational wave produces. And to bring it to a reasonable or manageable state, many techniques have been implemented. First, build a long enough interferometer so that the accumulated displacement is large enough. So with a 4 kilometer, instead of 10 to the minus 23, you end up with something like 10 to the minus 20 as a displacement measurement. And then there are other techniques like increasing the cavity power. You have a folding mirror, which acts like a fabric mirror. And this fabric mirror ensures that the light bounces back multiple times inside each of these arms, effectively multiplying the length over which the detection happens. So if you have a thinness of around 300, then you further reduce your sensitivity requirement from 10 to the minus 20 to something like 10 to the minus 18. And then there are techniques like power recycling. If you have a microsensor interferometer biased exactly at the dark port, all the power goes back to the laser source at the bright port, and the dark port is where you're sensing. You can put another mirror here to put that power back, increasing the sensitivity of the detector. That is another technique that leads to another factor of 10. So you 100 in fact. So you come from 10 to the minus 18 to 10 to the minus 16. And then you can do signal recycling. Most of these events are binary star mergers, neutron stars spiraling in, or black hole mergering. So these highest frequencies are the order of something like kilohertz. So most of the interesting band is in subhertz all the way to kilohertz, but LIGO detectors cannot go below 10 hertz because of the gravitational wave, because of the gravity, because of the vibrations that you encounter because of seismic noise. So the sensitivity of the detectors of advanced LIGO are from 50 hertz to a kilohertz. And since gravitational wave travel at the speed of light, and the length of these arms are very, very small compared to the actual wavelength of gravitational wave, we can put the signal back into the interferometer to accrue more signal. So this is called a signal recycling mirror. So this gives you another advantage of 100, bringing it to something like 10 to the minus 14. So 10 to the minus 14 now becomes amenable for measurement and displacement, and that is where the whole crux lies. So though everything is simplified, if you want this interferometer to work at 4 kilometer length, you would agree that maintaining alignment in a shaky ground, ensuring that these are all inertial with respect to the stars, so that the average ground vibrates at something like 10 to 100 nanometer in the bandwidth of something like 10 hertz to 50 hertz, and that is what actually disturbs the whole interferometer. And apart from that, the deviation of the optics, for example, if you want a fabricated interferometer which is 4 kilometer long and you want that to be in resonance and maintain the required sensitivity, then the quality of optics or the flatness of optics is exquisite. Usually when you talk about tabletop optics and lasers, you talk about lambda by 20 as good optics, lambda by 50 is extremely good, but in LIGO it goes all the way to lambda by 1000. And so there is a kind of an art in even fabricating them, measuring them and qualifying them. So this is a snapshot of the various components. So what is shown as a small block of laser here occupies a table of around 5 meters by 2 meters, and it consists of, I'll give a bit of detail there. And all the optics have to be isolated from the ground. As I said, the ground oscillates with something like 10 nanometers, and you need to build an isolation stage which can isolate by an order of 10 to the minus 14 if you want to be able to sense gravitational waves. So there are 7 stacks, 3 of them actively isolated, 3 of them passive. You know that if you hang a pendulum and the pendulum is above resonance, you have a 1/f isolation. So that degree is used. And all of these have been built in such a way that they can be put inside a vacuum, because obviously at 4 kilometers, the amount of phase that you accrue because of any fluctuation, the density of air itself can mask everything. A 1 meter air path has a phase delay of something like tens of microns with temperature changes of half a degree. So imagine at 4 kilometers what is going to happen. So the whole interferometer has to be put inside UHV vacuum at 10 to the minus 9 millibar, and that was what allows it to reach the required sensitivity. So every optical element, every component, every suspension has to be built so that it is UHV compatible. So not only do you mess up with what is the accuracy of the optical elements, you also want to make them clean enough that they can hold the vacuum system. Yeah. So I'll focus on 2 systems, 2 components, the laser and the optics. So this is the pre-stabilized laser as it's currently operating in Hanford, one of the observatories. And this is a complete layout of the optical system of the laser. So it has what is called an NPRO, which is a non-planar ring oscillator. I'll detail that a bit. Medium stage amplifier, and a high power stage, which was initially built as an injection seeded power amplifier, but now replaced with fiber laser, because this was built 10 years back and the current technology has made fiber lasers possible to do that. And the current operation happens with fiber laser, which is bought out from Coherent. And then you have a lot of diagnostic and further cavities to improve that, because in spite of having built ultra narrow line with laser and getting high in very low intensity noise, you still need to correct and compensate for many of those to make it silent enough to be able to do gravitational wave detection. So as early as 2013-14, we thought we had an inkling that we'll have a good shot at being able to convince the US colleagues to build a LIGO detector in India, and we started work something like 2013 and 14 to start looking at the laser system and the optics. And the idea was that, as I mentioned, treat LIGO as a kind of a challenge to build some of those components with our own expertise, so that for the next generation of LIGO detectors, for example, LIGO detectors are like the 3-inch telescope that Newton built. It's just the start of the story, and there's already plans to build what is called Cosmic Voyager and Einstein telescope, which are something like 10 kilometers long or 20 kilometers long. And so if we need to contribute to the next generation of detectors and also build the capacity for ultra narrow line with lasers or extreme laser technology and optics, we felt that was a good challenge to do that as part of expertise building for LIGO. So we started out by looking at what are the issues that we face in conventional laser technology, and you saw that in the case of LIGO, most of the components are built with conventional optical components because it was built by Max Planck Institute. It's a science institute, and they built it. We had a bit of expertise in monolithic design, so we started out with first trying to build a laser which will be stable on its own without having to do locking. So this is a drift-free laser. There's no free mirror mount. It's all machined out of a single block of aluminum, annealed 6061. And subsequent to that, we did a lot of FEA analysis and found out that the main reason for pointing drift was bimetallic activity. So if you can kind of isolate the crystal and mount it with a flexure so that there's no bimetallic activity on the crystal itself, the pointing improves to a very large extent without any active control. So this reduces the penalty on your servo controls, and the residual noise that you get after the servo control is activated. So this was the basis of which we started out with. So the whole narrow linewidth laser was invented for LIGO. It was done by the Stanford group, and the conventional vision was that if you have to build a narrow linewidth laser, essentially came from the dye laser people, you build what is called a traveling wave ring resonator. The traveling wave ring laser in dye laser was the one that could achieve sub-kilohertz line width in those days, and people borrowed that idea to build a monolithic ring laser in a Nd:YAG crystal. So essentially, the Nd:YAG crystal is cut and polished in such a way that there's only one phase which needs to be coated, and the rest of the ring is formed monolithically inside. This avoids any mirror mounts which can oscillate, change the cavity length, drift the cavity, or introduce noise. And this monolithic ring laser has to be unidirectional so that there is no mode burning into it, so that we can lead to higher order modes. So this is achieved by applying a magnetic field. Nd:YAG is slightly magnetoptic, which is used to kind of have a relative loss in one direction compared to other, which is what the dye laser people do with a normal Faraday oscillator. So the crystal acts as a Faraday oscillator also, so that it ends up with the unidirectional oscillator. And this is the workhorse of the complete LIGO laser. This is what establishes the narrow line width. The rest of it is all about amplifying it and maintaining it and improving upon the narrow line width that this oscillator produces. So we built this whole system from scratch just to learn how to do it, though it is available commercially from a company called Coherent as a Memphis laser, but we built this in an open format so that the people who are building it can learn how to play around with it, look at the temperature controls, the servo controls, and also the magnetic field, optimize it. And we learned a few bit of things which allow that to achieve quickly the required narrow line width. And here we have done beat frequency measurement using this as a commercial beat and this as a laser, and achieved something like 70 Hertz line width, and attributing all that to the laser that we built and 0 line width to the commercial laser. So that's the instantaneous line width. You also want to maintain this line width over a long delay line, which is a drift compensation. So that drift compensation comes by locking it to a cavity. And these cavities are also special in some sense that because you cannot build cavities which are made out of mirror mounts, they're going to drift and oscillate and introduce high frequency noise. So you need to build it as a monolithic assembly. So that technique also we developed. We initially did the bonding for fusilica with pre-aligned mirrors. We are currently doing for Zerada, and this is one of the techniques which allows narrow line width lasers to be locked over long time periods, and a kind of a bulwark for the timing community, especially cold atom based timing community, which uses it as a flywheel. So in the case of the cold atom, the time constant comes from the transitions, but the flywheel is the narrow line width laser. So this is another technique that allows that. So having done the open format, then we wanted to build something for our 10-meter prototype. We built an engineering version so that it is evacuatable. We saw that the open format laser, if you stand in the lab and talk, you get a modulation of few kilohertz. So the acoustic wave from your speech can modulate the laser by a few kilohertz. So we built a system which could be evacuated to avoid acoustic coupling, and that avoids that. And this is a system that we built for a 10-meter laser system, which is performed similar to what the LIGO laser system components that we'll get subsequently now as part of the collaborative effort. And this goes on to the 10-meter. The second part of the PSL that you saw was a 4-pass amplifier, and this pushes the power of the oscillator from 500 milliwatts to something like 20 watts. And this is thermal modeling for that. We repeated this and saw that matches with the design that the Max Planck Institute did. But we modified it. My colleagues in the laser team got away with this compensating lens because it introduced a bit of thermal lensing by making the path length much more compact. But this required us to build a system which was really tight knit. And in the case of the LIGO system, this is laid out on an optical table. So they had to design the thermal lens model such that they have a compensating lens. But in wanting to get rid of the compensating lens, the distances of the crystal that you have to get into optical confection does not allow you to use normal mechanical mounts. And also for robustness, we again use a monolithic technique to build a 4-pass amplifier, which is end pumped by fibers, and the laser threads through this in a sequential fashion, so that it just passes through and comes back. If you remove the amplifier, the oscillator is available. You introduce the amplifier, you get 20 watts of power without changing the line width of the laser. So this is our test bench, which we're in the current process of getting up and running. So the laser system will be tested here. We built some optics for it, and this will be both a training and a testing facility for some of the techniques that we develop, both for the laser development, the optics testing, also new techniques of interferometric locking, which contributes to the next generation of activity in LIGO. The other component that I'd like to kind of give you a glimpse about is the optical development, which again has commonality for various applications. So here the optical element is something like 380 mm in diameter, 200 mm thick, 40 kgs length, mainly because you want a heavy mass for the test masses. So that drives it so that the radiation pressure does not shake the mirror by more than the gravitational wave that can activate it, and that's where the size comes from. But the finish on this is in the order of angstroms. So silicon atoms have a spacing of 0.3 angstroms, so you can guess the kind of flatness that you want to get. And this ironically started out with an academic institution and is now a trap technology inside a company. So, and there's only one vendor in the world that who can do that. So it initially started out with CSO, which is Australian company, Australian consortium of scientific research, which built the initial optics for LIGO. And then this is no more funded. This has been disbanded. so subsequently, this technique, which was a lab polisher, initially people used to polish with pitch. So pitch has a limitation over which you can do figuring, and that does not allow you to do that. So they invented the Teflon lab polisher so that they can achieve the required lambda by 500 they required for the initial LIGO. And this was a technique that was developed completely in the CSA of Australia as part of the contribution that they did for the LIGO detector in the initial part. And this technique was then picked up by Chuba University for doing what is called semiconductor optics polishing, mainly for surface wave devices where they need to achieve very smooth, super smooth polishing. And this super smooth polishing is what now is captive inside ASML and Zygo, which produces optics for LIGO. It's a single vendor delivery, and that makes the gravitational wave community very uncomfortable because it's a single vendor who you are driven by their schedules instead of your project schedules. And we felt that since LIGO challenges us, let us see if we, given the expertise that we have in the center in optics and lasers, whether we can push the limit. We built a small experimental machine to just do float polishing, which allows us to now build a bigger machine, which we are trying to do for 5 mm diameter, and this is one of the targets. The other thing is to build metrology for it. So normally Zygo builds the metrology, that's why they're captive of it. So in this case, we just bought it out because you have to have some basic reference to do that. This facility is ready, which allows us to do metrology of the optics that we fabricate. And the other part of the optics is the coating that go on the optics. Dr. Ravindra Kumar mentioned about high damage threshold, but high damage threshold is one part of the story for the high intensity people. But in LIGO, since you're looking for extreme silence, the Brownian motion of the coating itself is a nuisance. So you need to be able to measure those Brownian motion on the coating, and which itself is a task of its own and requires very special techniques to do that. So that is another thing that we're addressing, building thermal noise interferometers, which can characterize optical coatings that are developed at Arakat. We have a very established coating facility, and we're adding these thermal noise measurements so that we can push the limits on the coating capabilities, both in terms of thermal noise, damage threshold, and those applications. And the hope is to build capacity so that not only do we build some of the running spares for the O&M for LIGO project, but also capacity for the new generation of projects that happens. So quantum is the flavor of the day, and some of these optics and laser techniques directly feed into the quantum techniques. In fact, LIGO is the first applied use of quantum technology, arguably. So this is radiation pressure. Sorry, this is radiation pressure. This is your shock noise, and this green is the residual part, which is a summation of these, and this leads to what is called the standard quantum limit. And for the first time, for the last 10 years, people have been toying with this idea that you can beat shock noise by introducing a squeeze light source into LIGO or an interferometer, so that you have a reduced shock noise, and this is demonstrable proof of that. So this is from the current O3 run, and it is operating with a squeeze light source with a dark port, and you have an improvement of 35% in the Livingston detector and 25% in the Hanford detector, which is without increasing the laser power, which makes the interference unstable. So with this, we also have started some work, because this is not something that is part of the advanced LIGO that we are part of the collaboration. With this upgrade, we'll have to build on ourselves. So we are starting out some work on squeeze light source development, and we hope to build a squeeze light source by end of this financial year, and test it on the 10 meter. And this is the scheme of the squeezer that we're building for our LIGO detector once it's up and running, so that we can arrive at the A+ detector. And this is something that we build completely in-house. This is, again, the bulwark of this is an NPRO technology, laser locking for the PLL cavities, the second harmonic generation, and then building a sub-threshold OPO, which generates the squeeze light for your LIGO part. So this allows us to keep pace with the two detectors that are evolving. From the day that we signed the MOU for transfer technique from them, it was an advanced LIGO. Now it is operating as advanced plus LIGO. We want to keep pace with that, which kind of pushes the limit of the technology that we are building for both optics and lasers, and also contribute later to larger projects, probably in the next decade, both on LIGO Voyager or Einstein telescope, which requires larger masses with better finishes and probably silicon masses at different 2-micron operation. Thank you.
Thank you, Dr. Sandal Raja.
Thank you.
I think you had brought in the laser applications beyond the engineering limits, where we all understood that sky is not the limit. I spoke about the larger cosmic world where things can be captured through our gravitational waves. And wonderful to have this technology to go ahead. And I think we should, as a country, we should take it forward in whatever capacity we can do. This is one thing LIGO has to come, and things has to, we should know more about the world, cosmic world. Thank you. Any questions from?
So, I mean, so nice to see that lots is happening even in spite of all the delays that have happened. I just wanted to know, so now all these technologies that we are getting a handle on, can we quickly transfer them to, find a guy? For example, let's take the example of the ultra narrow line width laser that you have made.
Sure.
Can that be made and sold to the world?
Yes.
I'm just saying, is there a company?
Let me break it down to two parts.
Yeah.
In the case of the ultra narrow line width, this is something that's ready for technology transfer, and the incubation centers, we already in fact putting some documents together. This is not very tough to build. And in fact, without the locking, it provides kilohertz, which is good enough for most of the applications.
Exactly.
So just an N-Pro with the pump diode and the control system is good enough to do that, and that's the first iteration.
What's the cost advantage that?
So, for example, a Memphiso costs you with the noise killer around 40 lakhs. This should be around sub 5 lakhs.
That's what I'm saying. We make for the world.
Yeah. No. We are focusing on the quantum initiative. We are making sure that at least some of the components, for example, in quantum initiative also you need narrow line with lasers.
Yeah.
Colleagues here from the cold atom would also say that some of these techniques could be useful for other applications also in locking their lasers also.
Yeah.
So this is something that we are trying to address in three ways. One, the optics and lasers. So laser part can be technology transferred because that is at the level where it can be done. The squeeze light source we will do for LIGO, but this technology is available to academia to look at communication. Squeeze light communication, SKD distribution, quantum key distribution, other thing. This it's an open collaboration. Anybody who wants to come down, use this facility to learn how to build squeeze light source at lower powers for other applications are welcome. That's one thing. But the optics is completely capital intensive. So we have, with the approval of our director, we have a project which is purely focused on optics development as a spares for LIGO, because you don't want to be held halfway for any geopolitical reason that you have the detector but you don't have space for the detector.
But that can also be sort of commercialized.
But that is in the GOCO model. Okay. So we establish a facility, demonstrate components for our LIGO and the synchrotron beamline, but it will be operated as a kind of a corporate entity. For example, we float the tender for 4 optics. We are looking for a bidder who will use our facility, use our expertise, build those components, raw material, everything is their business, and supply the components to us.
Wow.
So that kind of breaks the catch-22 situation where people complain that we don't have specialized optics in India, so we cannot build something new. But the vendor is also equally right that there's not sufficient capacity to build those, to invest that kind of money. So we are hoping that will break with this part for the optics part.
That's
and
wonderful.
Now coming to the damage threshold part, whatever we do for super polishing for LIGO or for the beamline optics also contributes to damage threshold.
Exactly.
Yeah, so that's a common problem. Here it is scatter. In the case of high energy laser, it's
exactly
damage threshold.
Oh, this is really exciting.
Yeah, so we have all the resources to, for example, the first one that we built was with a kind of a crystal cut from a catalog. For example, the photon GmbH, which gives you for $200 a cut crystal. But we have the capability to cut and polish them also with the required angle. We have done them recently. We're building some based on where we bought a Nd:YAG bowl and we cut them to the required distance. That's a matter of optical fabrication. There's nothing fantastic in it. But to achieve those angles in 3D is a bit of an engineering task. It's not a scientific issue per se. It's an engineering issue.
Hello, sir. So nice talk, sir. Nice efforts also. I'm curious, like how this contamination issues in these optical contamination issues are handling.
Things that is pushed by LIGO. So when my senior colleagues ask me what is the challenging thing in LIGO, these are not challenging. It is maintaining cleanliness, maintaining the clean rooms.
But how we are
and making sure that nobody skips the SOP, saying that chalega ye. So,
but how you monitoring like
so
contamination?
we have 2-3 things that we hope to resolve that by the time we are up and running the observatory. One is this 10 meter. The 10 meter serves multiple purposes. Let me come to that. Yeah, sorry. So the 10 meter is exactly a facility that is similar to one arm of your LIGO detector. It's a big building, 25 by 50, 25 by 75 with an isolated floor, with the cleanliness that has to match with our observatory also. So the SOPs and the practices that we involve here, and all our collaborative people who are going to work at the site have to spend time here to make sure that they learn how to work on the 10 meter with the required. In fact, there's a technique for garbing in LIGO. You have to wear your shoe boots first before you glove up. So it's as pedantic as that. And these were detected empirically. You have no mechanical way of learning it. So you learn from others' mistakes. But this is more of a cultural issue.
But have you developed any procedure like for a quality check and
yeah. So, for example, in the case of optics, you have fluorescence measurement and you have FTIR. So there's a kind of every optics that goes into the vacuum system before pump down has to be wiped with your FTIR sampling, and only when the FTIR passes you can start pumping down. So there's a kind of a set procedure to do that. And that's true for all the in-vacuum components. So the components in LIGO for us will be classified into class A and B. A are that see the UHV, B are that don't see the UHV. But even for the B, there are some stringent ones. But for the A, they're extremely stringent, because you'll appreciate that once the components are inside the vacuum chamber, you cannot break the vacuum chamber. The beam tubes are breakable, but the chamber cannot. So you have to take extreme precaution. And as I mentioned, the noise purely comes from the refractive index modulation, and the hydrocarbons are the worst. Yes. They have the highest possible polarizability. The water vapor is the next one, but water vapor you have large cryopumps in the actual LIGO, which takes care of that. But hydrocarbons, the contamination control is the only way to take care of making sure that you are not noise limited in your interferometer.
And one more thing, sir, like I'm wondering actually why this 4 kilometer harm, like, if you, for example, if you extend still, I mean, any specific reason, like why
so
exactly 4 or like, for example, 6, then we have even more liberty in detection.
There's a reason for that. Yeah. There's a proper reason for that. See, there are 2 things. One is the way the interferometer was initially designed, the mirrors hang from fusilica fibers. And for every kilometer, your local tilt increases by half a degree. By the time you're at 4 kilometers, you're already hanging 1.3 degrees away from the local normal. And if you want to align the interferometer, then you're going to kind of actuate with electrostatic actuators at 1.5 degree, which causes the cross coupling to be very high. To some extent, now that design has been solved. That's why the Voyager goes to 10 kilometers. So that's a kind of an engineering limit. But I think the more political answer is that that's the kind of land that we could get. Which is true in our case also. No, I think here it is free. This is DOE land, but this was a bit of a trouble for them, because there's commercial logging on the other side. But the limiting reason is this cross coupling. Yeah, so you heard our former secretary mentioning yesterday about the DSCM efforts. The HVAC itself is an engineering feat. Your building has to have a temperature stability of 1 degree average and spatial variation of plus or minus 0.5 degree. So that's an engineering feat in HVAC also. So what we routinely tell our CSD division that हमको एक AC चाहिए, वो नहीं चलेगा. And that we are already causing a lot of pain for them in our building itself. They're very unhappy with us that we're including too much into their designs and asking them to do things which is not our domain. So the vacuum level is -11? No, 10 to the minus 9 millibar. Yeah, it's UHV. It's UHV. It essentially comes from the polarizability. It's actually 10 to the minus 8. You have one order of safety margin to make sure.
Sir, why we are specifically using Michelson interferometer when there are other interferometers such as Mark Zander and February period interferometer?
Yeah. So let me come to the Michelson. I think I had a slide there which I probably missed. So let's imagine that the gravitational wave is coming from the plane of the board. It's propagating in this direction towards you from the plane of the board. It's a quadrupolar wave. So if it was exactly oriented in the plus polarization, we were lucky. So in one cycle, this portion of space would be expanding while this is contracting. And in the other cycle, this will be contracting, this will be expanding. Nothing like a Michelson to do that differential measurement, because it is absolutely insensitive to the lambda shift. But still we are building very narrow line lasers for other reason because of the fabric bureau. But otherwise, Michelson is common mode noise rejection is very high. And you only look at the differential arm changes. and they match exactly the quarter flow moment that you want to measure. So Michelson is intrinsically a gravitational detector.
I think we'll conclude, and questions can be, I think, a very interesting field. So we can interact during the dinner time. Thank you, Dr. Sandal Raja.
Thank you.
May I now also call upon Dr. S.V. Nakhe, Director RRCAT, to hand over the momentum to the session chair. Thank you all. And as announced earlier, we have a cultural program in the main auditorium. Please do join there.
हाँ कर रहा हूँ एग्जिट कर देना है तो